In episode 14 of the CySec101 training series, we are going to touch on networking concepts, and this is going to be the introductory networking room for the Cybersecurity 101 pathway of TryHackMe, and this is the very first room inside of the networking module. So we're going to go into some core networking concepts, and then as we go along this module, we're going to get more expansive, and we're going to talk about other concepts, security concepts, and then we're going to actually use some security tools that are very, very useful inside of networking. So first, we're going to have a word from our sponsor, and then from there, we're going to jump into the introduction. This episode is sponsored by the Hackaholics Anonymous membership community, which is the premier membership community for security professionals and hackers. And as a part of this community, you will get access to 4 tiers of benefits, and it starts with the supporter tier, which gets their own Discord server, as well as access to me directly and our advanced members, as well as early access to content, so on and so forth. And then there are the advanced members who get access to Python automations every month. They get access to live streams, exclusive content, exclusive downloads, very much like the Security Plus documents, as well as the practice examinations that we're going to be launching in a little bit. So to be able to join the Hackaholics Anonymous community, you can just go through the link in the description below, or you can go to our homepage and click the join button there, or you can simply go to youtube.com/@hankhackshackers/join, and then you will be taken directly to the join page. And I really look forward to seeing you in the community as well as in the Discord servers. And without further ado, let's actually jump into the networking concepts room. All right, so have you ever wondered why you need an IP address to access the internet? Is it true that an IP address can actually uniquely identify the user? Are you curious to learn what the life of a packet looks like? Are you curious to know what even a packet is, right? If you have any of those questions, you are probably a nerd just like me. And then you're going to get all of your questions answered inside of this room, as well as all the following rooms. This is going to be the first room in the networking module that's available for CySec 101. And in the very next video is going to be networking essentials. Then we're going to talk about the core protocols, as well as the secure versions of those core protocols. The prerequisites for this room and for this module are the pre-security path, which is like pre-kindergarten for people inside of the security and IT world. So I have done a lot of these videos, and they do exist on the channel. If you go to the earliest videos that are on the channel, basically the oldest videos that are on the channel, you'll get a lot of these videos available too. So offensive security intro, defensive security intro, what is networking, intro to LAN, the OSI model, and we're going to review a lot of these things again today. So if you haven't seen them, or if you don't want to go watch them right away, you're not going to miss much, because again, it's like pre-kindergarten for security. So we're going to review a lot of those things in the room today as well. But it is nice to get multiple exposures to these concepts, because it's a little bit easier to wrap your head around them. So if you've never heard of the ISO model, for example, then hearing it for the first time may be a little bit challenging, but it's not that bad, because again, we're just going to review these things in detail, and the more exposure you get to all of these concepts, the easier you'll wrap your head around them. The objectives that we have today are the ISO OSI network model, the IP addresses, subnets, and routing, and then the TCP, UDP, and port numbers, and of course, how to connect to an open TCP port from the command line. So that's going to be a practical exercise that we're going to run at the very end of this room. So let us get ready. Hopefully you're actually ready to go. This is actually one of the free rooms inside of TryHackMe. So anybody with just a basic free membership can deploy the virtual machines inside of this room. And then if you're interested in just getting the paid membership, it's literally $12 a month. And if you use the link in the description below, you will get a $5 discount off of that. So it'll make it even more accessible to you. So if you have not done so, definitely get yourself a membership to TryHackMe. Even if you just get a free membership, there's literally hundreds of rooms that are available for the free members. And then when you get into the paid membership, you just get some really, really dope stuff for the advanced teachings and everything like that. So that being said, let's actually jump into the OSI model. So if you've never been exposed to this, at first glance, it might seem complicated, but again, it's, just going through this repeatedly will make it click a little bit more. And I'm going to give you a couple of like cheat phrases that you can use to remember these things. And we'll look at some visuals to make it a little bit easier for you to wrap your head around it. And ultimately, I feel like you'll grab it fairly quickly. I think it's fairly easy, especially for somebody that's gone through it, that I had challenges. Now I know exactly how to teach it so that it makes it easier for you to understand. So we're not going to go super technical with this. We'll be conceptual so that you actually can wrap your head around it fairly easily. So ISO, which is the International Organization for Standardization, created the OSI model, which is the conceptual model, and it's more theoretical, and then we're going to talk about the practical model when we talk about TCP/IP. But the OSI model is basically the theoretical conceptual model behind communications across networks. So what needs to happen for my computer to talk to the YouTube server, and then what needs to happen for your phone or for your computer to get data from the YouTube server, and how do we actually establish this connection? What needs to take place, right? What are the individual steps? And what's really cool about this is that this happens in literally a fraction of a few seconds. So it's like it happens so quickly that it's kind of mind-boggling to wrap your head around the fact that these 7 steps, basically, these 7 layers, as we like to call them, they literally, it happens in a second. It happens in a couple of seconds. Now, it didn't happen like this at the very beginnings of the internet, because the internet was super slow around the time of America Online, right? So around that time, it was not fast. But right now, in the modern era of the internet, it's so fast for data to go through all of these layers that it's like, what is actually happening? So, it's good for you to understand networking. This is more for people who really want to be network admins and network engineers, that you would go into the depths of this stuff. But as a cybersecurity person, it's still important for you to understand this, because you will need to know what layers you have to protect, what protection actually means for each of these layers, and then, of course, how you would hack each of these layers if you actually were hired to be a pen tester or an ethical hacker. So, it starts with the physical layer being number 1, but then usually when you look at a visual like this, the application layer is actually the top layer. So we go from bottom to top in this model. When we talk about the TCP/IP layer, we're going to be going from top to bottom, and that's just another thing that they wanted to confuse us with, so they decided to flip it upside down. But basically, it goes from the number 1 to the top. And the way that I was taught to remember this was, if you look at the first letter of each one of these things, it can be, please do not throw sausage pizza away. So repeat that. Please do not throw sausage pizza away. Physical data network transport session presentation application. Please do not throw sausage pizza away. Please do not throw sausage pizza away. So if you repeat that a few times to yourself, you will most likely wrap your head around the organization of this, and then from there you can just kind of fill in the blanks, right? So the very first layer is going to be the physical layer, and it's referred to as layer number 1, and it deals with the physical connections between devices. So this is like the wires, right? The actual physical wires, and basically what it means to have binary data. So the zeros and ones that go through those physical wires, and that's how the communication starts, right? So if you are connected on a laptop, for example, there is no physical wire, most likely, that's connecting you to your router or your modem. So you're getting a Wi-Fi signal. But your router or your modem has a physical wire that's connected to it, that's coming from the cables outside in those beams, like those electricity beams, the big columns that are along the lines of every major street. And there's a physical wire that's running into your house that will get you access to the internet. And then from there is a Wi-Fi signal that's just distributed. So everything starts with that physical layer. And what goes through those wires is a series of binary digits, which is a bunch of zeros and ones, basically. So it can go through electrical wire, optical wire, and wireless signals as well. And all of those things technically fall under the physical layer. So in addition to the Ethernet cable, which is what you can see right here, this is what an Ethernet cable looks like. There's also the optical fiber cable, which is a much thinner version of this, and it actually has glass that goes through it, and you don't want to bend that in a sharp layer because you'll break the glass and then you won't be able to get your connection. So the optical fiber cables, fiber optics, are much more sensitive than these types of Ethernet cables, and they actually are much faster. And then so you have the Wi-Fi radio bands as well, which goes from 2.4 to 5 to 6 gigahertz of data that can transfer through those things. And if you have a 6 gigahertz band, obviously you have a much faster internet connection than a 2.4 gigahertz band. And usually when they connect your Wi-Fi for you, you at least have the option of 2 of these things if you have a decent Wi-Fi internet service provider. But that's basically it for the physical layer, right? And then we have the data link layer. The data link layer is what transmits the actual signal, right? So the data link, otherwise known as layer 2, represents the protocol that enables data transfer between nodes on the same network segment. So let me actually show you something that kind of makes this a little bit easier to understand. Okay, so I basically found this image by just Googling routers, switches, and modems. And this is what it's one network. This is representing one specific location. We can call it a floor, we can call somebody's apartment, so on and so forth. Now, most people don't actually have a switch. This is what this thing represents in the middle. And then each one of these dots that you see right here would have an Ethernet cable that's connected to them, and then it runs from that to the TV, to the recorder, so on and so forth. So most people in a home network don't have a switch. Most people in a home network will have either a modem and a router, or they'll have a router that has the modem connection in it. So typically what happens, you get your internet from your internet service provider, they hardwire an Ethernet cable or a coax cable that will go from the outside world and connect to your modem, and then the modem will have the Ethernet cable that connects to the router, and then the router will typically send out the Wi-Fi signal for all of your devices. In the modern world, most people don't have an Ethernet cable that connects from their router to their computer. You can have that. That's actually not a bad thing to do because it gives you a stronger, more persistent connection. But in the modern world, most people don't have that. In our home network, we don't have that. We have a really good router. It's very secure. It has its own firewall and everything like that. But it also acts as the modem. And then that sends the data out to the various devices that are inside of our house, all the TVs and the laptops and the computers and all of that stuff. And this is all considered to be the part of the data link layer. These devices being in the same network as they communicate with each other, this is all done through the data link layer. And the way that they communicate with each other is not through the IP addresses, because technically they're still in the same network. So they more communicate with each other through what's called as a MAC address, which is the media access control address. And the MAC address is the physical address for the device. And then there's something called the ARP protocol, the address resolution protocol, that we'll talk about in the next video, that will show you the translation between the MAC address to the IP address and how devices on the same network actually find each other via the MAC address and the IP address, so on and so forth. So this is essentially data link layer 2, right? So data link layer is layer 2. It's the layer right after the physical layer that gets the wires into the network. And then this is the way that the devices on the same network, so this is like the big thing, the big piece that you have to remember. Data link layer takes the devices that are on the same network and connects them to each other, right? Helps them communicate with each other. And there are certain protocols. So this is the IEEE code for Ethernet, which is 802.3, and then there's the 802.11 that represents the Wi-Fi, and these are just standards. So if we were to go look at this one more time, IEEE, Institute of, I think, let's see, stands for, it's a standard, but let's see what it stands for. So Institute of Electrical and Electronics Engineers, okay? And so this institute has the standards that we would use to make sure that everything is set up properly in networking. So for example, if you do 802.11, this is the standard for Wi-Fi. So this is the set of standards that define the physical layer and medium access control protocols for wireless local network communication. So this is Wi-Fi standards for that organization, which is the Institute for Electrical and Electronics Engineers. Okay, we can call it IEEE, which is probably an easier to, instead of saying IEEE or whatever, we're just going to say IEEE. But that's basically it. And the IEEE has a bunch of different standards. It's just that for the purpose of this video and this conversation, we're more interested with the Ethernet standards as well as the Wi-Fi standards. And the Ethernet standards are the ones that typically talk about the physical connection and then the connection of that to the data link layer. And the data link layer is what starts connecting to the actual Wi-Fi, the wireless connection, and the way that that links to our next layer, which is going to be layer 3, the network layer. So this is just an example that what you need to see is of what a MAC address looks like. So this is a unique MAC address that belongs to, I don't know what type of device this belongs to, but this is basically what a MAC address kind of looks like, right? So we expect to see 2 MAC addresses in each frame in a real network communication over the Ethernet or Wi-Fi. And this is what it looks like as far as the connection is concerned. So we have the destination that's in yellow, we have the source that's in blue, and then the remaining bits show the actual data that's being sent. So in this particular case, I mean, it doesn't really zoom in that much on it, but we can actually kind of just zoom in this way. So you can see these portions right here. These are all ones and zeros. So this is the binary. And then this portion right here, this is the hex code, hexadecimal code. And the yellow right here is the destination. The blue represents the source. And then over here, the yellow is the destination and the blue represents the source. And that's what it looks like when you're talking about a specific Ethernet or layer 2 connection in this situation, which is connecting to the CloudNet device, so on and so forth. So this is a screenshot of Wireshark, and we're going to be talking about Wireshark as we go further along inside of this module. And it's a really powerful tool, a very useful tool for sniffing network traffic, and it's free, which is one of the things that I love about it so much, which makes it very easy and convenient for people who want to become hackers to become hackers or network administrators. You can just download free software that is an industry standard. Like, everybody knows Wireshark. And if you don't know Wireshark, then you can't call yourself a security person. So let's talk about layer 3. Now, layer 3 is where the data link layer connects to the actual internet. So the data link layer is data on the same network, right? Data link layer is on the same network in the same location. The network layer is concerned with sending data between different networks. So in more technical terms, it handles the logical addressing and routing, basically finding a path to transfer network packets between diverse networks. So what you're watching, this video that you're watching, is basically a bunch of data packets that are being sent to you from the YouTube servers, and that's being done from their location of their server to your device. So your laptop, your computer, whatever, your phone. That's being sent from them to you through the air, right, through the internet, and it's being sent via these little packets, and it's being sent through the network layer. In the data link layer, we gave an example of one company office with 10 computers in the same office, which we didn't really talk about. I kind of skimmed over that. But let's say that so if the data link layer is connecting all those computers in the same office, which is what this is right here, right? So we have these computers and these devices that are in the same location, in the same office. They're being communicated via the data link layer. If the company has a bunch of different offices across different cities or countries or even continents, then the network layer is responsible for connecting all of those nodes, all of those computers to each other. So this is what that potentially looks like. You have computer A that's in one location, you have computer B that's in another location, and then these are all individual routers. So a packet will go through this router and then maybe this router and then come to this router and then connect to this person, or maybe they'll go from this router to this router and directly just go there because that's the fastest route possible. But sometimes maybe this one is down, so it has to go. So there's different routes that a packet can take depending on what is going on in the world and inside of the network communications devices that are available for all the routers that are available. So that's basically what it looks like. So it'll go from its own computer it goes to the local router that's inside of that room. Then it'll bounce and go to a variety of other routers across the world, which are usually provided by the internet service provider. And then it'll end up at the router for this computer that's inside the room with that computer. And then it'll send it to the actual computer. That's typically what the network layer looks like. So you have examples, and we already talked about the examples for this already. So I already talked about those examples. So the examples of the network layer would be things like the Internet Message Control Protocol or Internet Control Message Protocol, ICMP. We have the Internet Protocol, which is IP. You have Virtual Private Networks, VPNs, and of course IPsec or IPsec, and then SSL and TLS via VPNs. These are all examples of the network layer protocols. And then we have the transport layer. So the transport layer actually enables the end-to-end communication between applications on different hosts. So now it's going from my email provider to your email provider. That's the application. And the transport layer connects those two applications together, right? So it enables the communication between those running applications. Maybe it doesn't connect them, but it allows them to communicate with each other. So your web browser, for example, is connected to my web browser, is connected to TryHackMe over the transport layer, which is going to come up in a little bit. And or actually we're literally on the transport layer. So the web browser is connected to TryHackMe. Mine is connected to the TryHackMe web server over the transport layer, which supports various functions like the flow control, segmentation, and any error correction that needs to take place. And there are two very key protocols for the transport layer, which is the TCP, Transmission Control Protocol, that requires the verification of a connection. And then you have the UDP, the User Datagram Protocol, that does not require the verification of a connection. So what you're watching right now through a video from a streaming platform, which is YouTube, most likely is using UDP, which is sometimes why the quality of the video isn't perfect, because sometimes it'll be pixelated because the internet connection is kind of lagging, or you're not receiving all of the data packets. So it's not as important to get a perfect connection through the video streaming platforms. And you've probably recognized this in a lot of different, and it happens even with Netflix or with Amazon Prime or something like that. Any kind of video streaming uses UDP because it's quicker, so it can send data packets faster, but it doesn't require the confirmation of a connection. TCP requires the confirmation of a connection. We'll talk about that in more detail later. But all of this basically happens on the transport layer. So the transport layer, if you can think about the network layer connecting the actual computers to each other, the transport layer connects applications to each other. So we have my web server, for example, or my web browser connecting to the TryHackMe web server. You have your web or your YouTube application or your YouTube web browser that's connecting to the YouTube server. So that's all being done for between applications, the communications between applications. And then what happens is that once that communication is permitted and it's done through either of these protocols, then a session is generated. When a session is generated, it establishes, maintains, and synchronizes that communication between the applications. And it can mean initiating communications between applications, negotiating the necessary parameters for the session. It can also mean that data synchronization ensures that the data is transmitted in the correct order, and it has recovery in case of transmission failure. So imagine you close this browser, or accidentally something happens that the browser crashes. When you come back to this video, most likely it's going to pick up from where it left off, because you had a session that was generated for viewing this video, and then YouTube allows for those sessions to just be recovered so that you don't have to start from the beginning. And if I'm uploading a video to YouTube and something happens and before the upload is completed and that crashes, when I go back, or maybe like my external drive gets disconnected or something, when I go back to continue that upload, it'll allow me to continue from where I left off, and it won't restart the upload from the very beginning. I just basically pick up from where I left off, and that's very, very useful in recovery situations. A network file system, for example, is a very, very important one. So it's basically a file system, a file share that's being accessed over the internet connection. So somebody that's working in a remote location that needs to access this thing. So they would do a remote call to the file system. And then once they have their established connection, that session is generated, and then they can access the data, ensuring that it's actually transmitted in the correct order. And then if there's any kind of failure, they actually can recover that session. And then we have the presentation layer. So the presentation layer just makes sure that the data is delivered in a way that the application that you're using can understand it. So this is responsible for basically the data encoding, compression, or encryption of the data. So for example, you have the ASCII encoding or the Unicode encoding. And an easy way to understand this is that if you have an image that you're sending through an email, you can have JPEG, GIF. I pronounce it GIF. I don't trust anybody who pronounces as a GIF. And then you have the PNG. So these are a variety of different ways that an image can be encoded, right? And they serve different purposes. So for example, if you want a transparent background, you have to have a PNG file, because GIF or JPEG typically doesn't support transparent backgrounds. And then GIFs are usually for animated images, so you can't have PNGs who are animated. So if you have an animated image, it's a GIF typically. So it's different types of encoding that's available for these things. So even though it's hidden from the user's email client, we use the multi-purpose internet mail extension to attach the file to the email, and then MIME encodes a binary using 7-bit ASCII characters. So what you see if you're capturing that email is not the actual image, you just see ASCII characters, which is another version of encoding. So this is what's kind of interesting and important to understand, is that the presentation layer really has nothing to do with the data visually being presentable. That's for the application to present. The presentation layer just makes it so that the encoding, compression, and encryption, and then ultimately that going through the session layer and the transport layer, it makes it so that all those things are actually possible. And then you get to the application layer that actually views it, right? It makes it viewable to you. So it could be through your email. HTTP protocol is to request a file, submit a form, upload a file. You also use the HTTP protocol to connect your Gmail address and receive your data. And then there's the secure version of it, which is HTTPS. And then you have a lot of layer 7 protocols like file transfer protocol, domain name services, POP3, SMTP, and IMAP, which are all used for email. So you don't need to memorize these things. There's literally thousands of ports and protocols, and I don't think anybody's expected to remember that stuff unless you are just a genius with remembering things, which I'm not. I'm not good at data retention, but I'm really good at knowing where to find information. And that's the big thing that is important in a lot of environments, just knowing how to find the information and access that data. So that is what we got for the application layer. So just going back to the top real quick, just so I can show you this, right? So, you start with the application. That's how you interact with your phone or your computer. The application then sends that data, those data packets, to the presentation layer, the session layer, the transport layer, the network, the data link, and then the physical layer. It goes through all of this just to leave your house, to leave your network. And then it travels over the internet and then ends up at where it's supposed to end up. And then it goes through the physical layer, the data, and it just reverses until it gets to the application layer. So let's say that's for YouTube. You're trying to access a video on YouTube. You go and you submit your search query, you find the video, and then you click on the video. And all of that stuff that you're doing is going from your application layer all the way to the physical layer, and then ending up on the other side on the physical layer, going to the application layer, and then the YouTube server sends the video from their application layer to their physical layer, and then that comes back to your phone or your laptop, connects to your physical layer, then comes to the application layer so that you can actually play the video and watch the video. And that happens in a matter of seconds, not even a second sometimes, right? So this is what's interesting to understand. And this is what's amazing about the modern internet, is that it's so freaking fast. And it goes through all these different layers in a fraction of a second. And then you get access to your video and you get to do whatever the hell that you want to do, right? So This is just a little cheat sheet that you have available for you. So if you wanted to look at what these things are, but then there are so many different cheat sheets. So we can always go to Google right here and then actually just type in the ISO cheat sheet, let's say ISO cheat sheet, and then you'll get a bunch of different cheat sheets that will make it. And some of them are really detail oriented. Some of them are just very, surface level, kind of like this one. So if just depending on how much detail you want, there's a lot of stuff that's available for you that you can skim through so you can wrap your head around this whole thing. I like visuals that make me kind of just get everything in one image. And that, I think, is one of the big things that's also really powerful with the internet nowadays, that you can just basically click on something and you will get the visualization of a complicated concept all in one image. And then that way you can really easily wrap your head around it. So just find something that is appealing to you and save it for yourself. And that's how you can remember these various letters. And obviously, always remember, please do not throw sausage pizza away. Okay? Please do not throw sausage pizza away. That's how you can remember these layers. Okay, so which layer is responsible for connecting one application to another? So we talked about end-to-end connection of applications, and that was done through the transport layer. That's where end-to-end connection of applications happens, and it's done through UDP or the TCP protocols. Which layer is responsible for routing packets to the proper network? So this is where it goes from the data link layer to the network layer, and it goes from network to network, and packets are sent through routers. So if you can recall the image that we had over here, these are routers, right? So it goes from this guy's network through routers, and it gets routed to this guy's network, and that's done through the network layer. And then in the OSI model, which layer is responsible for encoding the application data? And that's layer 6 that we talk about over here, which is data encoding, encryption, and compression. And then finally, we have which layer is responsible for transferring data between hosts that are on the same network segment, which is what you see over here. This is the same network segment, and that is done through the data link layer, which is layer 2. So that's what we have for the ISO model. And now let's look at the modern version of this, where we actually, where network administrators and network engineers actually implement this into the real world. And that's done through the TCP/IP model. The TCP/IP stands for Transmission Control Protocol and the Internet Protocol. So TCP, Transmission Control Protocol, and then IP, Internet Protocol. This was developed in the 70s by the Department of Defense. And they did it mainly because they wanted to make sure that they have a process to manage something if it ever happened where they got a military attack for whatever. It allows the network to continue to function as it's a part of an out-of-service network, for example. It's possible due to the design of the routing protocols to adapt as the network topology changes, right? So you have a variety of different network topologies, which we've talked about previously. And once you kind of go through that, you can understand that the routing protocols still need to be consistent, even if the topology of the network changes, meaning the physical layout of the network. Network topology refers to the physical layout of the network, and the data still needs to transfer, and it needs to route properly no matter what the physical layout of the network is. Now, what happens is that because of the update of it, if we do ISO versus TCP IP, we can see that this is actually, they've combined the two, or not combined the two, they've combined multiple layers. And what it looks like is instead of having 7 layers, we actually have 4 layers. So let me actually kind of zoom out of this so you can see this a little bit better. So instead of having 7 layers, you actually have 4 layers. And the first 2 layers right here, the physical and data link, go into the network interface. Then you have the network, which is also the network, but they call this the internet layer. Transport is still transport. And then the 7 up here, 7, 6, and 5. So session, presentation, and application are falling all under the application layer of the TCP/IP. So these 7 have now been turned into 3. Right? Or excuse me, 4. Sorry. These 7 have been turned into 4. The data link and physical layers have been combined together. Network is still network, or otherwise interchangeable, is called internet. So either network or internet layer. You have transport, which is still the same. And then session, presentation, and application are all under the application layer, because technically they are all done through the application. So Google Chrome will generate a session. It will go through the encoding of the data to make it presentable, and then it will actually present it to you via the application Google Chrome, and it's all done under the application layer. So when you look at it like that, this is basically what it breaks down to. Now, this is not as user-friendly as the image that you just saw, because it's it is basically still the same. So you have the application, presentation, and session layers, which all fall under the application layer, and the protocols are still the same, right? HTTP, FTP, Telnet, so on and so forth. Transportation is still the transport layer. Network layer is the internet layer, which is ICMP, IP, so on and so forth. And then data link and the physical layer all fall under the link layer, which is Ethernet and Wi-Fi. There are versions of this that actually turn it, instead of 4 layers, into 5 layers. And basically what they've done is that they've added the physical layer. So they've added another line item for the physical layer, so to differentiate between this. But this, the application session and presentation are also still the application layer. The transport layer is still the same. Network is still the same. It's just that these last two right here, or the first two, I guess we can call them, these two have actually been separated. So you have the link layer as well as the physical layer. And that was something that was done by, by Kouros and Ross in their book, Computer Networking, a Top-Down Approach. And I guess it's important enough for them to mention to us. So most places, though, they worry about the 4 layers of TCP/IP. They're not considered about this version where it has 5 layers. As long as you know what the layers are and how they break down, that's basically the most important part of this whole thing. So to which layer does the HTTP belong in TCP/IP model? And that is the application layer, because HTTP, again, is application, presentation, and session. That's all falling under one layer inside of the TCP/IP model. And then how many layers of the OSI model does the application layer actually cover? And that is 3, right? Again, application, presentation, and session, all combined into one layer in the application model, or the application layer of the TCP/IP model. So now, let's talk about IP addresses and subnets. When you think about an IP address, you most likely recognize this as an IP address or this as an IP address, and this is considered a IPv4 IP address. Now, what happened is that there's approximately 4 billion types of, or 4 billion different unique IP addresses that can come up with IPv4, and across the world, there are way more than 4 billion devices. So ultimately, it runs out. But there has been some interesting things that internet service providers have done so that people can still deal with IPv4, but it eventually graduated into becoming IPv6, which is a very different type of formatting. And because it offers more positions in it and more variations, it can now generate many, many, many more unique IP addresses if you use IPv6. But for the most part, in the world today, we are still dealing with IPv4 formats of IP addresses. The main reason for this is because every host on a network needs a unique identifier so that the other host can communicate with it. Without the unique identifier, the host can't be found without ambiguity, meaning we can't know for sure what the address of a specific device is. So if you think about it as the home address, the postal address of a person, your postal address will allow the UPS or USPS or whatever the mail service is to actually find you specifically without ambiguity, right? Otherwise, your package is going to get delivered to somebody else. You won't be able to shop online. So that's what's important about IP addresses in the world of the internet, is that you are found specifically. And there's IPv4, obviously we talked about IPv6 as well. And the big thing that's very important to understand about IPv4, and this is where the details of subnets become a very important detail. It's not that confusing. I'm going to try to make it super simple for you, okay? The big thing is IPv4 addresses are 32 bits and they contain 4 octets. So if you can consider an octet like an octopus, right? If you can consider an octet to be 8 bits, If you divide 32 by 8, that means you have 4 octets, okay? Each one of these positions, so everything that's separated by this dot in the middle right here, that's 1 octet. So you have octet 1, octet 2, octet 3, octet 4. It goes from 0 to 255. Each octet goes from 0 to 255. However, the IP address itself will not actually include 0 or 255. Why? 0, so 192.168.1.0, is the network address. And then 255 is the broadcast address. So the IP address that your laptop will actually get is going to be between 1 and 254, okay? So you will never find an actual IP address of a machine that will be ending in 0 or 255, because the 0 is the network's address and then 255 is the broadcast address, and every machine on that network is going to have the same network address and the same broadcast address, but the unique IP for that machine is going to be from 1 to 254, okay? Hopefully that made sense. Now, what we need to understand is that there's something called a subnet, and the subnet is what kind of makes things accessible for either a small environment like your house or a business environment that has thousands of employees and thousands of machines, okay? So first you need to know how to pull up your configuration. So if you're using Unix or Linux, which, Mac OS is technically Unix, you would use ifconfig, and then it pulls up your IP data. And so in this machine, on this particular machine, the IP address is this, right? Ends in 89. The network mask is this, and I'll explain what this means in a little bit. And then we have the broadcast address that ends in 255, right? And then the actual network address, I don't think is on here, but the network address would be the one that ends in 0, okay? But the broadcast address, as we established, ends in 255, okay? So this is the IPv6 address. Notice how this is such a very different view than this one right here. And if you can imagine, because there are so many different variations, so this one actually has letters in it, right? So this one is only numbers. This one actually has letters. And so when you look at this, first of all, it's separated by 5 different chunks of data, and then there's letters in it, which means that you can have many, many more variations, billions. I think it's like centibillion, something. I don't know what the word is, but there's so many more billions. There are many more billions variations of the IPv6 than there are of the IPv4, okay? But this is basically what the output of ifconfig looks like. There's another command that allows you to look at it, which is the IP, and then AS is the address show. So AS stands for IP address show, and then that basically shows you a very similar output. Now, what we need to understand is mainly, because the output is similar for the most part. So it has the IP address still, but and then we have the IPv6 as well. But the difference here, the key difference here, is the subnet representation is different in ifconfig, because it actually shows you the network mask, which is the subnet over here like that. Over here, the subnet is represented by the /24. And the reason why that's important, okay? So going back to the concept of octets. So if we think that this is 8, this is 8, and this is 8, if we do 3 times 8, that means there's 24. So that's what the /24 represents. Meaning, this last position is the only position that will get filled in. So on this subnet, there can be between 1 to 254 addresses that can exist on that subnet. Now, the reason why this is important is when you go into the enterprise environment, their subnet is probably going to be 255.255.0.0, which means what? If we do 8 times 2, it would give us a subnet of 16, meaning that 16 positions, 16 bits on this are not going to be filled in, and then the other 16 will be filled in. In this one, 24 is not going to be filled in, and then the last 8 is going to be filled in, okay? That's how you can kind of understand this. When you see /24, that means 24 bits will not be filled in. They're going to stay exactly the same. So you see 192.168.66, 192.168.66. So that portion is not going to change. However, the last bit, the last 8 bits will actually change. And if you have an enterprise environment that has these two that are not going to change, but the last two will change, now you have 254 times 254, which ends up being 65,000 plus addresses that can be assigned on that network, which is way more conducive to a enterprise network in a business environment, because they have way more than 254 IP addresses. Most people, because they have their cell phone and their laptop and their desktop for work, the average employee will take up 3 IP addresses. You know what I'm saying? So if you have one person taking up 3 IP addresses, for the most part, you can probably have maybe around 100 employees, a little bit less. So let's say 80 employees that will comfortably be on that network. Anything more than an 80 employee environment, they need to have a larger subnet, because they just need way more than 254 addresses, right? So that is why a subnet looks the way that it does. And that's what it is. So if you can kind of just wrap your head around the fact that this piece, the /24, is representing the number of octets that will not be filled in. So if you divide it by 8, that means 3 positions are not going to be filled in. And then if it's 16, that means these 2 positions are not going to be filled in. And if it's 8, which, I mean, I can't imagine that there would be 8, that means that this first one isn't going to be filled in. These last 3 will actually be changed. So that's kind of what you can think about in that kind of an environment. So now that we have that out of the way, let's talk about private addresses. Now, we're going to talk about network address translation in a little bit, but what's important to know is that any IP address that starts with a 10, 172, or 192 is a private IP address, and this is by the RFC, which is the Request for Comments, a publication that's for the Principal Technical Development of the Internet Engineering Task Force, okay? That's, again, kind of like extra information that you really don't need. But you do need to understand that anything that starts with a 10, anything that starts with a 172, or anything that starts with a 192 is a private address. So for this lab that we're using, we're going to actually have this machine right here, which is a target IP address that was created for my virtual machine, and it starts with a 10, which means that this is actually a private IP address that belongs to TryHackMe. And when I'm done with this session, when I terminate this is going to go away, and this IP address will no longer be valid. Okay, so hopefully you can kind of wrap your head around this and understand how this whole thing works out. So remember, if it starts with a 10, 172, or 192, these are private addresses. That's very important to understand. Now, we presented earlier an analogy using public IP like your home postal address. A private IP address is different. The original idea is that it cannot reach or be reached from the outside world. It's like an isolated city or a compound where all the houses and apartments are numbered systematically and can actually exchange mail with each other, but they cannot exchange with the outside world. For a private IP to access the internet, the network address translation is what is used to create a public IP address so that it can actually communicate with the outside world. We're going to talk about this later on in this series, so I'm not going to jump too deep into it. But we do need to understand that if it starts with a 10 or 172 or 192, for the most part, that is a private IP address, okay? And then we have the routing concept. So imagine that the router is your local post office. You send your packets or your data or your packages and mail to the post office. The post office will process it. It'll send it to maybe another post office, and then it'll send it to another post office, and finally end up in the final post office for where it's supposed to be delivered to. And then in that place, it's going to send it to the actual person or the entity that's supposed to receive it. So you hand them the mail parcel, they know how to deliver it. If we dig deeper, you might mail something to an address in another city or a country. The post office will check the address and decide where to send it next. For example, it is to leave the country. We expect the central office to handle all of the shipments abroad. In technical terms, a router forwards data packets to the proper network. Usually, the packet passes through multiple routers before it reaches the final destination. The router functions at layer 3, which is the network layer, or the internet layer, inspecting the IP address and forwarding the packet to the best network router so that the packet gets close to its destination. So it goes from this, goes to this router, then to this router, and then this router, and then this person, or this router, and then this person. Does that make sense? So it goes through routers. Routers route. That's how you can kind of remember that, right? So here we go. Which of the following IP addresses is not a private address? So starts with 192, it's all good. Starts with 10, all good. 172, all good. If it starts with a 49, that is a public IP address. And that is the answer. Which of the following addresses is not a valid IP address? So remember, it needs to go from 1 to 254. Every single position can go from 1 to 254. So if it's going to 305, that means that this is not a proper IP address because it passed 254. It can be on 254, it can be 250, it can be anything between 1 and 254. If it goes past 254, that means it is not the IP address. So that is actually the right answer. So let's talk about UDP and TCP. So if we go back to the transport layer of how data gets transported, we can talk about, or we can remember that the transport protocols are UDP and TCP. Now, UDP, the user datagram protocol, allows you to reach a specific process on the host, very similar to TCP. It's a connectionless protocol, meaning that you don't need any kind of connection to be fully established, right? It doesn't even provide a mechanism to know whether or not the packet has actually been delivered, right? Which is why if you're watching a video and sometimes it doesn't come through at its full quality, it's because UDP doesn't care, right? It doesn't give a darn. I was about to start cussing. It doesn't care whether or not the packet's been delivered. It just sends the packets. And whether or not you deliver or whether or not you receive it, it doesn't care, okay? So the IP address identifies the host. We need a mechanism to determine the sending and receiving of that process, and it can be done by port numbers. A port number uses 2 octets, consequently, it ranges between 1 and 65,000 and change. Port 0 is reserved. So the number 65,535 is calculated by the expression 2 to the 16th power minus 1. Again, a lot of detail. You don't necessarily need this unless you're just going to become a network wizard, right? A real life similar to UDP is standard mail with no delivery confirmation. So there's no guarantee that the packet has been received successfully, similar to the case of sending a parcel using standard mail with no confirmation of delivery or tracking number or anything like that. In the case of standard mail, it means a cheaper cost than the mail delivery option with confirmation. In the case of UDP, it means better speed than the transport protocol that provides confirmation. So what if you want something that actually acknowledges received packets or provides confirmation? Then you go into TCP. TCP is a connection-oriented transport protocol. It's not connectionless, right? It uses various mechanisms to ensure reliable data delivery sent by different processes on the host. Like UDP, it is a layer 4 protocol because it's transport. Being connection-oriented, it requires the establishment of a TCP connection. So this one actually really cares that the data has been delivered, right? In TCP, each data octet has a sequence number. This makes it easy for the receiver to identify lost or duplicated packets. The receiver, on the other hand, acknowledges the reception of data with an acknowledgement number specifying the last received octet. And in this case, we need something called the three-way handshake to be actually completed. We also call it the TCP handshake, but it's basically 3 shakes of hands, or 3, I don't know. It's a 3-way handshake, whatever. There are 2 types of flags that we use, which is the synchronized packet and the acknowledgement packet. So the first one that's sent out is the SYN packet. The next one is the SYN acknowledgement packet. And then the final one is the acknowledgement packet. So you, as the person requesting, the client, you as the client, initiate the connection and you send a synchronization packet. And you say, hey, I'm just trying to find the connection to this. Here's my initial sequence number. The server will respond to your to your synchronization request by giving you a synchronization acknowledgement. So I acknowledge that you're trying to synchronize with me. And then it adds the sequence number randomly chosen by the server. So you send your sequence number, it sends its sequence number, And then at the final stage, you send the final acknowledgement saying, yes, okay, great. I acknowledge that you're acknowledging my synchronization, and I will send you my final acknowledgement, which means if this has been sent, if you see an ACK package, that means that the connection is actually been done. And this is what the visual looks like. Client sends the synchronization. Server sends, okay, I acknowledge your synchronization request. Client says, cool, I acknowledge your acknowledgement, and we are officially done. So similar to UDP, TCP identifies the process of initiating or waiting, which means listening, for a connection using port numbers. So there are TCP listening, UDP listening ports. They both connect via port numbers. And a valid port number ranges from 1 to 65,535 because it uses 2 octets and port 0 is reserved, So, which protocol requires a 3-way handshake? That would be TCP. What is the approximate number of port numbers in thousands? It's 65,000. And this 2-octet thing, so if you remember, if we go at the subnet example and we have 255.255.0.0, that means the last 2 octets are now reserved for that communication. And if you do 255 times 255, it ends up being 65,000 and some change. So that's basically how you get that. So let's talk about encapsulation, and then we can go into our example at the very end where we run some of these things practically, and then we can talk about our closing notes and our conclusion, and then we'll be done. Encapsulation refers to the process of every layer adding a header and sometimes a trailer to the received unit of data and then sending the encapsulated unit to the layer below. So the best way that I can explain this is through a visual, and I hope that I can find actually a really good one for you. So let's see what we can find as an example here. Okay, so unfortunately, I wasn't able to find an example that I was taught that I was looking for. But one of the best ways to actually think about it is what the term encapsulation really means in general. So encapsulation in general means you take something and you put it inside of a capsule. So you take whatever this is a programming example where they're taking variables and methods and putting it inside of the capsule to create a class, okay? But in general, this is the networking example where you have the actual data, and then on the link layer, you have the data, and then on the internet layer, you have the IP header and the data, and then on the transport layer, you have the UDP layer as well as the data, and then you have the application layer, which is the actual data. And all of these things are encapsulated, right? They are put inside of one giant packet, or, giant, quote unquote. And the way that that works is that that's sent off, and then when it's received on the other end, it's decapsulated, so it's opened up, and then each one of those headers tells the router where the thing needs to go. So it starts with when the user inputs the data that they want to send into the application. So you write an email or a message and you send the button or hit the send button. Application formats the data and starts sending it according to the application protocol used and using the layer below it, which is the transport layer. So it'll first start with the application layer, which is this thing right here. Whoops. This thing right here. So let's open this in an image. So it starts with the top layer, which is the application layer. You send your data. The data will go to the transport layer, and the transport layer will add its header saying that I'm going to send this using the UDP, the user datagram protocol. I'm going to send it using this protocol, and then here's the data, okay, in the UDP format. And then it's sent to the internet layer, which is the network layer. And then it has the IP addresses, meaning that it's coming from this source IP address and it's going to go to this destination address. And then here's the data, right? And then you have the final link address, which is going to take it from the frame itself, and it's going to add its header as well as the footer so that it can actually go to your physical router so it can leave your network, right? Because remember, it's going to start from your application, it's going to go down the line until it hits your router and leave your house, leave your building. And then from there, it'll land on the other side, and it will first be received by the link layer. Then it's going to be opened up by the IP address, and it's going to say, oh, it's supposed to go to this computer. And it's going to be opened up by this, and then it's going to finally decapsulate or open up the final encapsulated packet so that you can actually get the data that you wanted, which is the message, right? So the transport protocol segment or datagram. So the transport layer such as TCP adds the proper header information and creates the segment if it's TCP or datagram if it's UDP, and this segment is sent to the layer below it. The network packet, which is the network layer, and adds the IP header to the receive segment or datagram, and then it'll send that packet to the layer below it, which is the data link layer, and then the Ethernet or Wi-Fi receives the packet and then sends the proper header to create the frame. So if it's on the link layer, it's a frame. If it's in the network layer, it's a packet. And then if it's in the transport layer, it's either a segment or a datagram. And then finally, it ends up as the message or the funny cat GIF that you wanted to send to your girlfriend or something like that. So we start, again, we can look at it like this, right? We start with the application layer, then we send the application data and attach a TCP or a UDP header. So if it's a TCP, it's a segment. If it's UDP, it's a datagram. And then it's going to go back down to the IP layer or the network layer, which is going to take the application data, the TCP header, and then the IP header, and it's going to add that to it, which includes the source IP and the destination IP, so where it's coming from and where it's going. And then we have the Ethernet final layer, the physical layer, the link layer, which is going to take all of that information and then encapsulate it. So each process is basically getting more and more encapsulated. So imagine this is an envelope, then it's going to be placed inside another envelope, then it's going to be placed inside another envelope, and then it's going to be placed inside another envelope so that it can get sent out. That's what you can look at it. So this is what we can think about on the TryHackMe example that we have here. So on the search page, you enter your user search query. So I go up here, click on this, and I search for something in there. I'm so zoomed in right now that I can't see everything. I'm like, I think 250x or something. I'm really, really zoomed in right now. So it'll go from the search query, right? Then the browser, using this protocol, prepares the request and pushes it to the layer below it, which is the transport layer. Then that layer needs to establish a connection via the handshake between my browser and the TryHackMe web server. After that connection is made, it can send the request containing what I wanted to search for. And then each one of those segments created is sent to the layer, which is the internet layer. And then, so again, I'm putting it into the browser for my application. The browser is like, okay, I'm going to use a secure method to send this over. And then I'm going to establish a connection via the transport layer so we can actually send it to the IP, to the router that's inside of my house. And then the router is going to say, oh, okay, this is the IP address that it's coming from. And then it's going to go to the IP address of the TryHackMe server. And then the packet reaches that router, the laptop delivers it to the layer below, which is the actual data link layer, which is going to be that physical wire that's connecting my router to the pole outside of the building, okay? And then the router removes the link layer, header and trailer, inspects the IP destination, all that stuff, and then routes the packet to the proper link. And then when it lands on the other side, each router will actually repeat this process until it's finally gone to the TryHackMe server, which will unwrap the entire package and be like, oh, okay, this is what the guy wanted. Let me send it to him. And then the web server on that side will do the same exact thing and then send it to me. And then my wire receives it, sends it to my router. The router sends it to my computer, and then the computer unpacks it, and we get the data that we want. So on a Wi-Fi, within what will an IP packet be encapsulated? So on the Wi-Fi, it's going to be inside of a frame, okay? And then what do you call the UDP data unit that encapsulates the application data? That's the datagram. What do you call the data unit that encapsulates the data that's over TCP? That's called a segment. And that's all she wrote. So let's jump into Telnet and actually use this machine that I started about an hour ago. So let's get into it. All right, so what we are going to do is we're going to use the teletype network protocol, which is called Telnet. And it's used for remote terminal connection. And you can connect to a variety of ports. The ones that we're going to connect to is port 7, port 13, and port 80. Now, by default, port 7 is not accessible on any network because it's not secure. Neither is port 13. They're not secured ports, they're not secure protocols. So in most environments, other than this controlled environment, in most other environments, you're not even going to see these as open ports. The HTTP server, which is for web servers and web pages, will most likely be open. But what's going to happen is that it's going to be followed with an HTTPS port. So there's port 80, which is HTTP, and then HTTPS is port 443, which is the secure connection of HTTP, which is encrypted, right? But in this particular case, we're literally connecting to all of the insecure versions of these things. Before continuing, we need to make sure that echo and daytime servers are considered security risks, should not be run, which is the 7 and 13. However, we started them explicitly to demonstrate communication with the server, yada, yada, yada. So the way that you use telnet is just type telnet, the IP address, and then 7, meaning the port that you want to connect to. So in this case, this is what the echo service does, is that you just connect to it and then you type hi and it says hi. You say, how are you? It says, how are you? Bye, bye. So it literally just says everything that you say and it just prints it back to you. And if you want to close, you would do controlled and then the closing square bracket and then it close that connection. And if you want to, it'll close that connection, but then it'll pop you back into the telnet service. So if you want to get out of telnet, you type quit and then you close that out. And then pretty much the same thing that we're going to do with the third 13, which is the current date and time. That's all it's going to do. It's going to just spit me the current date and time, and it's going to close it immediately. And then finally, we have port 80, and I'm not going to give you that yet because I want you to see how it works. So let's just run these things real quick. So this is the IP address. So let me just copy that to make life easy here. And we're just going to zoom in on this guy right here. So we're going to do telnet. Now we're going to right click, paste the IP address, and then we're going to close on port 7. And it says, hey, you are officially connected to this port. So if I say hi, it's going to say hi. If I say bye, it's going to say bye. So I just do control square bracket and it closes, and then I got to do quit and it'll close that for me. Then we clear that out, and then we're going to run this one more time, except now we're going to connect to port 13, press enter, and immediately gets me the date right here. Which is December 26th, because this server for TryHackMe, all of their servers is actually, I think it's in the UK. It's basically somewhere that's a day ahead of me. So they're living in the future right now. And then so I get the 26th because today's Christmas Day. It's the 25th for me. And so that's done. And then boom, it just spits me out. It just closes me out automatically. And then finally, we have the one that will be done on port 80, which is going to be our web server. Now, I am actually connected to the web server, but there's a few things that I have to do to be able to finalize that connection. And the way that we do that is we need to first say that we want to make a GET request. Let me actually, this is a better way to do this. First, we need to say GET in all capitals, space, / space, HTTP / 1.1. That's the first thing you got to do. And then you press enter. And then you have to give it the host that you want to connect to, which is telnet.thm. Then you press enter twice, and then you can actually access the server, and it'll respond to you and say, your success or your connection was established successfully, which is done with the HTTP 200 response. And then you basically, if you can access any data, you'll be able to access it. If not, it'll just automatically close you out. But there are some data that we do need to be able to answer the rest of the questions on this lab. So I'm going to actually type in those things that I need to type in. So right here, it kicked me out because I didn't do what I wanted to do, or what I should have done, I guess. So let's clear this out, and then let's do this one more time. So not 8, we want 80. Close that out again. Goodness gracious. Boom, boom. 80, enter. Very good. So we're going to make a GET request, and it's going to go to the HTTP / 1.1. Press enter, and it's all good. So host is going to be the, what was it? It was telnet.thm. There we go. Telnet.thm. Press enter, and then press enter one more time. And now you have all the data that you want. And so the questions that we have at the end is, what type of server are you connected to, which is the light TPD 1.4.63, and then what is the flag, which is THM telnet master. And so if we go at the bottom right here, it is what is the connection, or what is the server type, and there it is. And what is the flag? There's the flag. And just like that, we have officially wrapped this particular room. So let's go through the conclusions and the final notes, and then I will give you a couple of other stuff, and then we're gonna get out of here. It's so crazy. When I started this recording, it was light outside, and just like that, it got dark. So we're officially wrapped. This was the networking concept, so the very, very basic introduction to networking, and we did run some couple of labs here. So that was it, and that's basically all you need. The very next video is going to be episode 15, I want to say, and then that's the one that's going to be on networking essentials, and then we're just going to go deeper and deeper into networking and ultimately even get to use some cool networking tools. So that is it for this one. If you did find this video useful and you would like to get more future videos on the CySec101 pathway, as well as basically everything else that we talk about on this channel, for example, the Security Plus certification course that's going to come out in a couple of weeks, I do encourage you to like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out. And if you have any questions, drop a comment and let me know what your question is. I am very responsive in the comment section. And then, of course, we're going to talk about anything that you would need in a video. So if you have a really big question that requires a long response, I'll create a video in response to your comment. The CySec101 training series is a response to Darnell Knight's comment. And Darnell was literally the guy that was like, hey, could you do something introductory? I was like, you know what? That's actually a really, really good idea. And so we started this entire playlist that does CySec 101 for people like Darnell. So if you are grateful for this, then you should just say thanks, Darnell, or something like that in the comments. But if you have any questions, also let me know that you have the question and I'll respond to your questions. And then, yeah, just make sure to like, subscribe, turn on the notification bell, drop a comment so that I hear from you. And of course, you get notified the next time that a video comes out. And then there's the Hackaholics Anonymous membership community, if you have not checked that out yet, which is the premier membership community for cybersecurity professionals and hackers. There are 4 tiers of benefits. Starts from the cyber supporter that they gets their own early access to content. They get their own Discord servers that get access to me directly, as well as all of our advanced members. And then it goes up to the advanced memberships, which is the Cyber Agent, Cyber Guardian, Cyber Master. They get Python automations every single month. They get live streams that happens every single month. They get exclusive content. They get exclusive downloads. For example, all of the notes and practice examinations and practice questions for the Security Plus that's going to come up. So if you want to join Hackaholics Anonymous, which I really hope you do, you can join through the link in the description below. You can go to our homepage and click the join button, or you can go to youtube.com/@HankHacksHackers/join, and you will get direct access to the Hackaholics Anonymous community. I really hope I do see you in the Discord chats. If I don't see you in the Discord chats, then at least I hope I see you in the comment section. And that's it for today. It's your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker / protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease. Merry Christmas. Happy New Year. I hope you have an amazing 2025. We're coming on our 1-year anniversary for this channel in January 4th of 2025. So thank you for being here. Thank you for being a member. Thank you for being a subscriber. Thanks for being a watcher. And thanks for being a part of this community. I hope you got a lot out of it. Love, peace, and chicken grease. Peace. Later. In episode 14 of the CySec 101 training series, we are going to be talking about networking essentials. And this is the continuation of the networking module that we started in episode 13. And it's part of the Cybersecurity 101 pathway of TryHackMe. And it's a really big module, the networking module. We have, I think, maybe 7 or 8 rooms that we're going to be covering. So this is just basic continuation of what we're going to be talking about with networking essentials. We did like the networking introduction in the last one, networking components, I believe. And then we're just going to be going through essentials, and then we'll start going through networking security and protocols and so on and so forth. So that is it. And real quick word from our sponsor, and then from there we'll jump into the introduction. This video is sponsored by Hackaholics Anonymous, the premier membership community for security professionals and hackers. And you can get access to 4 levels of perks and benefits, starting with the cyber supporter that gets their own Discord server and access to me directly, as well as all of our advanced members. And then the advanced level members like the Cyber Agent and the Cyber Guardians that get Python automations and exclusive content, exclusive downloads, live streams, their own Discord servers, and a variety of other benefits that are honestly really amazing. And I think they're an excellent bang for the buck, so to speak. To join Hackaholics Anonymous, you can click the link in the description below. You can go to our YouTube channel and click join, or you can essentially go to youtube.com/@hankhackshackers/join, and you'll be taken directly to the join page. Hopefully I will see you in the Hackaholics Anonymous community and in the Discord chats. Now that's out of the way, let's actually get into the introduction of the networking essentials. Alright, so have you ever wondered how your computer can dynamically configure its network settings when you turn it on or connect it to a new network? Have you ever wanted to know how many devices and countries your packets pass through before reaching their destination? Are you curious how all your home devices can access the internet even though your internet service provider gives you a single IP address? These are all nerd questions, right? So if you want to know the answers to these, this is what we're going through today. Last video we talked about networking concepts. Today we're talking about networking essentials, and then we're going to go through networking core protocols and secure protocols in the next couple of videos. And today we're going to go over the ISO OSI model and the layers of it, the TCP IP model and the layers of it, as well as the Ethernet IP and TCP protocols. So we touched on them in the last video, but today we're going to take a deeper dive into those concepts. We are going to learn about the dynamic host configuration protocol. We're going to learn about address resolution protocol, the network address translation, and of course, internet control message protocol, so the ping and traceroute tools, as well as just what those they do. So that is essentially the gist of today's video. And without further ado, let's actually talk about the Dynamic Host Configuration Protocol, DHCP. All right, if you can imagine connecting to a new Wi-Fi, so your laptop connected to the Wi-Fi of your favorite coffee shop, and automatically configured the network so you could now work on a new TryHackMe room while you're in the coffee shop. You didn't type an IP address, but your device is still all set up. So how does that actually happen? Whenever you want to access a network, at the very least, there are a few things that need to be configured. Number one, the IP address along with the subnet mask. And this is the IP address of your computer, right? Your router or the gateway, as well as the DNS server. All of these things need to be configured in order for you to be able to access a network, a Wi-Fi network, for example. Whenever you connect the device to a network, those things must be set according to the new network, right? So, for example, in this case, the coffee shop Wi-Fi, right? Configuring these settings is a good option, especially for servers. Servers aren't expected to switch networks, so you can essentially set them up and you don't carry the domain controller and connect it to the coffee shop Wi-Fi, right? You don't carry this big box with you that is the size of a room, basically. So other devices, however, need to connect to the servers and expect to find it at a specific IP address, meaning that IP address should not be dynamic. It should not be changing. It should be static for the most part. So when you have an automatic way to configure the connected devices, you have a lot of different advantages that come to play. Number one, it would save you from the time and energy to manually configure the network. And it's very important, especially for mobile devices like a laptop. Number two, it saves the address conflicts. So you getting somebody else's IP address, for example. So if two devices are configured with the same IP address, there's a problem that takes place. So you don't want to do that. The IP address conflict would prevent the involved hosts, the involved computers basically, from using the network resources. And this applies to local resources as well as the internet. So the solution is inside of our dynamic host configuration protocol. The DHCP is an application level protocol that relies on the UDP, the user datagram protocol, and the server listens on UDP port 67 and the client sends from UDP port 68. The smartphone and laptop are configured to use DHCP by default because it's dynamic. They move around, so they need to be dynamic, right? So the process is, you discover whatever the network is, you make an offering, and then the request, and then the acknowledgement, right? So that's kind of the whole idea here. So DHCP discover is by the client. The client broadcasts a DHCP discover message seeking the local DHCP server if there is one. Then the server responds with the DHCP offer message with an IP address that would be available for the client to use. So the DHCP server says these are the IP addresses that I have available, and then the client responds with, okay, well, can I have whatever one that is available, just give it to me. I'll take that request. You know, they make the request, the client, meaning your laptop, basically. Your laptop makes the request, and then the server responds with a DHCP PAC message to confirm that the offered IP address has now actually been assigned to that client. So, you know, you send the discover, the server responds with an offer, you accept the offer with your request, and then there's a DHCP acknowledgement saying, okay, so here's your IP address. Now, what happens is that this is a leased IP address. I don't know if we're going to talk about it, but this is called a lease, meaning it's not a permanent assignment. It will change the next time that you connect to that Wi-Fi router, for example, right? So the following packet capture shows the 4 steps explained above. In this example, we actually end up with this particular private IP address. If you remember from the last video that we did, if it starts with a 10, a 17, or a 192, or excuse me, 10, 172, and 192, that means that they are private. So if we run tshark, it'll search for, searching through the pcap file from the DHCP, we can see that these are the transactions that took place, right? This was the conversation. So there was a DHCP discover that was sent from our machine. Then there was a DHCP offer that came from the actual server, and then we made the request, and then finally we ended up with the acknowledgement, and this is what we actually got as our IP address that was assigned to us, right? In that exchange, we can notice the following. So the client starts without any IP network configuration. It only has a MAC address, and the first and third packets, the DHCP discover and request, the client searching for the server still has no IP network configuration and has not yet used the server's offered IP address. Therefore, it sends the packets from the 000 to the broadcast IP of 255 times 4, basically. As for the link layer, in the first and third packets, the client sends to the broadcast MAC address, which is just a series of Fs because they are not shown in the actual image above, in the output above. The DHCP server offers an available IP address along with the network configuration in the DHCP offer. It uses the client's destination MAC address and then the proposed IP address in this example system. So the link layer, meaning the physical, the MAC address layer, the first and third packets, we send it to the MAC address, which is not available in the display that we have over here, but it basically sends it to the MAC address because there is no actual IP address, right? And then once it is sent to the MAC address, the server offers an available IP address along with the configuration that is available in its offer, and then it uses the client's destination MAC address so that it will essentially assign that instead of this blank one right here, or this like generic one. At the end of it, the device would have received all the configurations that it needs to access the network or even the internet. In particular, we expect the DHCP server has provided us with these things: the leased IP address to access network resources, gateway to route your packets outside the local network, and a DNS server to resolve domain names, and we'll talk about that in a little bit. So when we say leased IP address, just keep that in mind. That's part of the dynamic portion of this, meaning that it's not permanent. You don't get this permanent assignment of this IP address to you forever, right? Because you're on a coffee shop, you're on a public Wi-Fi. So, you know, most likely you may not visit that coffee. Maybe you do, right? But most people don't revisit that Wi-Fi coffee shop or coffee shop Wi-Fi. And so the whole idea is that, you know, you use it for the length of time that you're there, and then when you leave, somebody else gets assigned that thing. So it's a lease, it's not a permanent assignment. So how many steps does DHCP use to provide network configuration? And the answer to that is 4. What is the destination IP address that a client uses when it sends a DHCP discover packet? And the destination IP address is the 255.255.255.255. And there we go. What is the source IP address a client uses when trying to get the IP network configuration? I think that was the 000 one, right? So it would, 000. Okay, so that is our IP address. So we're just going to do 000 and one more 0. There we go. All right, cool. Let's talk about the address resolution protocol, the ARP. In the last room, the networking concepts room, we talked about 2 hosts communicating over a network. And when they do that, an IP packet is encapsulated with the data link frame, and it travels over layer 2, the data link layer. the two common data link layers that we use are the Ethernet, which is on IEEE 802.3, and Wi-Fi, which is on 802.11. Whenever one host needs to communicate with another one on the same Ethernet or Wi-Fi, it has to send the IP packet with a data link layer frame. And then although it knows the IP address of the target, it needs to look up the target's MAC address so the proper data link layer can be created. So it needs both of those things, even if it's traveling over a network. It needs both the MAC layer as well as the IP address. So a MAC address is the 48-bit number typically represented in this kind of a format. It's hexadecimal, and this is another one. They're on the author's network, for example. So the devices on the same Ethernet network do not need to know each other's MAC address all the time. They only need to know each other's MAC address while communicating. Everything resolves around IP addresses. Considering this scenario, you connect via your device to a network, and if the network has a DHCP server, your device is automatically configured to use a specific router or a gateway, and then the DNS servers. Consequently, your device knows the IP address of the DNS server to resolve any domain name. Moreover, it knows the IP address of the router when it needs to send packets over the internet. In all of this scenario, no MAC addresses are revealed because you are no longer worried about communicating with somebody in your same network in your room or in your office or something like that. Now you're talking about the internet, right? So the World Wide Web. So two devices on the same Ethernet cannot communicate knowing each other's they cannot communicate without knowing each other's MAC address because, again, they are on the same Ethernet. They're in the same network. So as a reminder, in the screenshot, we see an IP packet with an Ethernet frame. The Ethernet frame contains the destination MAC address, the source MAC address, and then the type. In this particular case, it's an IPv4. Now, all of this is done in hexadecimal, so you can't really see it in this particular at this bottom portion, but it does show it to us on our Ethernet portion when we're looking at the Wireshark packet. So it has essentially for every level of the TCP IP, it actually has a section dedicated to it. And in the Ethernet portion, the link portion, we see the destination MAC address, the source MAC address, and then the fact that we're sending an IPv4 packet. So, Address Resolution Protocol, ARP, makes it possible to find the MAC address of another device on the Ethernet. In this example, a host with the IP address ending in 89 wants to communicate with another one ending in 1. It sends an ARP request asking the host with the IP address of 1 to respond. So 89 is asking 1 to respond. And the ARP request is sent from the MAC address of the requester, meaning this guy's MAC address. And it's listed as such, right? So it's not the actual MAC address. And then the ARP reply arrived shortly afterwards with the actual IP address responded with its MAC address. From this point, the two hosts can actually communicate. So the first time when it sends its request, it's sending it not knowing what the MAC address is. And then the person that you're sending it to or the device that you're sending it to will actually respond with its MAC address, and now you know what its MAC address is, and then you store it inside of your database, so next time you know exactly how to communicate, or for the rest of this transaction you know how to communicate. But the first time that you send it out, you don't know what the actual MAC address is. You're kind of making a request to try to connect to them, but you do know what their IP address is. So it's like, hey, who has this specific IP address? That's the request that we're sending out. And then the computer that actually has that IP address is going to respond, and then its MAC address is included in the response. And it's like, oh, that's where we're sitting. Cool. Okay, good to know, right? So if we use TCP dump, the package will be displayed differently. It uses the term ARP request and ARP reply. And so this is what that looks like. So we have the same, it's kind of similar, but it's saying this is a request. So who has this? And then this is the reply. This is at this MAC address. And that's basically the communication on TCP dump. This communication is reading the ARP PCAP file using TShark. This one is actually looking at the traffic via TCP dump. So the request or reply is not encapsulated with a UDP or even IP packet. It is encapsulated directly within an Ethernet frame. And this is what it looks like on Wireshark. So this is, we saw that previously in the last screenshot that we had, we were looking at the actual Ethernet portion. Now we're looking at the actual ARP portion where it's showing us the sender MAC and then IP address as well as the target MAC and IP address. So ARP is considered layer 2 because it deals with MAC addresses. Others would argue that it's a part of layer 3 because it supports IP addresses as well. What's essential to know is that ARP allows the translation from layer 3 to layer 2. So it allows both of those to take place. Let people argue about whether or not it's layer 2 or layer 3. For your intensive purposes, you need to know that address resolution protocol is resolving the MAC address to the IP address and vice versa, so that the machines actually know how to communicate with each other either on the same network or across the internet. So what is the destination MAC address used in an ARP request? And that's the very basic one that we have, which is this thing right here. It's like the generic one. So this is the destination MAC address that we use. And then in the example above, what is the MAC address of 66.1? So the MAC address of 66.1, if we look at it here, so it says who has 66.1, and in this case, this is the MAC address at 66.1. And then we're going to go over here and paste that over here. Very good. All right, cool. Let's move on to ICMP, Internet Control Message Protocol. The Internet Control Message Protocol is mainly used for network diagnostics and error reporting. So we use ping and traceroute as the commands to essentially accomplish that. It's very commonly used. So ping and traceroute is very commonly used. Ping uses ICMP to test connectivity to a target system and then measures the round trip time. In other words, it can actually be used to learn whether or not the target is alive and then how quickly it actually responds. Traceroute is the command that is run on Linux and Unix, and then it's traceRT on Windows, and it uses ICMP to discover the route from your host to the target. If you remember from the last video, we talked about the number of routers that a packet will go through to get from us to the destination that we wanted to get to. And that number of hops that it takes to go from one router to another, that's essentially what traceroute traces for you, right? It tracks it back for you. So if you've never actually played ping, or I guess ping pong table tennis, you can actually kind of understand what it looks like on the computer. But I mean, when you kind of think about ping pong or table tennis, it's just a ping pong, like you're just going back and forth, right? So the ping command will send a request, the echo request, and then the screenshot will actually show it right here. So we have the ICMP, Internet Control Message Protocol. That is the section for this. And it says echo ping request, right? That's what we did. And then we actually got a response that's going to be inside of the next frame that you would look at. The computer on the receiving end responds with the reply, which is right here. So the request frame is frame number 1. We are now in frame number 2, and frame number 2 is the reply of frame number 1, or the reply to frame number 1. A lot of things can prevent you from getting a reply. In addition to the possibility of a target actually being offline or shut down, a firewall can block the necessary packets for ping to work. So if we use C4, we count the number of packets. Otherwise, it would just run indefinitely. So when you use C4, it just runs it 4 times, and then it'll stop after the 4th time. And then it'll say 4 packets transmitted, 4 packets received. So in this particular case, it was actually up, it was running, everything is all good. The output shows there was no packet loss. Moreover, it calculates the minimum, average, and maximum standard deviation of the round trip time, which is what we have over here. So this is it, minimum, maximum, and then we have the average, and the same thing over here. So ICMP, where do we have the minimum, maximum, average? I think it's actually, this is it right here. Yeah. So minimum, maximum, average, and then the standard deviation. So MDEV, which is this one right here. The median deviation is what that would stand for. Traceroute basically routes or traces the route. So how can we make every router between our system and a target reveal itself? We do that with traceroute. And it's done with the field that's called time to live. That indicates the maximum number of routers a packet can travel through before it is dropped. The router decrements the packet's time to live before it sends it across. So by 1, meaning it'll decrement it by 1 before it sends it across. When the TTL reaches 0, the router drops the packet and then sends the ICMP time exceeded message. In this context, time is measured in the number of routers, not seconds. So the terminal output shows the result of running traceroute to try to reach example.com. Some routers don't respond. In other words, they drop the packet without sending any ICMP messages. Routers that belong to your ISP might reveal their private IP address. Moreover, some routers that respond and show their public IP address, and this would let us look up their domain name and discover their geographic location. Finally, there's always a possibility that ICMP time exceeded gets blocked and never reaches us. So we can see that this is the very first hop. This is the first packet that was sent out, and it's going from the gateway, right? And then private IP, public IP, private IP, these things didn't actually respond. And in a private IP, this seems to be, what is it? I feel like this is like the locations that are associated with those individual routers. It seems like they're in Marseille in France. And then you get some more. These are the other ones as well that go on the way. And finally, you land at the destination that you wanted to land at. So the very last hop, if it's not dropped, and if it makes it all the way to the end, it will actually be the destination that you want to look you want to connect to, right? So you can always take something like this. So let's see if this is a free room. This is actually a subscriber only room, but you can basically go to Gemini AI or Meta AI or GPT or any of the major AIs and talk to them and basically say, you know, show me a sample traceroute output and then explain to me what it looks like. Or you can just copy and paste something like this and go and have it be explained to you. But for the most part, it's just tracing the route that a packet takes to go from your gateway, from the location that is starting, to the place where you want it to end, which is example.com. So if you see that this 215.14 at the end, that's where it actually ends up at. And if it doesn't make it there, then the packet didn't survive, or it was dropped along the way, and it's mainly because there's connectivity issues. And then you can kind of see at what point it was dropped. What was the last step that it took before it was dropped? So using the images above, how many bytes were sent in the echo ping request? So if we go and look at the images here, it says how many bytes were sent. And so let's see what we got over here. 64. What am I saying? It's literally right here. I don't need to go any further than that. So 64 bytes were sent. And that's typically what it looks like with every single one. The echo ping request. We sent in the echo ping request. Oh, so maybe we're looking at the wrong one. So over here, inside of the echo ping request, how many bytes were sent? And so if we go and look at the data here, we have 40 bytes. There you go. 40 bytes were sent. That's the number that they're looking for. I was looking at the wrong section there. So there we go, 40. And which IP header field does the traceroute command require to become 0? So which IP header field does the traceroute command require to become 0? My bad, it's TTL. TTL needs to reach 0. That's completely my bad. See, you learn things, right? You go through these things and you learn things, and I'm learning with you because I haven't gone through this room before, and I am not a master of networking, so I'll admit that straight up, obviously, if you haven't been able to tell. Okay, cool. So now let's talk about routing. So considering this diagram below right here, it only has 3 networks. However, how can the internet figure out how to deliver a packet from network 1 to network 2 or network 3? That is an overly simplified diagram, obviously. We need some algorithm to figure out how to connect network 1 to 2 and to 3 and vice versa. So we have network 1 over here, we have network 2 and we have network 3. So considering this, how does the internet figure out what it is that you are trying to do and where you're trying to go, right? So let's consider a more detailed diagram. The internet would be millions of routers and billions of devices, and the network below is a tiny subset of the internet. The mobile user can reach the web server. However, for this to happen, each router across the path needs to send the packets via the appropriate link. Obviously, there's more than one path. Route, meaning one path being route, connecting the mobile user and the web server. We need a routing algorithm for the router to figure out which link to use. So we have the mobile user trying to get to the web server, right? So this is actually the diagram that we looked at in the last video. So which route is it going to take to end up here? At the very least, the fastest one would probably be boom, 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 and then right here. or sometimes it may be boom, 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 boom here, right? So it depends on what is available. It's one of the big pieces. But the whole point is that there needs to be an algorithm that will figure out which one to use. So this is where it kind of gets a little bit technical. So the routing algorithms are beyond the scope of this room. However, we will briefly discuss a few routing protocols so that you can become familiar with their names. So OSPF is the open shortest path first. It's a routing protocol that allows routers to share information about the network topology and calculate the most efficient paths for data transmission. It does this by having routers exchange updates about the state of their connected links and networks. This way, each router has a complete map of the network and can determine the best routes to reach any destination. So OSPF, the shortest path first, and it's done by finding the entire map of the network essentially. And once you have those updates constantly being shared, then the router has a complete map and knows exactly the best route to reach the destination. The next one is EIGRP, so Enhanced Interior Gateway Routing Protocol. EIGRP is a Cisco proprietary routing protocol that combines aspects of different routing algorithms. It allows routers to share information about the networks they can reach and the cost, like the bandwidth or delay association with those routers. Routers then use this information to choose the most efficient path for data transmission. So EIGRP is a Cisco proprietary routing protocol. It combines aspects of different routing algorithms and allows routers to share information about the networks they can reach and the cost, for example, how long it will take and how much resources it will take associated with those routes. And then the routers use this information to choose the most efficient paths for the transmission. BGP is the Border Gateway Protocol. It's the primary routing protocol used on the internet. It allows different networks like those of the ISPs to exchange routing information and establish paths for data to travel between these networks. BGP helps ensure data can be routed efficiently across the internet, even when traversing multiple networks. So this is the primary routing protocol on the internet, and ISPs, internet service like AT&T and Spectrum, for example, they exchange routing information to establish paths to travel between these networks, and they help ensure data can be routed efficiently across the internet when traversing multiple networks. RIP does not mean rest in peace. It's the Routing Information Protocol, and it's a simple routing protocol often used in small networks. Routers running RIP share information about the networks they can reach and the number of hops that it's required to get there. As a result, each router builds a routing table based on this information, choosing the routes within the fewest hops, to reach each destination. So this is for the smaller networks. BGP is for the internet as a whole. We have EIGRP, which is a Cisco proprietary routing protocol that combines aspects of different routing protocols. And then you have the open shortest path first, which is allowing routers to share information so that you can get the most efficient path to get across. So which routing protocol discussed in this task is a Cisco proprietary protocol, and it's this one, EIGRP, the Enhanced Interior Gateway Routing Protocol. So here we go. Drop that in there, and let's move on to the NAT, the Network Address Translator. So in networking concepts, the last room, we calculated that the IPv4, the version of IP addresses that you see that is the, the 10 dot, whatever dot, like the basic one that pops into your head when you think of an IP address, it can support a maximum of 4 billion devices. Because there are so many other devices, there are way more than 4 billion devices, computers, smartphones, whatever. It was clear that IPv4 would be depleted quickly. So one solution to address this was the network address translation. And the idea behind NAT is to use one public IP address to provide the internet access to many private IP addresses. And in other words, if you're connecting a company with 20 computers, you can provide internet access to all 20 computers by using a single public IP address instead of 20 public IP addresses. So technically speaking, the number of IP addresses is always expressed as a power of 2. To be technically accurate, with NAT, you reserve 2 public IP addresses instead of 32. Consequently, you would have saved 30 public IP addresses. So the whole idea here is to what? Use one public IP address to provide the internet access to many private IP addresses. Unlike routing, which is a natural way to route packets from destination to host, or from destination host to the from support. What am I saying? From the source host to the destination host. I literally lost my mind. Unlike routing, which is the natural way to route packets to the destination host from the source host, right? Routers can support NAT, must find a way to track ongoing connections. Consequently, NAT supporting routers maintain a table translating network addresses between internal and external networks. Generally, the internal network would use a private IP address range, while the external network would use a public IP address range. So what you can expect is that, number one, privacy-wise, the outside world isn't going to see your private IP address, but then functionality-wise, because there is so many more that needs to be accessed in a public network out in the public internet, you can use one private IP address to get a hold of many different public IP addresses. Multiple devices can access the internet via a router that supports NAT. The router maintains a table that maps the internal IP address and port number with its external IP address and port number. For instance, the laptop might establish a connection with some web server. From the laptop's perspective, the connection is initiated from its private IP, which is this thing, and the TCP port number, which is 15401. However, the web server will see the same connection as being established from this IP, which is a public IP, and a TCP port 19273. So the router does this translation like without you even thinking about it. It's doing it in a fraction of a second, right? And so this is the whole idea here, that the laptop right here, or the cell phone, either one of these things, if it wants to access the internet, it goes through the router, and the router translates this private IP to a public IP so that the internet can see it. So in the diagram above, what is the public IP that the phone will appear to use when accessing the internet? So the one that the phone is going to use is 0137. So 0137 will end up using 212.3.4.5 is what it's going to end up using. So 212.3.4.5. And assuming that the router has infinite processing power, approximately speaking, how many thousand simultaneous TCP connections can it maintain? And we're going to say 65 because there are 65,000 ports. So assuming that it has infinite processing power, we can say it's approximately 65,000. So basically one for every port. And that was it for the network address translator. And really, that was it for the networking essentials that we were talking about. It was kind of a quick little run through here, mostly a lecture. And then we have this one little exercise that's left for us. So I'm going to zoom out real quick, and then we're going to run through the exercise, and then we're going to get our flag, and then we are going to wrap it up. So let's do it. This room introduced us to a variety of protocols. We have covered these things. Although we use the internet daily without coming to access most of the acronyms, these protocols are the foundation for a functional network. So please follow the instructions to get the flag. That's basically what we're doing here. So it says, which protocol do we need? As we have learned in this room, different protocols and techniques are used to solve various problems. In this exercise, we will go through this. Okay, so let's actually start it. So here we go. I want to find out the DNS server and the default route on a network automatically. Which protocol should I use? So we want to find out the DNS server and the default route. Which one do we use? Is it ICMP? Is it network address translator, ARP, or DHCP? And the default route on a network automatically, I'm going to go with DHCP. Very good. Cool. I want to find another host's hardware address, which is the MAC address on the network. Which protocol lets me do this? And that would be the address resolution protocol. Very good. I want to confirm that I can exchange packets with another host as if I am playing ping pong. Which protocol supports this? That would be ICMP. And then we need to give 25 devices internet access. However, we only have one public address. That would be the network address translator. And just like that, we have completed the exercise. Easy money. Let's go. So ready. I'm so happy that this is working. Okay, great. So, and here we go. We're going to click on that, and we're going to get notified of the success, and we are officially done. Congratulations, ladies and gentlemen. Hopefully you made it through this whole thing with me as well. So if you found value from this video, or if you want to get the next series of videos that are going to come out from the CySec101 training series, I do encourage you to like, subscribe, turn on the notification bell, drop a comment, all that good stuff, because there is going to be regular videos coming out in CySec101. There's also a new training series for Security Plus that's going to be coming out in the next couple of weeks. So if you want to get, jump start on that, I would highly recommend that as well. And you can even get early access to that by becoming, again, one of our subscribers. And then you can also join Hackaholics Anonymous, which brings me to the Hackaholics Anonymous membership community, which is the premier YouTube community for security professionals and ethical hackers. And you will get access to 4 tiers of memberships. So the cyber supporter, who gets early access to content, they get their own Discord servers, as well as access to me and all of our advanced members. And then we have the cyber agents and the guardians and the masters, who get Python automations every single month. They get live streams with me. They get their own Discord servers. They get exclusive content, exclusive downloads. For example, all of the notes that will come from Security Plus upcoming, as well as the practice questions and the practice examinations, so on and so forth. All of that is reserved for all of our advanced members of Hackaholics Anonymous. So to join Hackaholics Anonymous, you can click the link in the description below, or you can go to our homepage on the channel and click join, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. I really do hope to see you inside of the Discord servers. At the very least, I hope to see you inside of the comment section of the channel. And that's pretty much it for today. This is your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker/protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease. I think by the time that this comes out, Christmas will have come and gone. So I think it's probably going to be the day after Christmas, or maybe the weekend of something like that. But it'll definitely happen after Christmas, I think. So hopefully you got a lot of value out of this channel. We are literally right around the corner with the new year, and we're about to hit our 1-year anniversary with this channel. So it means a lot to me that you're here. It means a lot to me that you're watching, and I really hope that you're getting a lot of value out of this channel. I do look forward to seeing you in future videos, and in the comment section, again, love, peace, and chicken grease. If no one else loves you, I love you. Later. In episode 16 of our CySec101 training series, we're going to go through networking core protocols, and this is a part of the Cybersecurity 101 pathway of TryHackMe, and we're just continuing down with our networking module here. We've done 2 rooms, I believe. So we did networking concepts, and we did networking main components, or what was it called? Something along those lines, where it was, we did the general networking concepts, and then we did the networking essentials. There we go. So we did networking concepts, we did networking essentials, and then today we're going through the core protocols in networking. And this episode has been brought to you by the Hackaholics Anonymous membership community, which is the premier YouTube community for security professionals and hackers. And you get access to 4 tiers of benefits. It starts with the cyber supporter that gets their own Discord server, as well as direct access to me and all of our advanced members, early access to content, so on and so forth. And then we have the advanced memberships, the cyber agents, guardians, and the masters, where they get access to Python automations every single month. They get access to live streams with me, exclusive content, exclusive downloads like the documents and the notes and the practice examinations and questions for the Security Plus that is coming up. So if you wanted to join Hackaholics Anonymous, you would access the link in the description below, or you can go to our homepage on the channel and click join, or you can simply go to youtube.com/@HankHacksHackers/join, and you'd be able to go to our join page for Hackaholics Anonymous. Now, without further ado, let us jump into the introduction for networking core protocols. All right, this is the 3rd room in the series of 4 rooms about computer networking. We've already done concepts and essentials, and we are going through core protocols today. And then there's going to be the secure protocols. That'll be the next thing that's going to come up. The prerequisites for this video and for this room is to just understand the various layers of the ISO OSI model, as well as the TCP IP model. I think we'll probably touch on it very briefly, but if we don't, it would be very beneficial for you to know what those things are, and you can very easily just Google ISO OSI model, and then even the TCP IP model, and then just go to Google Images, and you'll get a really nice cheat sheet, from 100,000 different locations where it would just break these things down for you in a variety of details. So we have Ethernet, IP, and TCP protocols, which are the big things that we're going to be talking about since we're going to be talking about the core protocols in networking today. So if you have not gone through the basic networking concepts, this is the recommended approach for you to take. You should at the very least understand what the TCP IP model looks like and what the ISO OSI models look like so that the rest of this stuff will make sense to you. We're also going to be running some basic commands through the virtual machine that we have for this room, as well as the attack box. And we're going to be learning about these protocols in particular, which is the Whois protocol, the domain name system, HTTP and FTP, SMTP, POP3, and IMAP. I've already started the machines, and the attack box is all running as well. So everything's all good, ready for us to go. So we are about to jump into the very first one, which is DNS. All right, chances are that you are like me in the sense that you are not Rain Man and you don't remember numbers extremely well. Meaning, maybe you do remember numbers, right? So let me rephrase that. I'm pretty good with numbers. I'm decent with numbers, but I don't remember the IP address for YouTube or the IP address for Google or the IP address for Gmail or the IP address for Facebook. I don't remember these addresses. And if we had to remember the addresses of the favorite websites that we go to all the time, especially considering the fact that their IP addresses are actually dynamic, they're rotating in and out. So they don't even keep the same IP addresses for security purposes. So if we had to remember all of those IP addresses, it's probably very likely that we would go to like some kind of IP address book, so to speak, where you have a contacts list and you reference those IP, because we just won't remember all of these numbers. There are billions of domain names online, and it's just impossible to remember all of them, again, unless like you are a whiz with numbers. So the DNS, the domain name system, is where that becomes a little bit more convenient for the layman, for the average person like me, right? I don't know that the IP address for Google is whatever it is, but I do know google.com and I do know facebook.com and I do know Gmail and you know, fill in the blank for your favorite domain. So it's like I know these locations by name, but I don't know their addresses. And that is where the domain name system really just kind of flexes its power. It's responsible for properly mapping a domain name to an IP address. That's what the DNS protocol and the DNS system is really all about. It operates at the application layer, which is layer 7 of the ISO OSI model, and it is also, I guess, layer 1 or layer 4 of the TCP IP model. I don't know, because they flipped it upside. It's confusing. You know, all I know is that ISO OSI has 7 layers and TCP IP has 4 layers, and some of the layers from the ISO model have been crammed into one layer. For example, we have the application, the presentation, and the session layers from the ISO model that has been all crammed into the application layer of the TCP IP model. That's basically all I know. and of course, I know the various layers. It's just that the order of them is always confusing. I have a little bit of dyslexia, but whatever, it's all good. So DNS traffic uses the UDP port 53 by default and TCP port 53 as a default fallback. There are many types of DNS records. However, in this task, we are going to be focusing on these specific records. Now, if you've ever set up a website, then you should be familiar with these things. If you've ever set up, if you've ever bought a domain name and set up hosting, these things should actually be very familiar too, because for each domain name, there needs to be an A record, a quadruple A record, a CNAME record, and an MX record. So the A record, which is the address record, maps the host name to one or more IPv4 addresses. For example, example.com will go to this IP address. The quad A record is similar to the A record, but it's for IPv6. So remember that it's quad A, so quadruple A. And AA and AAA would refer to battery sizes. So furthermore, AAA refers to authentication, authorization, and accounting. Neither of them fall under DNS. So this is just extra information to confuse you a little bit. What's important is to understand that quad A, quadruple A, is the record for IP address IPv6 addresses, and then the A record, the address record, is the IPv4 addresses. And then you have the CNAME record, which is the canonical name, and it maps a domain name to another domain name. So for example, example.com can be mapped to example.com without the wwws right here. So www.example.com can be mapped to example.com without the W's, or even example.org, right? So it's the canonical name, which basically maps the domain name to another domain name or other versions of it. So just in case somebody doesn't put the www and they just do example.com, they'll still be taken to the website. And if they do example.org, if you've purchased example.org, then you can also just redirect it so it goes to your main website, your main domain name. Then there's the MX record, which is the mail exchange record that specifies the mail server responsible for handling emails on a domain name. These 4 records are important to understand because they are pretty much the base requirements for setting up any domain name. Now, when you type example.com in the browser tries to resolve this domain by querying the DNS server for the A record. However, when you try to send an email to testexample.com, so test@example.com, the mail server would query the DNS server to find the MX record. So if you want to look up the IP address of a domain from the command line, you can use a tool like nslookup, and then we can even go to something like nslookup.io, which is a website that does it for you. So if you don't want to do a command line, or if you don't have access to a command line, and maybe you're just running it from your phone or something, and you still want to find the DNS records for something, then you can actually go to nslookup.io, which is, it's literally what it looks like right here. So if we went to nslookup.io, you can tell I use that very frequently. That's the website. That's basically it. And then you just kind of go in here, and then you do, let's do example.com, and then run that. And then it says, look, this is the IPv4 address of example.com. This is the IPv6 address. Now check this out, right? So we talked about the IPv4 address and the IP address just changing regularly. So this is the current one that is happening as I record this. But when we go look at this thing, look at, actually, you know what? It is the same IP address. Okay, never mind. My bad. Their IP address did not change. I thought for one reason or another, I thought that their IP address would actually be dynamic and it would change. But I guess example.com, not that big of a deal. Google needs to rotate their IP address. Microsoft will need to rotate their IP address, so on and so forth. So nslookup does the same exact thing that nslookup.io does. And the command is basically nslookup, and then you put the domain name, and then that's pretty much it. And you can do www, you could do https ://example.com. Essentially any way that you would refer to the domain name, so long as you have the end of it right, which is, I believe, the top level domain. As long as you have that right, then everything else will actually map to the place that it should, and then it'll get you the A record as well as the quad A record, which is in this particular case this. So this is an IPv6, this is IPv4. Now, it led to 4 packets, this example that we had right here. And in the terminal below, we can see that the first and third packets sent the DNS queries from the A and quad A records, respectively. The second and fourth packets show the DNS query responses. So the first and third is the queries that were sent out, and then this one and this one were the responses that came back to us. And so we can see that at the end of the response for this one, we see the IPv4, and at the end of the response for this one, the quad A record here, we see that this is the IPv6 address for example.com. So which DNS record type refers to IPv6? And that is 1, 2, 3, 4, the IPv4, or quad A. It's the quad A record that refers to IPv6. Which DNS record refers to the email server? That would be the MX record. And that's basically it. That's really all you need to know for now for the name records, the DNS records. So let's go into the who is protocol. All right, so in order for these records, for the A, quad A, MX records, or other DNS records for the domain name, in order for those things to be set, somebody needs to have the authority to do that. And whoever registers a domain name is granted this power. So for example, you can get the valid DNS records for example.com if you are the one who registers that domain, meaning the person, or the entity, I should say. The entity who actually registers that domain name is the person or the entity that would set the valid DNS records for that domain name. So for example, you can register any available domain name for 1 or more years. You need to pay the annual fee, and you're required to provide accurate contact information as the registrant. So your actual name, your phone number, the address, so on and so forth. This information is part of the data available via a WHOIS record and is available publicly unless you privatize that information. Although written in uppercase, WHOIS is not an acronym. It's pronounced who is, right? However, don't worry if you want to register a domain without revealing your contact information. You can use one of the privacy services and hide all your information from the record. So you can actually be private. And in a lot of cases, a lot of people are, because you don't want the person who owns the domain name to get spammed all the time and get contacted by people all the time. It just becomes a really pain in the ass. For the most part, most WHOIS records are actually private records. Now, you can look up WHOIS records of any registered domain name using one of the online services via the command line tool WHOIS, available on Linux systems, among others. And as expected, a WHOIS record provides information about the entity that is registering the domain name, including the person's name or the company's name, the phone number, the email address, so on and so forth. And we can see this is kind of what it looks like. So that doesn't really do me much good. So let me kind of zoom in on this, see if I can get you a little bit better. Okay, so the registrar WHOIS server is based on, the corporate domains website. And let's see, the registrar itself is corporate domains. The contact email is domain abuse at CSC Global. This is their phone number. The registrant name is privatized, so therefore we don't see it. But this is essentially all the information about the actual person or the company. So the registrant could actually be a company. The admin most likely is going to be a person, but it could also be a company that manages the domain name. And then there's, their phone number, their fax number, their email address, so on and so forth. So all of this information falls under the WHOIS records of a given domain, right? So I think for the purpose of this exercise, it's actually been kind of marked out for us because maybe they want us to actually run it. So in this case, right, WHOIS, and then this is the .com that has been redacted for us. But this is the record. This is kind of what it looks like. So the registrar is GoDaddy. They registered their website with GoDaddy. This is the abusegodaddy.com, the phone number to GoDaddy to contact them. And then you have the registrant information that is private, right? Domain by proxy LLC, so on and so forth. So when was the x.com record created? Provide the answer in this format. When was the twitter.com record created? Provide the answer in that format. So for the purpose of this exercise, now we actually get to go and use our virtual machine on our attack box. So I got to zoom out of this a little bit and go to split view. And now I have access to my attack box here. And so we're just going to run the WHOIS domain here. So we're going to do WHOIS, and then we will do x.com. And then press enter. And we get a bunch of information here, and we need to go to the top to find the date, right? So they want year, month format, which is when was it created. So if we go here, we can say creation date is right here, 1993, 04, 02, and that will most likely be the date. So let's paste that, see if that's right. That is right. Now, when was twitter.com created? So same thing, WHOIS. Let me make sure it's actually typing in here. WHOIS twitter.com. And then we'll go in here and we'll scroll up, and then we'll get the creation date for the Twitter domain name. So where is that? Creation date 2000. So 01/21. It's interesting that x.com was actually older than twitter.com. I think obviously, like when the domain names became a thing, there were a lot of people that bought these like very short domain names. So probably a.com, b.com, like all these domain names, because they're so easy to remember. There were people that just made a killing from buying domain names at the very, very beginning, and they bought it for, relatively cheap prices, and they were parking them. So it's called parking a domain name, and you basically just pay the annual fee for having it. And as time went by and these things became more and more popular, so let's see, how much did Elon Musk pay for x.com? And this is the let's see, he bought it back from PayPal, so I guess PayPal owned it. He co-founded X.com in '99 and invested about 12 million in the company. He was the largest shareholder in the combined company. X merged with another company, also purchased Twitter for 44 billion and rebranded it as X. So I guess he's owned it essentially for the most part. But as we can see right here, that it was actually created in 1993. So this was not Elon Musk who originally bought it. He bought it from whoever the original creator, the registrant was. So, you know, kind of random trivia. I don't know if that's going to be ever important to you, but that's kind of where my thoughts go usually. I'm like, oh, I wonder how much he paid for this. I wonder how much this whole thing cost, coming from 1993 to 1999, which is 6 years. It's like, I wonder how much that thing appreciated in 6 years, and whoever the original person was, like, I wonder how much he paid for that, or how much he made off of that, I guess I should say. Okay, so let's go to the HTTPS protocol. HTTPS is the protocol that is all about web browsing. So if we go here and we look at this at the very, very top right here, we can see that TryHackMe has HTTPS and then TryHackMe, right? So if I went to any website, dnslookup.com, click on that, click on it one more time, and then we can see that it is HTTPS. If we go to google.com, click on that, we can see that it is HTTPS. So HTTPS is the secure version of HTTP, which is the hypertext transfer protocol, which is the protocol for web browsing. So anytime that you use your web browser, you are for the most part using HTTP and HTTPS protocols. Hypertext transfer protocol, the S in HTTPS stands for secure. And this protocol relies on TCP and defines how your web browser communicates with web servers. And some of the commands, which are the most common commands, are get, post, put, and delete. Get retrieves data. Post allows us to submit data. Put is used to create a new resource on the server and to update. So typically, I associate put with updating data and overriding existing information. And then delete, obviously, as the name suggests, deletes a specific file or resource on the server. So when I make a request to google.com, right? So if I just go here and I do google.com, press enter, I now made a get request to get google.com, okay? When I go in here and I type in how much did Elon Musk did that, now I just did a post request where I sent a post. I sent something to Google, and then they're now sending me data back, okay? And then, you know, put and delete typically has to do with updating databases or something like that. So for the most part, your interaction with the websites that you go to has a lot to do with get and post requests. For the most part, that's the majority of transactions or communications, conversations that happen with a web browser. But then when you update something or when you delete something, you delete a specified file or resource on the web server that you're accessing. So you delete one of your pictures from Facebook, you are sending a delete request to the Facebook server, and then they delete it from their servers. So HTTP commonly uses port 80 and HTTPS commonly uses port 443, and these are both TCP ports. And if you remember from the last video that we did, TCP is a connection-based protocol, meaning that we have to establish a solidified connection in order for TCP to actually work. UDP is a connection-less protocol, meaning it really doesn't give a damn whether or not a connection is made. It just sends data. It doesn't even verify whether or not the data was received or anything like that, right? So TCP is the more secure, the more reliable version of the two protocols between TCP and UDP. And then there are less commonly known ports such as 8080 and 8443. 8080 is typically reserved for actual web servers. So Apache, that's what I kind of connect 8080 to. And then 8443 again is also, these are both also HTTP protocols, but usually they're used for specific web servers. When you're looking at HTTP and HTTPS specifically in terms of web browsing, for the most part, this is more common, okay? It's commonly used. This is not a be-all and end-all. For the most part, it's 80 and 443 are reserved for HTTP and HTTPS respectively. Now in this example, we're going to look at Firefox to browse the 10.10.163.136. Our browser fetches the web page and displays it perfectly. However, we are interested in what happens behind the scenes. So I'm guessing this is in the screenshot here, they're showing a different IP address that they access, but this is the IP address that was assigned to me when I launched this right here. So if I come out of this and I just go to the browser here, and also if you're connected via OpenVPN to the TryHackMe server, you can just do this from your own computer. I'm doing it from the AttackBox web browser because for me it's a little bit easier to actually access this way and to do the recording without having to worry about you seeing all the other stuff that's sitting on my computer. So this is the website, right? So we have the Art of Espresso that's loading, so on and so forth. But we're interested in what happens behind the scenes. So if we use Wireshark, we can examine the exchange between the Firefox browser and the web server more closely. The screenshot below from Wireshark shows the text sent by the browser in red and the web server response in blue. And we'll get into how to analyze Wireshark responses. I don't know if I have to do it for this particular room. If I do, then we'll just pull up Wireshark. But this is basically what the screenshot looks like if you actually go into Wireshark and look at the HTTP stream that is done for this website. So first there was a GET request, right? So we sent a GET requests to the domain name or the IP address, which was the one for the coffee website or whatever, the espresso website that we just got. So this whole thing is the request contents. And then there was a response from this web server saying, okay, the response code 200 means that your request went through, and it gave back what you wanted to do, and it gave you that response. And then this is all the contents of the response that you got. And so the title is The Art of Espresso. The body is, you know, what is espresso? Espresso is a concentrated form of coffee, yada, yada, yada. So that is it, right? So you have the request, and then you have the response. And that's typically what it's like when you interact with a web server, okay? Now, as we remember from networking concepts, we use the telnet client to connect to the web server running on 10.10 at port 80. We had to send a couple of lines such and such to get the page that we wanted. On some servers, you might get the file without sending the host anything. So you can use this method to access any page and not just the default page, which is at the /. To get the file.html, you would send get file.html HTTP1 for instance, and then get file HTML might work depending on the web server in use. The approach is efficient for troubleshooting as you would be talking HTTP with the server, which is basically the language that the server requires. So now we're going to actually do that. So we're going to use telnet to access the file flag.html on this particular IP address. So what is the actual hidden flag? So in order for me to do that, and we want to do it with our command line here. So I'm going to clear my command line. And I'm literally just going to use the telnet command very simply. So it's telnet, and then you do the IP address, which is 10.10, what is it, 163.136 is my, and then we're going to do it on port 80. So that's basically what we do right here. You just do that, and then you press enter, and then there you go. The connection is now made. Now what I need to do is I need to actually form my GET request to the actual file that I'm looking for. So in this particular case, instead of doing GET, just a root right here, and then doing HTTP1, I'm going to do get /flag HTML, and then do HTTP1, and then let's do that real quick. And the host could be anything, I guess. So I'm going to do a get, and it's all caps lock, and I'm going to do /flag.html, and then I'm going to do HTTP1, also in all caps, /1.1, and that's what that looks like. We press enter. And then the next line, we need to give it a host. So in this case, it's going to be host, and it could be anything, I guess. So I will do host, and I will do anything, and then press enter, and then one more enter to actually send it, and then we actually get our response. And so it worked because we actually did get the response here. So now what we're trying to do is find the flag. So the response was okay. So I actually got a good response from this thing. And then here's what it is. This is where the document actually starts, right? The header is hidden message, and the style of the body and everything is like that. And then the hidden text right here is the flag. So it's THM ... and then copy and then you go here and you go there and you paste it, and there we go. So just to give you a quick review, just so you know what I entered to get this flag, okay? First I did telnet. Let's zoom in, hopefully you can actually see this. So I did telnet, and then I did the IP address that I've been provided, and then I did 80 because I'm trying to connect to the HTTP port on 80. And then as long as this is up, as long as that port and that IP address is up, then you will get, okay, you were connected and this is all good. All of this is just going to come automatically without you doing anything. As soon as you press enter on this command, the rest of this comes up immediately. The next one is these two commands that you have to enter. So the get request is the request that I want to send to the web server. So I want to pull this flag HTML file from the web server. And then I'm going to give it the language essentially that I'm communicating with it, which is HTTP/1.1, which is the version of HTTP that we're using to make this request. Okay. So essentially this could be get /file.html, anything.html, or just / by itself, meaning that I want to go into the root domain, the root partition of this web server, and then that would be followed by HTTP 1.1. So this part is going to be essentially no matter what kind of request you make, that part is going to be at the end of it. This is the part that will change depending on what type of data you are trying to get from the server. So you type this, you press enter, and then on the very next line, you need to give it some kind of a host value. So in this case, we just did anything as the host, and then I pressed enter, which gave me this blank line, and I pressed enter again, and then it gave me the actual response from the web server. And then it tells me that this is the server type, and this is the date, and the content type, and then begins the actual data that I requested. So now it's the HTML document that I requested, and then it's going to say in the title that this is a hidden message, which makes me feel like I'm in the right place. This is the style of the rest of the website, of the rest of the document. So background is white, color is white, font family is Arial, sans serif, font size is 1 pixel, . So font being 1 pixel is like super small. So you can imagine that if it was actually on the web browser, most likely it's going to be missed because it's so small. But then because we're looking at the source code here, it's not going to be very small over here. We're going to be able to see exactly what we want, which in this particular case was the flag. So we got it and it's all good and we did right and I'm happy about it. So I hope you got the same answer that I got. So now let's go to the transferring files using FTP. FTP, as the name implies, is the file transfer protocol, and it's the protocol that's used to transfer files. So it's very efficient for file transfer. When all the conditions are equal, it can achieve higher speeds than HTTP, which is basically designed to retrieve web pages. Now, the commands defined by FTP protocol are the user, the pass, which mean the username and the password. And then you have the RETR for retrieving. So it's used to download a file from the server. And then you have STOR to store or upload a file to the server, right? So RETR retrieves, STOR stores or uploads a file into the server. Now, the FTP port is port 21 by default, and it's conducted via another connection from the client to the server. This is not a secure port, okay? Just to kind of put this out there. This is not a secure version of the port that we're trying to use. And then as we go into the secure protocols for networking, we're going to talk about the secure version of FTP, which is actually SSH, or I think it's actually SFTP. I may be wrong. I know that port 22, which is secure shell, is a secure encrypted port. FTP is not an encrypted port. It could technically just be FTPS, File Transfer Protocol Secure, or SFTP, which is Secure File Transfer Protocol. In the terminal below, we executed the command FTP to connect to the server, and we used the username Anonymous to log in. We didn't provide any password. Issuing ls returned a list of files available for download. Typing ASCII switched to the ASCII mode as it is a text file, and then get the coffee txt allowed us to retrieve the file. So FTP and then the IP address actually connected to it right here. And then the very first one is asking for the name, and so we did anonymous press enter, please specify password, and then they just pressed enter without putting anything. And the password, the login was successful because I guess Anonymous doesn't require a password. And then the remote username is Unix, the binary code is da da da. So all of this is just responses from the system. And then you have this command line. So the command line changes from this to FTP if you've actually successfully logged in, which allows you to then run commands like ls, because it is a Unix, see, remote system type is Unix. So since it's Unix, you know that ls will actually work, and then it's going to really, I guess, respond with the stuff that you got over here. So the directory send was actually okay, so it actually received the information that you wanted from it. And then we did type ASCII to change it to ASCII mode. And then we said get coffee.txt, and then local coffee.txt is how it was downloaded. Coffee.txt came from the location, entering passive mode, opening binary mode, warning 47 da 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 da, transfer complete. Bytes received in da 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 seconds, and then we just put quit, and then we exited out of it, and it's all good. Now, if you wanted to look at this on Wireshark to see what the actual transaction looked like, this is what it looks like. So let me see if I can zoom in for you a little bit. So we have the very first request, which was responded with a status code of 220, meaning that it was successful. And then the very next prompt that was sent was user anonymous. And then we got a please specify the password, and then we did nothing. So pass is empty here. And then another 230 response, which is a successful. Anything in the series of 200 is successful. So when you see 200 responses, that means everything was okay from the system and you got some kind of a successful message. So password was empty, login was successful. The system responded and gave us the type that we wanted, which is the Unix type. And I guess ls in this case would be L8 in this case. And then it went into passive mode. And then list is a command that you can make. Oh no, so you know what? ls is list right here. So my bad. So list is the command that we sent into it to actually get access to the contents of the directory. And then the directory responded. And then type A, meaning for switching to the ASCII mode, and then the system responded, and then entering passive mode, so on and so forth. So these, the ones that are in red, are the commands that was sent from the actual user. But what seems to be the case is that, so if we can try to track this down over here, so we did password login successful, remote system type is Unix, using binary mode to transfer files. The very next command was ls, so there was no pasv to enter passive mode, and then it automatically just entered passive mode. And then here comes the directory listing, and then directory send was okay, and then we did type ASCII, and then it switched to ASCII mode, and then we did the get coffee, and then that happened, and then it entered passive mode by itself again. So it seemed like it happened as an automatic send to the system. So it was something that was automatically requested, and then the response was entering into passive mode. It wasn't anything that the user in this particular case actually did, because these commands, the red commands that we see here, they imply that the user actually entered PASV and then entered PASV over here. So that was not indeed the case. So now, use the FTP client, FTP on the attack box, access the server at this location, and retrieve flag.txt. What is the flag that was found? So we are just going to run the command as it is over here. Very, very simple. And I'm going to do exactly what they say to do. So we're going to do FTP, and then I'm going to do the domain name that I've been given, or the IP address, excuse me. So that's it, FTP, and then the IP address, press enter. And I'll zoom in on this for you a little bit. The name in this case is going to be what? Anonymous. Press enter. Password is just going to be empty, so I'm just going to press enter. And I am now logged in. So check this out. Very, very simple, right? Easy money. So FTP and then the IP address. Then the response came up to here. This was the response that I got, and I was supposed to send something in. So I just said the user is going to be anonymous. And then check this out, it's root permissions too. Isn't that interesting? So the user is going to be anonymous. Excellent. Please specify the password. And I didn't input anything. I just pressed enter, and then the login was successful. Now, this is not going to be the case in the real world, just so you know. This is a lab environment. They're trying to make it as easy for us as possible. in a lab environment, most likely you're not going to be able to log in as anonymous. And most like 99.999% of the time, you need to have somebody's actual username as well as the password, because you are not going to get into the FTP system that easily. Just giving you a heads up here. But, I pressed enter with no password and it said login successful, remote type is Unix. So using binary mode. Now, if it's Unix, if I do print working directory, it should say that this is my current directory. I'm inside the root directory. If I do ls, it should just list all the stuff that is in the directory, which in this particular case is the coffee file, the flag file, and the t file. So now the next command that we had over here was to just switch to ASCII mode. So we'll just do type ASCII, press enter, and now we've switched to ASCII mode. Now I can do get flag.txt, press enter, and file transfer is complete as we get over here, right? So I did ls, which you saw me do. It's all good. It listed the contents of the directory, type ASCII, and it switched it to ASCII mode. And then I did get flag.txt, and then it made the requests. And then finally it said the transfer has been complete. So now I should have a flag.txt file. I don't know where it is, but seems to be that I have it. So now that we have that, we can actually quit out of this mofo. Boom. And then that is goodbye. So it's all good. So it downloaded to wherever I am currently logged into on my terminal. So if I do print working directory, it's inside of the root directory. If I do ls, I should see that there is actually a flag file inside of my root directory. So I can now simply do cat for concatenate flag.txt, and there is my flag, baby. I love when these exercises work as smoothly as they do. Then again, these are very, very simple exercises. So hopefully you were able to follow along with that one as well, and you were able to get the response that I just got. So now let's go into the SMTP protocol. So just like browsing the web and downloading files, sending email also has its own protocol, and that is the Simple Mail Transfer Protocol, which is SMTP, which defines how a mail client talks with a mail server and how a mail server talks with another mail server. So the analogy for SMTP is when you go to the local post office to send a package, you greet the employee, you tell them where you want to send your package and provide the sender's information before handing them the package. Depending on the country that you're in, you might be asked to show the ID. This process is not very different from SMTP. Now let's present some of the commands that are used by the mail client when it transfers an email to the server. So hello, or EHLO, initiates the session. And this is, I believe, an actual O, so it's not a 0. And then we have mail from specifies the sender's email address. Receipt to, RCPT2, specifies the recipient's email address. And then data indicates the client will be sending the content of the email message. And then this dot is sent by a line to itself to indicate the end of the whatever. I guess the sentence is not finished. That's funny. Okay. So terminal shows an example of an email sent via the telnet protocol. So if you did not watch our previous video, you can use telnet on a variety of different port numbers. So we actually did telnet on port 80, but now we can do telnet on port 25, which is the SMTP, the Simple Mail Transfer Protocol server. So we can use it so that we can actually send an email. Now, once it is connected, then it's going to just say, hey, you know what? Hello, client THM, right? And then mail from this person, and then receipt to this person, and then data. And then it says enter message ending with a dot on a line by itself. So from user to user, telnet email is going to be subject, and it's going to be say, hello, I am using telnet to send you an email, and then dot by itself to imply that we are ending the email on a line by itself. And then that's it. And we should get an OK. And then we can do quit so that you can actually close your connection. And that's basically it. So sending an email using telnet is quite cumbersome. However, it helps you better understand the commands that your email client uses under the hood. Wireshark shows us what's actually happening. So we go here, and the first request to actually connect to telnet was successful. And then so we sent a hello client.thm. And so we were initiating the conversation to the client.thm server. And then the response was, hello, everything's all good. Then we said we want to mail from this email address. We want to send it to this email address. And then all of these things was okay, accepted. Now the data, you press data, and then it says, all right, enter the message ending with this. So you press data, and then you press enter, and it says enter the message ending with yada, yada, yada. And then you said from this person to this person, subject is going to be this person or this subject. And then hello, I am using the telnet to send you an email, and then dot by itself at the very end on its own line is implying that that's the end of the email, and it's going to be okay, and then quit, and we're good. So that's basically what that looks like. So now that we've actually covered it, let's send an email. So which SMTP command indicates that the client will start the contents of the email message, and that would be data. And when does the email client, or what does the email client send to indicate that the message has been fully entered, and that is the dot on a single line. I mean, I guess we don't have to send an email. I'm kind of disappointed. I was hoping that we can actually send an email, but yeah, I'm just gonna leave it alone. I'm not gonna go down the rabbit hole because I always end up going down the rabbit hole. But the instructions are very, very clear, and it makes it even more clear when you're looking at the Wireshark output. So up until, you get the connection via telnet, first thing you do HELO, and then the name of the actual server that you want to communicate with, or you want to use to send your email. And then it's going to say, okay, you're all good. Now we're going to mail from, that would be the next command. So mail from, all in caps, and then you do a colon. And then inside these brackets right here, you would put the email address from that you want to send from. And it's obviously sitting on the client THM that you've just connected to. And it's going to say, all right, cool. And you say RCPT2 colon inside the brackets, you would do the name of the email that you're sending to. And it says, all right, that's cool too. And then you type data, all caps, press enter. And it says, all right, cool, enter the message ending with whatever by itself. And then this is all being typed by us. So from user client to this person, subject, telnet email address. And then you type your actual body of your email. And then when you're done, however long the body is, the very last line needs to be a dot by itself. And then you press enter and it says, okay, all good. And then it's sent it, so you're all good. And then now you can just type quit so that we can close the connection with the mail server. And that's basically it. So now let's talk about the POP3 server, or the POP3 protocol that is for receiving email. The post office protocol version 3, which is POP3, is what we use to check our received email. So you receive an email and you want to download it to your local mail client, and this allows you to do that. So it allows the client to communicate with the mail server and retrieve the email messages on there. Without going into all the details, an email client sends its messages by relying on SMTP and retrieves them by using Post Office Protocol 3. SMTP is similar to handing your envelope or package to the post office. POP3 is similar to checking your mailbox for new letters or packages. So very simple, right? SMTP, you drop it off at the post office. POP3 is your actual mailbox in front of your house. Some common POP3 commands are user for the user, pass for the password, stat to request the number of messages and the total size that are currently in your inbox, list lists all of the messages and their sizes. So stat just says this is the number of messages and how big they are. List actually lists the messages and their individual sizes, and then you can retrieve the message by its number, right? So retrieving the specified message, DELE deletes the number, so marks the message for deletion, and then quit ends the session so that you can get out of it. And then of course you can use telnet to do the same thing. POP3 sits on the 110 port, so SMTP was on port 25, POP3 is on port 110. So telnet, the IP address 110, you connect and everything's all good. Okay, so far everything's all good. This is going to be the response that you get by just doing telnet IP and then the port number. And then we do authorization, okay, plain, dot, all good, user, strategos, I guess, whatever. And it's going to say, okay, password is whatever. I guess, and then you press logged in. You press the password, you press enter, and it says, okay, you're logged in. Then you do stat, and it says 3, and then the size. So there's 3 messages, and the size is 1,264 bytes, I guess. And then we have list, and then so it says, okay, 3 messages. This one is this size, this one is this size, so on and so forth. And you say retrieve number 3, so retrieving this email, and it says okay, and here we go. So this is where it's coming from. This is where it's to, which is Strategos or Strategos or whatever. And then it says received from this IP address by example with SMTP envelope from user client. This is the ID. This is da 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 da. This is the actual body. So this is literally the email that we sent in the previous exercise that we did, or that they showed us using SMTP. It's the same exact email, but now since it's been sent to Strategos or Strategos, whatever, this is the body of the email that they got. And so now, cool, all right, quit, and then it's logging out. So he didn't even delete the email. He just read the email, and I was like, all right, cool, all right, we're good. So someone capturing their network packets would be able to intercept the exchange traffic as per previous Wireshark captures. The command in red are sent by the client, and the lines in blue are the servers. So first, we connected, and then it says auth to authenticate, and it says, okay, plain text, all that stuff. User is going to be Strategos. Okay, password is actually entered in here. So there was a password that was entered because it is a mail server after all. And it says, all right, cool, you're logged in. And it says stat, show me my emails. And it's like, here are the email count and the size. Okay, list them. And here's what it did. And then it said retrieve number 3. And then this is the response from the server. And then he said quit. And he bounced. And that was it. Very, very simple. So connecting, all right, cool, now we can actually connect. So connecting to the POP3 server requires authentication. Use the following login credentials when needed. Now look at the traffic exchange. What is the name of the POP3 server running on the remote server? So look at this. What is the name of the POP3 server running on the remote server? I would say it's xClient, right? Or is it Dovecot? Okay, Dovecot Ubuntu Ready. So what is the name of the server that is available? So let me just double check and make sure that I'm good. Okay, yeah, it is Dovecot. So Dovecot was the correct answer, which is right here. So it says Dovecot is ready. That's the name of the mail server. That's in our traffic capture. Now use telnet to connect to POP3, and then what is the flag contained in the 4th message? So we are gonna go out here one more time. We're gonna clear this bad boy. We're gonna do telnet, and then we're going to connect to the same IP, but we're doing it on port 110. It's gonna press enter. I totally misspelled telnet. So telnet, there we go. 10, and then for, my God, what am I doing here? What am I doing? Telnet, and then we're gonna do 10, 163, 136, port 110, very good. All right, cool. Now we are actually ready. So it says what? Connected to such and such. Okay, client is ready. So what is the next thing that we got to do? We got to send an authentication request, right? So that's the first thing that it said, client is ready. So the next thing that we're going to do in all caps, we're going to do, let me make sure I'm all caps, auth, press enter. All right, cool. You are ready. Now user is going to be, who's the user? Linda, right? Yeah, Linda. So user is Linda. Linda, listen. Very good. User is okay. Pass, just like that, is going to be PA $$123, enter. There we go. We are now officially logged in. So I can first just do this, right? Stat, and it's going to say, all right, there are 4 messages. I can do list, and then it's going to give me my list of 4 messages. So here we go, right? Just to show you what's going on here. So the client is ready. I did auth, and then it said okay, and it gave me these 3 lines, and it says user Linda, so capitalized user, and then Linda is the actual username, and then pass, and then that's the actual password, and now I'm logged in. The first command I gave it was stat. It said you have 4 messages. Then I said list, and then it gave me my list of messages. So now I'm going to do RETR, and I'm going to say 4, press enter, and now here's the email, and there we got it. So RETR4, okay, cool. This is the da 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 da, and it's from the user client Linda at server. This is the flag. There's my flag, baby. Copy my flag, go over here, paste the flag, and we are good. All right, so now let's talk about IMAP, and we are officially wrapped with this room. POP3 is enough when working from one device, maybe your favorite email client on your desktop. However, what if you want to check your email from your office desktop computer and from your laptop or even your smartphone? In this scenario, you need a protocol that allows synchronization of messages instead of deleting a message after retrieving it. So for example, what I just did will delete email number 4, and I haven't actually quitted from this thing. So if I go over here, and let's see if we do list one more time on this thing, if it'll still have, oh, it still has all of my messages. So if I quit, let's quit and then go back and do another connection to the telnet, and it's going to say it's ready. So I'm going to do auth, and then it says unknown command. So why am I not ready? What did I do? Error unknown command? What? Quit. Maybe I did something wrong. So connection closed by foreign host. So connected, oh, it's because I had the extra backslash. So there you go, that's all good. So now I want to authenticate, press enter, very good. User is going to be Linda, and then I'm going to do pass of PA $123, press enter. And now if we do list, oh, I still have 4. So I guess it doesn't automatically just delete the emails. So that is, okay, never mind. So I was mistaken. So that's my bad. But I mean, based on the instructions, it kind of leads you to believe that it will allow synchronization instead of deleting a message after retrieving it. You see what I'm saying? So one solution to maintaining a synchronized mailbox across multiple devices, Internet Message Access Protocol, IMAP, Message Access Protocol. So IMAP allows synchronizing the read, moved, and deleted messages. Let me say that one more time because my accent just destroyed it. IMAP allows synchronizing read, moved, and deleted messages. IMAP is quite convenient when you check your email via multiple clients. Unlike POP3, which tends to minimize server storage as email is downloaded and deleted from the remote server, IMAP tends to use more storage as email is kept on the server and synchronized across the mail clients, right? So POP3 tends to minimize server usage because the mail is downloaded and deleted from the remote server. The IMAP tends to use more storage because the mail is kept on the server instead of being downloaded, and it's synchronized across the mail clients. The protocol commands are more complicated than POP3. These are the list. So we have login, and then you give it the username and the password, and it authenticates you. Then you say select the mailbox. So it selects the mailbox folder that you want to work with. And then you say fetch the mail number and the data item name. So for example, fetch number 3 body, for example, right? So you want to retrieve the body of email number 3, and it fetches message number 3, header and body. And then you say move the sequence set to the mailbox. So it moves the specified messages to another mailbox, and then copy the sequence set and then the data item name. So copies the specified messages to another mailbox and then log out. So this is definitely much more complicated than what we dealt with SMTP as well as POP3. So knowing that the IMAP server listens on TCP port 143 by default, we will use Telnet to connect to it and then fetch the messages. So Telnet IP address port 143. It says all good, you got your connection, everything's all good. So login Strategos. That's the first thing. Login Strategos. Now, we did that and it said okay. So I guess the password is being hidden from us in this case. And then it says select inbox. So it says okay, flagged or whatever. These are the flags, meaning what you can select as the types of messages that are available for you. And then so these are the flags that are available. So it says okay, 4 exists, right? Is that what's the next thing? So fetch, he didn't even do or maybe that's the flags permitted. I don't think this was the, let's see, what's the next thing? Let's go to this. This is actually more useful. So login, Strategos, and the password. And I said, okay, so yeah, these are all the responses from the server. So this was, none of these things was something that I would have actually seen. So then the next one would have been select inbox. So the next command that he did was the actual select inbox command, which is right here. So login Strategos and then select inbox. After he did select inbox, these are all of the responses that could potentially exist. So 4 exist and 0 recent, all of these things is coming from the server, all of this blue. And then he says fetch 3 body. So fetching 3, which is email number 3, I guess, and the body of it. And then it retrieved the body of that email. And then it said, okay, log out. So for the most part, that was fairly simple if we just know what we are looking at here. So this is what the user sent. This is what the user sent. And all of this was a response from the server. Okay, so that's very important to understand. So do we have an exercise that says what IMAP command retrieves the 4th email message? So it would be fetch, right? So fetch 4, and then we do body like that, and that's what would receive it. But the most complicated part about this is knowing the difference between, at least when you're analyzing something like this that's not color coded. I guess it's everything that starts with kind of an asterisk is the request or the response, excuse me, from the server, and then the stuff that's also misleading because this is starting with an A, so, and this is starting with a B, and then these are all asterisks, and then this is starting with a B. So that's not a good enough system to know which one is the server and which one is the client. So the best way that I could analyze this just as a first timer kind of looking at this would be the ones in the blue obviously are the server. This is what the client sent. So this was login, their username and the password, and then they were able to retrieve some kind of a response, and it started with okay, everything's all good, da 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 da, and it's like, all right, cool, select the inbox. And then so the response from the server was, all right, I'm selecting your inbox, these are all the things that you can check out. And then he said, all right, fetch number 3. So 4 exists, meaning there are 4 emails that exist, right? 0 of them are recent, and then unseen is 2. UID validity, UIDs are valid, UID next 5, predicted next UID, so on and so forth. So these are the key elements of this response from the server. There are 4 that exist, 0 of them are recent, and it goes, okay, so fetch the number 3, fetch number 3's body. And then so it fetches the header as well as the body. So this is all header, and then this is the body right here. Hello, I'm using Telnet to send you an email. Okay, cool. And then that's it, right? And then you do log out and you get out of the system. So we don't have an exercise for this one because they didn't give us a username and password that we can use, but you can kind of, hopefully you can wrap your head around the process of using IMAP to retrieve email. And with that being said, we're just going to talk about our conclusion, give you a couple of final notes, and we will wrap this video. So in the last room, we discussed the Telnet protocol, and we used a few of the ports that were definitely not on here. In this room, we actually used the other fundamental protocols, and a lot of them were done with Telnet. So we actually accessed an HTTP server, FTP, SMTP, POP3, and IMAP. We were shown at the very least how to do it, and in a few of them we did ourselves. And we did that with the Telnet protocol. We just did it on different ports. Now, with the protocols that we covered, we now have a better understanding of how domain names are resolved, how web pages are served, how email is sent and received. And another primary purpose of this room is to give you a good understanding of how a protocol functions behind the graphical interfaces, which is exactly what we did, right? So the protocol itself was technically Telnet. Technically, that was a protocol. We just used different port numbers to be able to access the various services that you can access using Telnet. Telnet is the protocol. The transport layer is that it was using the transport, the TCP, and then we have the port 23, which is the default for Telnet. But then you were also able to use the HTTP port using Telnet. We were able to use the FTP port using Telnet, right? And then we were able to see some examples of the SMTP POP3 and the IMAP as well using the Telnet protocol. So that's what's important to understand, is that for the most part, the FTP one, actually, I think we did FTP, and then we used FTP and then the IP address. But SMTP, POP3, and IMAP, as well as I think it was the ones that we did in the last video, they were all using Telnet and then the IP address, and then we just gave it a port number. So these are essentially the protocols. These are some of the key protocols, right? The core networking protocols, so to speak, that are used in networking as a topic, as a concept. And then in the next video, we're going to talk about the secure versions of some of these very important protocols and how we can access them. HTTPS is technically a secure protocol, so that really won't count, but I think we'll probably talk about it as well. But I think we're going to be talking about secure shell, for example, or secure copy, and file transfer protocol secured, and so on and so forth. So there are secure versions of all of these protocols, and it's very, very important to know that in the context of system administration, in the context of cybersecurity, you would not use FTP because it is not encrypted and it is not the secure version of that protocol or that port. Therefore, it won't be encrypted, and people can basically very easily capture the data that's being transferred, communicated back and forth on that port number. So it's just really, really important to understand. So that is basically it for this, and we are officially wrapped. So let me just give you a couple of notes, and we'll wrap it up. All right, so if you found this video useful, and if you want to get future videos on the CySec101 pathway, and of course the big video that's going to be coming up in the next couple of weeks, which is the Security Plus training series that's coming out, I do encourage you to like, subscribe, and turn on the notification bell so that you get notified the next time that those videos come out. And of course, drop a comment. I do very much love hearing from people inside of the comment section. If you just want to say hi, if you just want to say thanks, all of that stuff is super welcome. If you have a question, please drop your questions. If you need something clarified, please let me know. There was actually a guy earlier today that asked about some of the new rooms that came from TryHackMe, which I'm going to be creating because he asked for it. And I'm like, okay, of course, if I can get anything that will help you guys in your journey of cybersecurity, I would be more than happy to do it. So this is why I do these things. So please drop a comment. Let me know if you have any questions and if there's anything that you need from me. And if I can, I will. If I can't, I'll politely say, I'm sorry, I can't, or at least not right now, whatever, right? So like, subscribe, turn on the notification bell, drop a comment, say hi, and just let me know that you're actually in the community. It would mean a lot to hear from you. And then there's the Hackaholics Anonymous membership community, which is the premier YouTube community for security professionals and hackers. And it has 4 tiers of perks. And it starts with the cyber supporter at $4.99, and they get their Discord server as well as access to me directly and all of our advanced members. They get early access to content. And then we have the advanced members that get Python automations every single month. They get live streams every single month with me. They get their own Discord servers. They get exclusive content, exclusive downloads, like all of the notes and the practice questions and the practice exams that's going to be coming out with the Security Plus course that's coming out in the next couple of weeks. So if you want to join Hackaholics Anonymous, you can do so in the link in the description below. You can go to our homepage and click the join button, or you can simply go to youtube.com/@HankHacks, hackers/join, and you'll be able to join the best community for security professionals and hackers. And I really look forward to seeing you in our Discord chats and inside of the community tab for the Hackaholics Anonymous members. And if nothing else, then I would very much love to see you in the comment section in our YouTube community over here. So this is your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker/protector. No one else loves you. Hank loves you. Love, peace, and chicken grease. The new year is right around the corner, baby. So I hope you're getting all your ducks in a row and getting ready for 2025. And I will see you in the next video. In episode 17 of the CySec101 pathway, we are going to go through the networking secure protocols. And this is the last room that falls in the 4 rooms that we were talking about for the networking module of the Cybersecurity 101 pathway of TryHackMe. And after this video is over, we're going to actually start using some of the tools that have been outlined for us to use as far as networking is concerned, and of course how networking connects to cybersecurity. So that is the goal for today's video and for today's room. This video has been sponsored by the Hackaholics Anonymous membership community, the premier membership community for security professionals and hackers. And you get 4 tiers of benefits. It starts with the cyber supporter that gets access to their own Discord server, early access to content, and of course, they get access to me and our advanced members. And then we go into the advanced memberships like the Cyber Agent, Cyber Guardian, and the Cyber Master. And for each one of those membership tiers, there is a variety of different Python automations that are released every single month. There's exclusive content, exclusive downloads, downloads, like all of the practice questions and practice examinations and the notes for the upcoming Security Plus certification, as well as the live streams that happen every single month. And of course, they get their own Discord servers as well, and a variety of other benefits. So to join Hackaholics Anonymous, you can click the link in the description below. You can go to our homepage and click the join button, or you can simply go to youtube.com/@HankHacksHackers/join, and you'll be able to join Hackaholics Anonymous. Now, without further ado, let us jump into the introduction of the Networking Secure Protocols room. In the last room, we talked about the networking core protocols, and we learned about the protocols that are used to browse the web and access email, and a couple of other protocols as well. And they're really good, but they're not protecting the confidentiality, integrity, or authenticity of the data that's being transferred. And this is very, very important because after all, we're literally talking about cybersecurity on this channel, and everything that TryHackMe does has to do with cybersecurity and pen testing and hacking and so on and so forth. So security is basically the common thread, the through line that has to do with every single thing that we talk about. So obviously, if we're going to talk about networking, the most important thing is security, which is why we're talking about secure protocols. So when we say that confidentiality is not protected, it means that someone watching the packets can read the password or credit card information when sent over HTTP instead of HTTPS. They can access your private documents that are sent via your email. And if you don't protect the integrity of the data, it means that an adversary can change the contents of the transferred data, meaning if you authorize the payment of £100, they can easily change it to another value like 100,000. And then authenticity means ensuring that we are talking with the correct server, not a fake one. So there's so many different versions of the transactions or the communication of a person or a client and a server being intercepted and modified. So when the integrity of something is modified, that means that essentially what can happen is that, not only can I change it to 800 pounds or 100,000 pounds, whatever, I can also change the account that it's going to. And instead of going to the right account, it's going to go to my account, right? So there are so many things. There are so many things that can happen, which is why security is such a big deal, because people don't get robbed at gunpoint. I mean, they probably still do, but they don't really get robbed at gunpoint anymore. What's happening is that they're getting robbed online. And this is just, it's kind of scary and it's terrifying, but it is the current state of the world. So it's very important for consumers in general, as well as security professionals like you or me. And, I don't know if you're watching this for a job or if you're watching this just to get better at security, but whatever the reason is, this is just a common conversation these days. And you just got to get good at networking security, regular information security, so on and so forth. So the transport layer security, which is TLS, is added to existing protocols to protect communication confidentiality, integrity, and authenticity. Consequently, HTTP, POP3, SMTP, and IMAP become HTTPS, POP3S, SMTP-S, and IMAP-S, where the S stands for secure. We will examine these protocols and the benefits that we reaped from TLS. So it's deemed insecure to remotely access a system using Telnet. So Secure Shell was created to provide a secure way for you to access remote systems. For example, SSH is an extensible protocol that offers added security features for other protocols. For example, SCP, which is for secure copying, meaning transferring files back and forth using the Secure Shell protocol. So for this particular room, it would be very beneficial for you if you actually go through the networking concepts and networking essentials video, and of course going through the networking core protocols video as well, just so you have a good, well-rounded foundation before we actually jump into everything that we're doing here. Now, you can actually watch this video and then go back to the other ones, and then everything else in this video will make even more sense for you. So it's totally up to you what you want to do, but by the time that this video actually comes out, all of the other videos are going to be available. So essentially, core protocols will be episode 16, this will be episode 15, and this will be episode 14 of the CySec101 playlist. So feel free to watch it in whatever order you want to watch it. What we're going to learn today is the SSL, Secure Socket Layer, as well as TLS. Then we're going to learn how to secure existing plain text protocols, which is the ones that we just talked about. And then we talk about how SSH replaced the plain text telnet, and then how VPN creates a secure network over an insecure network using encryption. So it's a lot of good stuff that we're going to talk about today, and it's going to be a mixture of lecture versus practical applications in some of the virtual machines that we have. So without further ado, let's jump into the very next task, which is TLS. There was a point in hacking that you would only need a packet capturing tool to read all the chats, emails, and passwords of the users on your network. It was not uncommon for an attacker to set their network card in promiscuous mode, meaning just capture everything, including those that are not destined to it, meaning those that are supposed to actually get to that destination, right? So it captured everything. They would later go through all the packet captures and obtain the login credentials of unsuspecting victims. There was nothing a user could do to prevent their login password from being sent in clear text. Nowadays, it's become uncommon to come across a service that sends login credentials in clear text because there's so much hacking that has happened and so many companies have gotten sued. Down and out, it's become commonplace for most of the, if not everything, most of the transactions, if not all of the transactions, and all of the communications that happen online to actually be encrypted. And this is a very important thing to understand. So as a reference, every time I say transaction, I mean you interacting with a server online. It doesn't necessarily mean that you exchanged payment with something. A transaction could simply be you entered your username and password into a web form and then you were able to log in. That is a transaction online. That's how I refer to it. It could also be considered a communication, a connection, so on and so forth. So in the early 1990s, Netscape Communication recognized the need for secure communication on the World Wide Web. They eventually developed SSL, which is the Secure Sockets Layer, and released SSL 2.0 in 1995 as the first public version of SSL. In 1999, the Internet Engineering Task Force developed the TLS, Transport Layer Security. Although very similar, TLS 1.0 was an upgrade to SSL 3.0 and offered various improved security measures. In 2018, TLS had a significant overhaul of its protocol and 1.3 was released. The purpose is not to remember the exact dates, but to realize the amount of work and time that was put into developing the current version of TLS, which is TLS 1.3. Over more than 2 decades, there have been many things to learn from and improve with every version that has been released. Like SSL, its predecessor, TLS is a cryptographic protocol operating at the OSI model's transport layer, which is why I said watch the other videos first, because the OSI model's transport layer is something that you should already be familiar with. It allows secure communication between a client and a server over an insecure network. By secure, we refer to the confidentiality and integrity. TLS ensures that no one can read or modify the changed data. So take a minute to think about what it would be like to do online shopping, online banking, or even online messaging and email without being able to guarantee the confidentiality and integrity of the network packets. Without TLS, we would be unable to use the internet for many applications that are not part of our daily routine. And this was one of the big things that in the early days of the internet, people were very, very hesitant to buy things from online stores. And then Amazon came around, and now it's like businesses are going out of business. People would much rather buy something online than to go to a physical retail store. Like, are you kidding me? Why would I waste my time to drive to a place and do all these things when I know exactly what I want? So I would much rather just order it from Amazon, order it from somebody's website or Etsy or something like that. And then you can just have it delivered to your door. You know what I mean? As long as you're willing to wait a couple of days, it's not that big of a deal anymore. It's so rare for people to actually go do physical shopping, it's mind-boggling to think about, because I remember the early days of the internet and I remember how hesitant I was. And I was like, I'm not putting my credit card information into this. Are you crazy? So anyways, we've come a very long way. That's basically the point. So nowadays, tens of protocols have received security upgrades with a simple addition of TLS. Examples include HTTP, DNS, MQTT, SIP, yada, 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 which have become HTTPS, DOT, which is DNS over TLS, MQTTS SIPS, where the appended S, of course, stands for secure due to the use of SSL or TLS. So what we're going to talk about is visiting these actual protocols now, which are all the protocols that we viewed in the last video for core protocols. And now we're looking at the secure versions of those protocols. Now, we're not going to talk about the TLS handshake, but if you're curious, you can check out the Network Security Protocols room, which I don't think I have done a video for. Oh no, maybe I have done it. I feel like I have done this video. Maybe I did, maybe I did not. I'm not exactly sure. You can definitely search for it. If I have not done it, then I will most likely have to go and do it. So do me a favor, go do a search, because I do want to I want to keep record time for recording this particular video, because I always go down rabbit holes. So if you can just check the channel and notify me whether or not the Network Security Protocols room, and you will see it from the very intro of the video where I'll show you what, the top of the room, and I'll announce what room that we're in, so on and so forth. So if this video does not exist on the channel, if you could just let me know in the comment section, and I'll guarantee that I'm going to go ahead and record it and make sure that it's available for you guys. So we'll give a general overview of how TLS is set up and used in this video. The first step for every server or client that needs to identify itself is to get a signed TLS certificate. Generally, the server administrator creates a certificate signing request, which is called a CSR, and submits it to a certificate authority. The certificate authority verifies the signing request and issues a digital certificate. Once the signed certificate is received, it can be used to identify the server or the client to others who can confirm the validity of the signature. For a host to confirm the validity of a signed certificate, the certificates of the signing authorities needs to be installed on the host. In the non-digital world, this is similar to recognizing the stamps of various authorities. The screenshot shows the trusted authorities installed in a web browser. So this is what we have: the certificate manager, and then you have your certificates, authentication decisions, and then you have authorities. And these are all the trusted authorities of a web browser. So if I were to go ahead and find this, so let me see where it would be on Google Chrome real quick. Okay, so the easiest way to do this is to go to chrome://certificate-manager/local certs, and then it will bring you to the local certificates page right here. And then you can just click on View Imported Certificates from macOS, and it will show it to you on the web browser here. Or you can do Manage Imported Certificates from macOS, and then it'll actually open it inside of your macOS settings. Now, this is also available for Windows as well. So it's pretty universal. And then you can see what the certificates are that have been imported from your machine into the web browser that can certify you as the user, right? And that is essentially the way that we would do that piece. And in this particular case, you can see all of the certificates for this person on their certificate manager. And this looks like it might be a Linux system. Kind of looks like the certificate manager of Linux. I may be mistaken, so don't quote me on that one. But anyway, generally speaking, getting a certificate signed requires paying an annual fee. So Let's Encrypt allows you to get your certificate signed for free. And this is a service that you have over here. So nonprofit certificate authority providing TLS certificates to 500 million websites. Read all about our nonprofit work this year. And this is, it's very, very important to understand that in case you have a website or in case you have a server that you want to secure with TLS certification, you don't necessarily need to pay hundreds of dollars per year, because certificates can actually be very expensive. So if you actually go, so here's another one. I'm going down rabbit holes, right? So GoDaddy TLS certificates. So if we went over here and then we did SSL TLS certificates for secure websites, and you pull it up on GoDaddy, you can see that, there's the multiple website cleanups, which is $11.99 a month, and then you have $16.99 a month, and then it just goes higher and higher from there depending on the type of certificate that you're requesting. And this is these are the way that they sell it to you. The best plan, perfect for brands and e-commerce websites that need priority support and the fastest malware removal turnaround, and an ideal for websites that want heightened security, including daily backups, DDoS, So this is kind of what it is for I guess I would say this is SSL security. It's not even TLS security, right? So that's what's really, really important to understand, is that even GoDaddy, this like massive service, this massive website, is not even offering TLS certificates. They're offering SSL certificates. And then, as we just established, TLS is much more powerful. It's more secure than SSL is. And so they don't even offer it at GoDaddy. So that's just one of the things that I'm like, okay, well, if you can get it from Let's Encrypt for free, then why not, right? That's kind of the question at hand here. So finally, we should mention that some users opt to create a self-signed certificate. A self-signed certificate cannot prove the server's authenticity, as no third party has confirmed it. So you can actually use a command line tool or a variety of different software to download on your computer and create a self-signed certificate. But because of the fact that no third party has confirmed it, when you try to access the server on a browser, if I try to access your server on my browser, even though you've created a self-signed certificate, it does not necessarily mean that I'm going to get that one. There's like, I don't know if you've ever tried it, but when you try to access a website that doesn't have a verified certificate, there's this warning message that comes from the web browser that says, warning, this is not, this may be a malicious website, or this is not a verified website, proceed at your own risk, or it doesn't even offer you the option to proceed because that website has been listed inside of a variety of malicious databases, so on and so forth. So it's just a very it's a glitchy it's one of those messages that does not inspire confidence. So if somebody's trying to access your server and they get that message, you may be completely valid, right? But if they get that message, they're immediately going to be like, nope, I'm never trusting this name, and that's it. You've lost all of your credibility. So it's worth it to go through a third-party service, because we just found out that there's a free one called Let's Encrypt, and you can do it for free. So what is a protocol named that TLS upgraded and built upon? That would be SSL. And which type of certificate should not be used to confirm the authenticity of a server? So which certificate should not be used to confirm the authenticity? I want to say it's self-signed, probably, right? Self-signed certificates. Maybe that's the answer. The kits like that. Let us move on to the next one, which is HTTPS. We covered this in the networking protocols or core protocols, which is HTTP, the Hypertext Transfer Protocol, which relying on TCP and uses port 80 by default. We also said that we also saw how all HTTP traffic was sent in a clear text for anyone to intercept and monitor. So for example, this is the screenshot from Wireshark, which is a standard open source packet sniffing tool, a network sniffing tool. So if we zoom in on this a little bit, you can see that this is the request that the person sent from their web browser. And then the response from the web browser was all in clear text. So you can see, this is the title, The Art of Espresso, which is the website that we tried to access, and everything was returned back in clear text. There's zero encryption on this traffic sniff. And that's very, very important to understand, because if we sent a username and password into this website, then it's going to, again, clear text, you could see it. Text HTML, you could just see it without having to decrypt anything, which is a very big vulnerability. So if we look at the most common steps before a web browser can request a page, after resolving the domain name to an IP address, the client will carry out the following two steps. It establishes a TCP three-way handshake with the target server, and then it communicates using the HTTP protocol, for example, issuing requests like get the server or get the specific location, which is just the root. That's what that / implies. So the two steps described above are shown in the window below. And this is just a list of packets that you would see inside of Wireshark. So we have this whole section right here, right? So the first portion, which is this piece right here, is the synchronization. Sync was acknowledged, and then the acknowledgement, and it's coming from this place, it's going to the server. The server responds that they have an acknowledgement, and then finally the client says, all right, cool, let's complete our connection. And then there was the actual get HTTP request that was sent right here, and then there was the response that came back, and then just a communication that went back and forth between the client and the server. And then finally, we have the FIN acknowledgement, which is essentially the closing of that connection, right? So This is all captured in plain text. It's captured in clear text, and we can see it right here. Hypertext Transfer Protocol. You can see the request that's being made right here. And I'm pretty sure, well, I thought that they were going to show it, but it says, so the two steps described are shown in the window. The 3 packets for the TCP handshake, which is 1, and then the HTTP communication is marked with 2, and the last 3 displays for TCP connection termination, meaning closing that connection, which is 3. So this is exactly what we just saw right here. HTTP over TLS is now the Hypertext Transfer Protocol secure, and it's basically HTTP over TLS. Consequently, requesting a page over HTTPS will require the following 3 steps. There's the 3-way connection with the target server, establish a TLS session, and then communicate using those exact protocols. So this piece right here is the key piece that encrypts the rest of this interaction. So if we were to look at this now, you can see that you still have the connection, and then you still have the TLS right here, right? So over here we did not have it. It just says HTTP, so on and so forth. Over here, it's now TLS, client, hello, server, hello, so on and so forth. And then the rest of the communication is now being done via TLS, and it is now encrypted. So we have the establishing of the 3 packets marked with 1, then several packets are exchanged to negotiate the TLS protocol marked with 2. Finally, the HTTP application data is exchanged marked with 3. Looking at the screenshot, we can see that the application data, because there is no way to know if it is indeed HTTP or some other protocol over that. So this is what you see: application data, application data, application data. There's literally nothing else that is going to be sent to you because it is now all being done over TLS. So if you try to look at that the way that we did before, this is what it looks like. So compare this to this screenshot that we saw right here, where everything is literally visible and you can read through all of this stuff. And then this one right here is just a bunch of encrypted jargon. You have no idea what's going on. You see that there's TryHackMe.com, and I see that, but that's pretty much it. There's literally nothing else that is legible to the naked eye. And you would have to go through a large series of processes to try to decrypt this, which, unless you're very, very good at decryption, you're probably not going to pull off. So getting the encryption key, adding TLS to HTTP, leads to all the packets being encrypted. We can no longer see the contents of the exchange packets unless we get access to the private key. So you cannot decrypt it unless you have that private key. Although it is improbable that we will have access to the keys for encryption in TLS, we repeated the above screenshots after providing the decryption key to Wireshark. The TCP and TLS handshakes don't change. The main difference starts with the HTTP protocol marked 3. For instance, we can see when the client issues a GET request. So these portions don't actually change. It's just this piece right here that starts to change. And instead of seeing application data, you can now actually see certain data from the actual requests that are being made. So if you want to see the data exchange, now is your chance. It is still regular HTTP traffic hidden from prying eyes. So this is what it looks like right here, except now it's been decrypted and it's not a bunch of jargon, hexadecimal or binary or ASCII type of coding, right? The key takeaway is that the TLS offered security for HTTP without requiring any changes to the lower or higher protocols. In other words, TCP and IP were not modified, while HTTP was sent over TLS the way it would be sent over TCP. So TLS offered security without requiring any changes in the lower or higher layer protocols. Basically, they were not modified. While HTTP was sent over the TLS, it would be sent over TCP normally. It's just now it's been encrypted. That's basically all it's doing for you. So how many packets did the TLS negotiation and establishment take in the Wireshark HTTPS screenshot above? So we have this right here. So we have 1, 2, 3, 4, and 5 packets. So that is the answer right there. And then what is the, what? An establishment connection and establishment take. So what does the hint say here? It says you need to count the packets to establish TCP and the packets to negotiate the TLS. Oh, I see. So it's 5 plus 3 because the original are 3. So that would be 8. So 8, not 83. Okay, 8. There we go. 8 is the answer. What is the number of packets that contain the get login when accessing the website over HTTPS? So get login, the number of packets. So this is not the one. This is the one right here where we're trying to get login over HTTPS. I want to say that's the one, right? So if we check the decrypted screenshot after they actually use the decryption key, we can see right here that they're trying to get the get login, and then the number of packets would actually be here somewhere. So let me just find that real quick here. Oh, I see. They want the actual packet number, the number of the packet. I thought I had to get a count of the number of packets. So it's packet number 10 right here. So frame 10, packet number 10. So that is the one. I want to say it's actually 10, right? There we go. It is 10. The entire time I'm like, where's the count? I thought I was supposed to count the number of packets, but it's not a count. We just need to get the packet number. Okay, great. So let us move on to SMTPS, POP3, and IMAPs, which is all around sending email. So changing these protocols, so SMTP, POP3, and IMAP, is no different than adding TLS to HTTP. And then what happens is that every single one just ends up getting the S appended at the end of it. So SMTPS, POP3S, IMAP-S. And so these are the insecure versions of these protocols. So HTTP is port 80, SMTP is 25, POP3 is 110, and IMAP is 143. And then these are the secure versions. So HTTPS is 443, SMTP-S is 465 and 587, POP3S is 995, and IMAP-S is 993. So as you can see, they have default port numbers that are very, very different than the insecure versions of those same exact protocols. So TLS can be added to many other protocols. Their reasoning and advantages would be exactly the same. And so if you capture the network traffic, which of the following protocols can you extract login credentials from? SMTPS, POP3S, or IMAP. And obviously, if it has the S at the end of it, that means it's been encrypted. So you can't do that. So IMAP would be the only response that you can actually extract login credentials from because it is not encrypted. So that's a very, very quick one, very, very easy one. So let's talk about SSH now, Secure Shell. We have used the Telnet protocol in Networking Concepts Room, or the Networking Concepts video, so you can go find that. I think it's not the last episode, but the episode before this one. So I think episode 15, I believe, or not even episode 15. I think it is episode, yeah, or episode 14. It's basically the very first one that has to do with networking. Although it is very convenient to log in and administer a remote system, it's very risky when all the traffic is sent in clear text. It's easy for anyone monitoring the network to get a hold of your login credentials and then just use them when you use Telnet. So this problem necessitated, that's a good word. This problem necessitated a solution. Tatu Yolen. I hope I pronounced that right. I feel like I killed that last name. But Tatu developed this secure shell protocol and released SSH1 in 1995 as freeware. Thank God for Tatu. Interestingly, it was the same year that Netscape Communications released the SSL 2.0 protocol. A more secure version, SSH2, was defined in 96, 1999. OpenBSD developers released OpenSSH, an open source implementation of SSH. Nowadays, when you use an SSH client, it is most likely based on the OpenSSH libraries and secure code. It offers several benefits, and these are just a few of them. So there's secure authentication. So besides password-based authentication, it supports public key and two-factor authentication. OpenSSH provides end-to-end encryption, protecting against eavesdropping. It notifies you of new server keys to protect against man-in-the-middle attacks. Integrity, in addition to protecting the confidentiality of the exchange data, cryptography also protects the integrity of the traffic. SSH can create a secure tunnel to route other protocols through. This setup leads to a VPN-like connection. And finally, if you can connect to a Unix-like system with a graphical user interface, SSH allows you to use the graphical application over the network. And these are just a few of the benefits. So you would issue the command SSH username at hostname to connect to the server. If the username is the same as your logged in username, you only need SSH hostname. Then you will be asked for a password. However, if public key authentication is used, you'll be logged in immediately. This requires that the key is actually inside of your configuration file that stores all of your keys. So this is not something that can just be done willy-nilly. You actually have to set up the key authentication and the configurations, and then you'll be able to just log in immediately. The screenshot below shows an example of running Wireshark on a remote Kali Linux system. The argument -X is used or is required to support running graphical interfaces. For example, SSH and then -X to connect to a graphical interface. And so we can see this over here in the background right here. You see that the SSH request -X is to connect to a graphical interface, and then they're actually connected, and now they can run their IPAS, so on and so forth. So all of these things are actually available, but then you can run Wireshark immediately, and it just opens up Wireshark in the graphical user interface inside of your window. So even though you are technically connected via the SSH inside of a command line terminal, you are now inside of that system, the Kali system. And if you just run Wireshark at the bottom right here, it just opens up Wireshark in the graphical interface. So it's very, very useful if the system, the remote system that you're connecting to, actually supports graphical user interfaces. It's very useful to actually run the -X so that you can connect and open up a graphic interface. So while the Telnet server listens on port 23, the SSH server listens on port 22, and that is something to also keep in mind. So what is the name of the open source implementation? And that would be Open SSH for open source SSH. And now we can actually run our very first exercise for SFTP for the Secure File Transfer Protocol, and FTPS, which is File Transfer Protocol Secured, basically the same thing. SFTP stands for the SSH File Transfer Protocol and allows secure file transfer. It is part of the SSH protocol suite and shares the same port number, which is port 22. If enabled in the OpenSSH server configuration, you can connect using a command such as SFTP username. Once logged in, you can issue commands such as the get file name and then put file name to download and upload files respectively. Generally speaking, SFTP commands are Unix-like and can differ from FTP commands. SFTP should not be confused with FTPS. And so my bad for calling them the same thing. You are right to think that FTPS stands for File Transfer Protocol Secure. How is FTPS secured? You are correct to estimate that it is secured using TLS, just like HTTPS. While FTP uses port 21, FTPS uses port 990. It requires a certificate setup, and it can be tricky to allow over strict firewalls as it uses separate connections for control and data transfer. Setting up an SFTP server is as easy as enabling an option within the OpenSSH server like HTTPS, SMTPS, POP3S, yada, yada, yada. The other protocols that rely on TLS for security, FTPS requires a proper TLS certificate to run securely. So we're going to click on the View Site button to access the related site and follow the instructions to obtain the flag. And this requires that I zoom out of this thing finally. And so let's actually do the View Site so we can see what's going on the side right here. So let's go. Matching clear text protocol to secure protocol. So we've learned that every protocol uses a default port number and a secure version uses a default port number. And what we're going to do is we need to match the clear text protocol's default port number with the secure protocol's default port number. So for example, HTTP is on port 80 and HTTPS is on port 443. So we would match 80 to 443. So let's try and see what we can find here. And I have not memorized this, okay? So just giving you a quick heads up here. And it seems like I can't zoom out of this thing, which is actually very inconvenient. So let me see what I can do to get the zoomed out version of this, this piece so I can kind of remind myself of the notes here. All right, so here we go. We only get 3 attempts to do this thing. So let's first match all the ones that we know for sure. So I know that 80 matches to 443, so I know that's good. I know that port 21, which is, no, port 23, which is Telnet, matches to port 22. I know FTP is on port 21. And so we do have the little screenshot here that kind of helps. No, not this one. There is one right here, I think. There we go. So we do have some of these things that make it a little bit easier for us. So POP3 is on 110 and POP3S is on 995. So 110 will go to 995. HTTP I already did. SMTP is on 25. So SMTPS would be on 465 or 587. So 25 will either go to 465 or 587. And it's right here, which leaves us with IMAP, which is on 143, and IMAP S connects to 993, so that will go up here. And then finally, we have FTP, which is port 21, which connects to FTPS, which is on 990. And there we go, just like that. we got the thing. So just to let you know, right? So I am not a whiz at remembering numbers. I just know how to find information. And for networking and things like this, if you see open ports when you run a scan and you want to verify what it is, there is nothing wrong with pulling up a cheat sheet so that you can find out what you're looking at. For the most part, I don't know of anyone that is that good with numbers that they have memorized exactly the thousands of port numbers and what they're assigned to. I don't know anybody. I personally don't. I'm sure people like that exist. I know they exist. It's just that I personally don't know anyone. So I can't imagine that it's like commonplace. So, just don't be afraid to use cheat sheets and to find the different port numbers and all these things to kind of make your life easier. It doesn't matter if you memorize these things. What's important is that you know where to find the information to be fully functional and competent at the job that is expected of you. So that being said, we can now move on to VPN, the virtual private network. All right, this is a very important concept because it's actually very commonplace for people to use VPNs these days for a variety of different reasons. So consider a company with offices in different geolocations. Can this company connect all of its offices and sites to main branch so that any device can access shared resources as if physically located in the main branch? The answer is yes. The most economical solution would be setting up a VPN, virtual private network, using the internet infrastructure. The focus here is the V for virtual in VPN. When the internet was designed, the TCP/IP protocol suite, focused on delivering packets. For example, if a router gets out of service, the routing protocols can adapt and pick a different route to send their packets. If a packet was not acknowledged, TCP has built-in mechanisms to detect this situation and resend the packet. However, no mechanisms are in place to ensure that all the data leaving or entering a computer is protected from disclosure and alteration. A popular solution was the setup of a VPN connection. The focus here is on the P for private. So the focus in this situation to actually get access to the same branch as if you were physically there, that would be V for virtual. The focus here for the connection and making sure that everything, all the data leaving or entering is protected from disclosure or alteration is the P for private. And then finally, all companies are requiring a private information exchange in their virtual network. So a VPN provides a very convenient and relatively inexpensive solution. The main requirements are internet connectivity and a VPN server and client. The network diagram here shows an example of a company with two remote branches connecting to the main branch. A VPN client is in the remote branches is expected to connect to the VPN server in the main branch. In this case, the VPN client will encrypt the traffic and pass it to the main branch via the connection in the VPN tunnel. And then the VPN traffic is limited to the blue lines. The green lines would carry the encrypted VPN traffic. So you can see that you have the blue lines right here, which are representing the VPN traffic. And then you have each one of these sections, which is an individual network. And this little blue Apple cloud right here, if this cloud that we have represents our VPN connection, right? So we have, again, so a VPN client in the remote branch is expected to the VPN server in the main branch. In this case, the VPN client will encrypt the traffic via the traffic and shown in blue. So this is it right here. And then the traffic is limited to the blue lines. The green lines would carry the traffic encrypted wise, or decrypted, excuse me. They would carry the decrypted VPN traffic. So as we go, my goodness, I hate it when this happens. So as we look at this, so you have these traffic lines, right? So the traffic could come from this location, and then it would come from this location, and it's going to the VPN server. And then from here, it's being sent to the router for this location, and the router sends it to the main VPN server or the main branch, and then it goes through the firewall. On all of these green lines that we see here is the decrypted version of these blue lines, these traffic requests that are happening. So OpenVPN is one of the most common and one of the most popular VPN services. And even TryHackMe uses OpenVPN for you to be able to connect your own computer to the TryHackMe servers and then get access to the virtual machines and run all of the exercises. So in the program below, in the diagram below, we see 2 remote users using VPN clients to connect to the VPN server in the main branch. In this case, the VPN client connects a single device. So, and this is what we see right here. In this case above right here, we see that the networks are connecting to the main branch. In this particular case, you just see that a single user is connecting through the VPN server for the main branch. So this is their router. This gray circle that we see here is the router of this person. So they're going from their laptop, they're getting their Wi-Fi through the router, they're sending their request through their router, the router sends the request to the VPN service, and the VPN service encrypts that data, and then it sends it to this. And technically, all of this is actually encrypted because it's going through the VPN service. So the VPN service is the middleman. It's the middle ground that makes sure that everything is encrypted, including the requests that are being made, and then when they finally get access to the main branch. So once the tunnel is established, all the internet traffic will usually be routed over the VPN connection via the VPN tunnel. Consequently, when we try to access an internet service or application, they will not see our public IP address, but the VPN server's IP address. This is why some internet users connect over VPN to circumvent geographical restrictions. Furthermore, the local ISP will only see encrypted traffic, which limits the ability to censor internet access. So this is actually something that a lot of my relatives in Iran use the VPN for, because Iran's internet service providers and the government in Iran has strict restrictions for Iran being able to access Instagram or just a general web browser so they can connect to other countries because of a variety of different reasons. They don't want the people that live in Iran to be able to access the outside world. So in order for that to take place, my relatives get a VPN service. The VPN service gives them an external IP address. So it's not the IP address that's being used inside of Iran. It's not an Iran IP address. It is the IP address that is outside of Iran. And then from there, now they're able to access Instagram, for example, and they can send me messages, so on and so forth. So this is actually very, very important. And there are services like Netflix that have certain content that is only available to certain locations for a variety of similar reasons. And for that purpose, you would need to connect to a VPN service that accesses Netflix from a country that has permission to access that data, to access that content, those movies and shows. And then now they can actually watch those movies and shows, even though they're physically inside of a restricted area. And then they're using VPNs to access data from outside of the country, which makes me wonder why these countries even do this, because it's so commonplace nowadays to actually use a VPN server. So if a user connects to a VPN server in Japan, they will appear to the servers they access as if they are actually in Japan. These servers will customize their experience accordingly, such as redirecting them to the Japanese version of the service. The screenshot shows the Google search page for connecting via Japan. And you can see everything's been translated to Japanese, right? So instead of seeing, I mean, Gmail is still technically in English, Google is still in English, but everything else is the Japanese lettering and the Japanese alphabet. So it's the connection that we have here, sudo OpenVPN, and connecting to whatever the location is via the Japanese OpenVPN. And again, OpenVPN is one of the most common VPN services because it's free and it still allows you to do a lot of the things that you would be able to do through a free VPN or a paid VPN service. So in many scenarios, one would establish a VPN connection to route all the traffic over the VPN tunnel. Some VPN connections don't do this. The VPN server may be configured to give you access to a private network, but not to route your traffic. Furthermore, some VPN servers leak your actual IP address, although they are expected to route all your traffic over the private network. Depending on why you are using a VPN connection, you might need to run a few more tests like the DNS leak test to verify that you're not being leaked. Finally, some countries consider using VPNs illegal and even punishable, for example, Iran. Please check the local laws and regulations before using VPNs, especially while traveling. So, you know, fair warning, depending on where you're watching this, because I know we have, I think at this point, we have probably over 50 countries that access the information on this channel. And I am inside of the United States, so there aren't that many restrictions. I don't think there are any restrictions that are enforced upon me that are, for example, in Iran or in countries that just have really strict governments. So if you're watching this from a different country, that has very, very strict laws, please keep in mind that you need to navigate everything according to the laws of your country, because I really don't want you to get caught and then be imprisoned or punished or fined or whatever. I really don't want that to happen. So please keep this in mind. Regulations and compliance and these types of environments are very, very different in different countries, and the general concepts are the same, but the specific rules as to what you can do with these concepts can change based on the country that you're using. So what would you use to connect the various company sites so that a user at a remote office can do this? And obviously the answer is VPN, because that's all we've been talking about for this particular task. So closing notes, and then I think we actually have a virtual machine that we're supposed to be accessing as well. So let's run that. In this room, we covered 3 main approaches to secure network traffic. The first one was to use TLS, which secures many protocols like HTTP and POP3, so on and so forth. And they're usually given an S at the very end of it for secure added to the name. So for example, SMTPS and POP3S. The second approach to secure traffic is to use Secure Shell. Although Secure Shell is mainly used for remote access, it can also transfer files securely and establish secure tunnels. Creating the SSH tunnel is a solid choice if you want to pass the traffic of a plain text protocol such as VNC. Now, the last approach was to use the VPN connection, a virtual private network connection, to secure the traffic. And its connection is usually the perfect option for connecting 2 company branches, or maybe a country that wants to connect to the services of another country. So what we're going to do is we're going to go through a hands-on challenge right now. And I've already started this virtual machine. And the task is basically that the browser has been logged into the TLS keys, so we can take a closer look at the traffic using Wireshark. This logging was achieved by adding an extra option to the browser shortcut, executing Chromium SSL key log file, and then giving the location of the log file, dumps the TLS keys to the SSL key log file. The packet capture is called randychromium.pcap and is saved in the documents folder. When you open the packet capture in Wireshark, you can configure Wireshark to use the SSL key log, so you can get all the TLS traffic decrypted. You can see 5 steps to achieve this in the 2 screenshots below. And then this is what we're going to do right here so that we can actually get that. And then once we do that, we are going to get the content of the login credentials from the PCAP file and the password so that we can actually get our answer right here. So first and foremost, let me actually load the server that we have, or the virtual machine that we have. And then from this, we need to be able to, the application, let's see, the application made power manager has stopped. Okay. We can just close this out. I don't want to send anything in this regard. And it seems to be that my browser is a little bit glitchy for my virtual machine. So I'm just going to open up in a full screen mode right here so that we actually have this. Oh, it's still the terminal. It's kind of weird. It's a little bit glitchy, but okay, whatever. So, all right. So the first thing that we need to do is to be able to execute Chromium SSL keylog to get the SSL keylog file. So let me just verify whether or not I even have that inside of my system right here. So let's see. All right, so the first thing that I did was I just ran a basic find search command, and it is find, and the / represents that we want to search this entire machine. So it's just a root and everything inside of the root. And then the F represents a file that I'm searching for, excuse me. And then the dash name would be that I'm searching for it by name. And then this is the actual file that I'm searching for. And then when you do to_dev null, or when you do to greater than dev null, whatever, it takes all of the error messages and the permission denied messages, and it just sends them to the dev null folder, so that you basically just see a successful result if there is any. Now in this particular case, thankfully, it is actually here. So we're going to go to the documents, and there is our SSL keylog, and then there's Randy's Chromium PCAP file. So we actually have that. I don't need to download it. And I guess I could have downloaded it by running Chromium SSL keylog, yada, yada, yada. So that has actually been done for me, and I also have the Chromium PCAP file. So now the next thing that I got to do is actually open up the PCAP file, and what's going to happen is that it's going to hopefully just open it up with Wireshark, so I don't have to worry about just opening it randomly. So I'm just going to open up Wireshark as such, and it will open up the software for me. And then from there, I will just locate the PCAP file because we know exactly where it is. And then we will go ahead and use our specific key. So there we go. And then there it is. It just immediately takes me to the Randy Chromium. So I just did file open, and then it opens this up for me, and it allows me to search that. And I'm going to click open right here, and it'll open the PCAP file for me like this. So the next command is to go to to click on any of these things. It seems to be that they right clicked on just one of the packets, and then went to protocol preferences, transport layer security, and open the transport layer security preferences. So I will click on any of these things and go to protocol preferences, transport layer security, and then open the security preferences. And then over here, we should have, I don't know if I need to be on packet 366 specifically, but we're going to go to browse and then choose our key and then click OK. So we're going to do browse, and we're going to choose our key log, and then we're going to do open and then click OK. And yeah, everything got decrypted. Okay, so now the question here is, one of the packets contains login credentials. What password did the user submit? So the key here, if you don't know how to use Wireshark, is we can actually search for the contents of all of these files by certain keywords. So all of these packets, we can actually search for them by certain keywords. And one of the easiest ways is to do Control F, and it actually brings up this little pop down here, drop down for you. And then you can click on display filter, and then you can search for string. So that's one of the keys that I'm going to do. I'm just going to type in login and then see what shows up for the keyword login. And let's see what we can find here. So it says 365. It's packet 365 seems to have the post login request. So I can now open this packet by just double clicking it. And then now we can just look for the strings, the data that is inside of it, and see what we can find. Okay, so packet number 365 is the packet that actually has the post login request, and then the it's being from the 148 IP address 192.148 ending, and this is the private IP address, and it's trying to access Facebook. And then we have another one that is also trying to access Facebook again. And in this particular case, we can check 366 because that's actually what the hint for this question gave us. And we can now go into the contents of this packet to try to pull some data. And so we have HTML form encoded application URL form encoded. If we do a breakdown here, we can see that there we go. So you have the email field, the password field, login, so on and so forth. And of course, there's the flag that we're looking for, which is inside of the password field. And then let me see if I can copy this value. So let's see what we can do here. And we can copy value, so that should be fine. And let's go here and paste it, and there we go, submit. And that is it. We are officially done with this particular room. So what I'm going to do is I'm going to just kind of give you a quick little rundown of exactly what I did to be able to grab this information. So number one, everything was located inside of the documents folder. And the first thing that I had to do was essentially just open up the PCAP file using Wireshark. And you can either, so let's go here. You can either click this button right here for Wireshark, or you can just go to the command line and type in Wireshark, then press enter, and Wireshark will open up. And then when you do that, you click on File and Open, and it takes you to the browser. And then from here, the File Explorer, you can click the actual PCAP file that you want to open, which is the PCAP file for Randy Chromium. And then once we did that, you can go and right-click any of these things and then go to Protocol Preferences right down here. And then you go to Transport Layer Security and then open the Transport Layer Security Preferences. And then you'll see this window. And from here, it's already going to be on TLS selected on that. So we need the master key log file name portion. You're going to click Browse, and then you're going to click, choose the SSL key log, and then come here and press enter or press OK. Once you do that, everything is automatically going to be decrypted, and you get essentially the contents here. Now, the first thing that I did was I just searched for login, and it brought me to packet 365. And I searched through packet 365 and I couldn't find anything. And one of the stuff that the hint gave us right here was that just check for packet 366, which is the very next packet. But if you look at packet 366, there's something over here that is actually very, very useful to us, which is the form URL encoded. So you can actually search for that. So you can search for form, and it will probably bring up a bunch of things that have the word form in it. So if I did that, so form, press enter, and it will bring me packet 24. And then because it has application form URL encoded, that's one of them. And then that may actually have something else in it too. So if we actually open that up and go over form URL encoded, we can see form item key value. These things are empty. So that's definitely not what we're looking for. And then you can just click find one more time, and it'll take you to the very next packet, which is packet 366, because that's the only other one in this traffic that we've captured inside of this PCAP file. That's the only other one that actually has the form URL encoded in there. And if we know that somebody's submitting a username and password, we can be sure that they're submitting it inside of a form, which means that we can actually go and capture that data. And now we can go and analyze that data. So we have HTML form URL encoded, and then this was like this. Originally, it wasn't opened up. So then you just open this up, and then you go look at it. And for each one of these things, so there is the LSD, and then email. So that's the guy's email, and then pass, which is the password. And there's the password that we were looking for. So that is how we were able to find that flag ultimately, which is the answer for our very, very last question. And just like that, we are wrapped with this room. So I'm going to give you a couple of final notes here, and then we'll go into the next video. All right, so if you found this video useful, and if you want to get more videos along this CySec101 pathway, I do encourage you to like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out. And there's a lot of videos that come out. For example, there's going to be a Security Plus series that's going to come out. But for the most part, as far as TryHackMe is concerned, I'm going to be focusing on wrapping up and finishing up the CySec101 training series. And in that, you can come to the channel and you can literally search for whatever it is that you may be trying to find by just going through the content, and then you can even just click on this little search button right here and then search for something by name. So there's a lot of different ways, and there's a lot of different, there's over 240 videos that are on this channel now, and by the time that you see this, I think there's going to be a couple more that are going to come out as well. So there's a lot of stuff. So definitely make sure you like, subscribe, turn on the notification bell, and then drop a comment if you have any questions. I am very responsive in the comment section. I check the comment section multiple times a day. And I don't know how frequently I'll be able to do this because my actual work life is now becoming a little bit busier as well, thankfully, because there is now opportunities that are presenting themselves as my studies of cybersecurity got bigger, and I just kind of kept pursuing this pathway. So this is something that I think will be I'm still going to be very, very active in the comment section. I will still respond to you in the comment section. I just may not have the opportunity to check the comment section multiple times a day. So take advantage of this opportunity while you can, and drop your questions and drop your comments. And what happens is that if it's a really good question, then instead of replying in the comment section, I'll actually just create a video in response to your question, which is why this whole CySec101 series came out, because of Darnell Knight's comment for introductory content on cybersecurity. So thank Darnell Knight. If you haven't done so already, just give him a quick little shout out inside of the comment section here. And that's basically it, right? So like, subscribe, turn on notification bell, drop a comment so that you actually get notified the next time that a video comes out, and then you get all your questions answered. And then there's the Hackaholics Anonymous membership community, which is the premier YouTube community for cybersecurity professionals and hackers. And there are 4 levels of membership. We have the cyber supporter, we have the cyber agent, cyber guardian, and of course the cyber master. And for each one of those levels, there is a variety of perks that are available. So everybody gets a Discord channel, starting from the cyber supporter to the cyber master. And then in the Discord channels, even as a supporter, you'll get access to me and all of our advanced members. But as you go further along the advanced memberships, you'll get access to Python downloads, exclusive content, exclusive downloads, for example, the notes, as well as the practice questions and practice examinations for the Security Plus content that's going to be coming out. And there's, live streams that happen. There is a lot of stuff that I give away as a part of the membership of Hackaholics Anonymous. So it's very near and dear to my heart, and I really hope to actually get to see you inside of our Discord community. And to be able to access it, you can use the link in the description below, or you can go to our channel and then click on the join button, or you can simply go to youtube.com/@HankHacksHackers/join, and you'll be able to join Hackaholics Anonymous. So if I don't see you in the comment section, I really hope to see you in the Discord chats, and in either case, I really hope that you found this video useful. It's your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker/protector. If no one else loves you, Hank loves you. Happy New Year, because the New Year is right around the corner. Love, peace, and chicken grease, and I'll see you in the next video later. In episode 18 of the CySec101 series, we are going to go through Wireshark, the basics of the Wireshark tool, and this is a part of the networking module of the Cybersecurity 101 pathway of TryHackMe. And so far we have done the primary 4 rooms, so networking concepts, essentials, core protocols, and secure protocols. And today we're going to go through the basics of Wireshark. In the next episode, we're going to go through the basics of TCP dump, and then the basics of Nmap in the following episode after that. And this is all a part of the networking module of the Cybersecurity 101 pathway. So it's going to be a good one. I think you're going to get a lot of value out of it. And let's jump into it. This episode is brought to you by the Hackaholics Anonymous membership community, which is the premier YouTube community for security professionals and hackers. And as a member of the community, you will get access to 4 tiers of memberships and 4 tiers of perks. It starts with the Cyber Supporter, goes to the Cyber Agent, Cyber Guardian, as well as the Cyber Master. And the Cyber Supporter is our beginner group, and you get access for a Discord community, which gives you access to me and access to all of our advanced members as well. You'll get early access to content and a few other cool perks. And then you get access to the advanced memberships, which is the Cyber Agent all the way to the Master, which gives you Python automations every single month. You get access to your own Discord servers, as well as exclusive content, exclusive downloads, and of course live streams with me. And some of the exclusive downloads would actually be the Security Plus training that's coming up, and the practice questions, the notes, as well as the practice examinations that comes with that. So there's a lot of perks available for people of all levels. And if you wanted to join, you can join through the link in the description below. You can join through our main YouTube channel and just click the join button, or you can just go to youtube.com/@HankHacksHackers/join, and you'll be taken to our join page. Now, without further ado, let us jump into the Wireshark basics room. Wireshark is an open source tool, and it's cross-platforming and works on every operating system. And it's a packet analyzer, so it's a network packet analyzer tool that's capable of sniffing, which is used for ethical hacking and pen testing, and also investigating live traffic, as well as investigating packet capture files, which are known as PCAP files. And it's commonly used as one of the best packet analysis tools because it's open source, and it's kind of an industry standard. A lot of people use it because it's very functional and it has a graphic interface. And then there's also a command line version of it, which is called T-Shark. Now in this room, we're going to look at the basics of Wireshark, and we're going to use it to perform some fundamental packet analysis functions. I've already started our virtual machine, which will give us access to it. And then we're going to use this, if you wanted to actually do it via SSH or RDP, you actually don't need to, because it literally provides this split screen view as soon as you click the start machine button. Now, what's interesting is that this is unfortunately only available to subscribers that can actually deploy virtual machines here. So you would need a paid membership, but the paid membership, literally there's a discount link in the description below that'll take it from $12 to $5. So it's like, it's already inexpensive, but when you use the discount link, it even becomes more accessible to everybody. So that's one of the cool things about it. But if you don't have a TryHackMe paid membership, you can just download Wireshark. It's open source, it's free to download, and then you can use it to analyze some sample PCAPs and things like that, and just go through the motions the way that I'm going to go through them. There's going to be 2 capture files that we're going to use in this exercise. There's the HTTP1 PCAP to simulate the actions shown in the screenshots that we're going to see later on, and then we're going to obviously need the exercise PCAP to answer the questions at the very end of this. So the very first question is which file is used to simulate the screenshots, which is the http1.pcap. And then we have the which one is used to answer the questions, which is the exercise PCAP. So those are the 2 questions for our introduction here. So let's actually jump into the overview of the Wireshark tool. There are a lot of cool use cases for Wireshark. It is the most potent traffic analyzer tool available in the wild, as it says. And these are some of the main use cases. So detecting and troubleshooting network problems like a network load failure point and congestion in your network. You can also detect security anomalies such as rogue hosts that may be on your network or abnormal port usage and suspicious traffic that's happening. You can also investigate and learn protocols and the details of those protocols, like the response codes and payloads that may be attached to any given transaction or conversation that is done via your network ports. It's not an intrusion detection system, so keep that in mind. It only allows you to discover and investigate packets in depth. It doesn't modify packets, it reads them. So modifying packets is a completely different tool. For example, Burp Suite could be one of those things. Therefore, detecting any anomaly or network problem highly relies on the analyst's knowledge and investigation skills. So this is very important for us to understand. This is strictly an analysis tool, and it relies heavily on your abilities and your knowledge as the security analyst and the investigator. Now, we have the GUI and the data that is associated with Wireshark in general. So GUI, if you don't know, is the graphical user interface. And so this is kind of the term or the acronym that's used for everything. So Microsoft Windows, for example, has a GUI. What you're seeing right now is a GUI. It's a graphical user interface. It's not a command line. So a terminal would be a command line tool. Wireshark has a GUI, and then the command line version of Wireshark is called T-Shark. Now, it allows you to investigate the traffic in multiple ways. We have 5 sections that stand out at first glance, which is the toolbar, the display filter bar, recent files, capture filter interfaces, and status bar. So this is actually something that shows up when you open Wireshark. And we also actually have a screenshot down here as well. So this is our toolbar at the top right here, very similar to the toolbar of any other software or tool that you've used. It has the file, edit, view, so on and so forth. Then there's the display filter, which is right here, that you can embed or type out your filters to actually, or not necessarily your filter, I guess it could be called a filter, or your parameters, your arguments to filter the packets. You would use this section to create your display filters. And then we have our recent files that would be on the very, very homepage right here. So welcome to T-Shark or welcome to Wireshark. And then this is the most recent file that was opened up. This is the section that allows you to capture, filter, and available sniffing. Capture filter and available sniffing interfaces. I'm like, what? That doesn't even make sense. So this is actually the capture filter that you see right here, that you can say what type of filtering you want to put upon your capture. And then down here is the interfaces that you can monitor and start capturing traffic from. And then what you will do once you've selected it, you would click this shark fin kind of up here, and it starts sniffing traffic. So for the purposes of this exercise, we're actually going to be looking at PCAP files, but you can actually do a live capture of data as we learned before. And at the very bottom right here, you have the status bar that shows you where you are in the status of this thing. And then once you've actually loaded the packets, you will see the number of packets always at the bottom. And then when you start filtering through the packets up here, the number will adjust down here to show you how many packets are associated with the display filter that you've generated up there. And this is exactly what we can see right here on the right-hand side. So we have the overall view of this whole thing. And then from, we have the toolbar, we have the display filter, we have the recent files, which are the ones that we're going to be using. And then we have the capture portion, as well as the status bar at the bottom right here. So all exactly the same as we saw in the screenshot. Now, when we load a PCAP file, this is what it looks like. So you have the packet list right here, and then at the bottom in the status bar, we can see that there's 43 packets at the bottom right here. So we can see that right there, and there's 43 that's displayed, and that's very important to understand because there's no display filter that's been assigned here. But if you do use a display filter, then you'll have 43 packets, and then it'll say, okay, 12 are displayed, so on and so forth. And then you have the packet file name, which is HTTP1, which is also available at the top right here, HTTP1 cap file. So this is generally what it looks like when you load the packet. And then we have the coloring of the packets, which is actually an interesting little feature that makes it very useful in my opinion. So there's the color packets that show you in order of different conditions and the protocol to spot anomalies in protocols and captures quickly. This split explains why most everything is green in the given screenshots, because they're healthy packets. This glance-at packet information can help track down exactly what you're looking for during analysis. You can create custom color rules to spot events of interest by using display filters, and we will cover them in the next room, in the next portion. I guess this is for the Wireshark basics. So technically we are inside of the networking module, but there's a series of rooms for Wireshark, and I believe they're referring to that room, which is the next room in the Wireshark series. If you're interested in that, there's actually a series of videos on Wireshark that I've done. I'm doing this specific review of this particular room from the perspective of Cybersecurity 101, and I'm gonna do a more detailed breakdown of this compared to what we saw in the original recording of this particular room. So if you've been a part of this channel for a while, you may already recognize this room and the contents of this room, but what they're referring to in the next room is the next room in the Wireshark series. And if you want to watch that, you can go ahead and find that by just searching for Wireshark inside of the channel's video content. So Wireshark has two types of packet coloring methods: temporary rules that are only available during a program session, and permanent rules that are saved under the preferences file profile and available for the next program session. You can use the right-click menu or view coloring rules menu. And this is interesting because I think I'm looking at the THM, the TryHackMe window in the dark mode, so we can't really see this part right here, but you can use the right-click menu or view coloring rules menu to create permanent coloring rules. The colorize packet list menu activates or deactivates the coloring rules, and then temporary packet coloring is done with the right-click menu or view conversation filter menu, which is covered in task 5 of this room. So we'll talk about that in a little bit. So these are the default permanent coloring methods that we see right here. So the ones in black right here, so let me see if we can go in a little bit. So the ones in black right here, you can see that this is bad TCP, and then it goes to the filter itself, which would be a bad TCP filter. So you have TCP.analysis flags and the TCP analysis window update. For example, you have the HSRP state change, you have spanning tree topology change, OSPF state change, and of course ICMP errors. So as you can kind of imagine, these are associated with errors, packets that have to do with errors. You have this light yellow right here, which is for the address resolution protocol packets. We have the pink, which is for pings, so ICMP packets that are relevant to the ping protocol or the ICMP protocol. Then you have the TCP reset, SCTP abort, TTL low or unexpected, and these are a little bit of concern. So these red packets are typically of concern. When you see a TCP reset packet, there should be something to kind of address or look into a little bit further. You have checksum errors, and these are available in black as well. So again, goes back to the concept of errors, but it's been organized with the red right here, which means that it is another one of those of note things. So basically anything that's in black or in red, typically I'm like, okay, we need to look at this a little bit further. If it's in the lighter colors, it's not that big of a deal. So server message block packets or HTTP packets, routing packets, TCP or UDP, so on and so forth. These things are the default packets, the permanent coloring rules that are assigned with it, and then you can modify them as you need to. But for the most part, this is what it kind of resembles, is that if you see black or red packets, it should be of note. You should look at it further depending on the exercise that you're doing or the goal that you have. A lot of your answers may actually be in there, but then there's a lot of stuff that's also in just regular packets that you tend to not worry about because of the coloring, but a lot of times your attacker, the person that's attacking your network, may be clever, and they may be resourceful enough to know that, hey, this is what the coloring in Wireshark is like, so I need to do my activities in a way that these color codes don't apply to them. So it doesn't mean that only pay attention to the black and red packets. It just means that those are usually the ones that you would look at first. They're the kind of a little bit more of note, a little bit more critical, and then you still analyze the rest of your traffic. And then you need to use the various display filters and the various tools that are available within Fireshark to find the answers that you're looking for. So traffic sniffing in this particular case is the blue button that we mentioned earlier to actually start capturing network traffic. The red button, as the stop kind of implies, will stop sniffing traffic, and the green button will restart if you wanted to restart the sniffing process. The status bar will also provide the used sniffing interface and the number of collected packets. So we can see this right here. So this is looking at the ENS5 interface right here. That is live capture and process. And then we have the number of packets. In this case, there's 5,041, and then displayed are 5,041 packets. If we wanted to read PCAP files, which are basically packet files, this is what we're looking at over here. And these are the screenshots that we're going to be using for reading of the PCAP file, which is the HTTP1 file that we're going to look at. So you can go into this by just doing use of the file merge menu to merge a PCAP with the processed one. When you choose the second file, Wireshark will show the total number of packets in the selected file. Once you click open, it will merge the existing PCAP with the chosen one and create a new PCAP. Note that you need to save the merged PCAP file before you can actually start working on it. And so you can actually merge two PCAP files if you wanted to, and it would be done under the file merge menu, as you can see right here. And then this will be step number 2, where you select the second PCAP file. It'll show you how many 483 data records, which means that there are 483 packets with this one. And then you click on that, you click open, and the final step would be that you can see now the merged PCAP file has been renamed. So we can see right here, this is the original, this is the second one, and now this is the final one, which has been the merged file and has 526 versus this one just having 443, excuse me. So this one has 43 combined with the 483 will give us 526 packets in total. So if you wanted to look at the file details, then there's a lot of different ways to actually look at file details. So we're just going to look at this particular one. So knowing the file details is helpful, especially when working with multiple PCAP files. Sometimes you will need to know and recall the file details. For example, the hash of the file, the capture time, capture file comments, interface, and statistics to identify the file, classify, and prioritize it. So you can view the details by following the statistics capture file properties or by clicking the PCAP icon located at the left bottom of the window. So if we click on statistics and go to capture file properties, it will open this up for us, or you can just click that little button right there and it'll still do the same thing and it'll give you the file properties. So we have the file name, length, the SHA-256 hash value, the RIPE MD160, the SHA-1, and then you have the format of it, of where it technically came from. I guess it came from TCP dump potentially. The encapsulation was for the Ethernet, and then we have the snapshot length, and then you have the time that this thing was captured, and then the hardware. In this case, it's not known. The interface is also unknown, with the exemption of this link type, which is our Ethernet, and then just some general statistics. So the number of packets, the time span that it took to actually capture those packets, the average packets per second, average packet size, the number of bytes, and average bytes, so on and so forth. So a lot of these things are very, very tedious details, but if you are really doing a very deep dive in your investigation, a lot of this stuff will actually be useful to you. So the average time, for example, that it would be to capture a packet per second. So if you're getting very low packets per second, it means that it's a slow network, right? If you're getting a really high amount of packets per second, it could mean that it's a quick network, a fast network connection, or it could mean that you're under a DDoS attack, a distributed denial of service, and somebody's flooding your network with a bunch of packets. That could be one of the reasons. So there's a lot of different things that can actually be resolved, or a lot of things that you can find if you're looking for specific details. More often than not, you're not looking for those types of details. More often than not, you're looking for a specific IP address or something inside of these packets that you can search for to find. But sometimes you may actually need to look at details like this to try to get more file details for yourself. So what we're going to use is the exercise PCAP file to answer the following questions. So for example, the file comments, the total number of packets, and the SHA-256 hash value of the capture file. So now that I'm here, I'm just going to click on this, double click on that exercise PCAP. and it's going to open it up for me. It takes a couple of seconds, as you can see from the status bar down here. And then you can see also the number of files, the number of packets that are being generated. So the first thing that I can just pull is that the number of packets here is 58,620. And that was actually it right here. So 58,620 is the answer right there. So the next question is the capture file comments. So we can go to statistics, capture file properties, and then from here, it'll open up this window right here, or we can just go all the way at the bottom right here, click on that little button, and it'll still open up the same exact thing for you. And just to kind of zoom in so you know what I clicked on, it's this thing, it's like a little notepad with a pencil. That's the thing I clicked on. So I'm going to click on that, and it'll open up the capture file properties for me. And I'm looking for the comments. So the comments is literally down here. There's a bunch of comments right here. And at the very, very bottom of the comment, there's the flag that says TryHackMe Wireshark demo. And that is the flag that we're looking for here. So this is the capture file comments. It's at the very bottom of this data, the capture file properties. And then finally, we want the SHA-256, which is actually in that same thing that I just closed out. So SHA-256 value is right here. That's the SHA-256 value. So you can highlight this. Let's see if we can do it like that, and right click on it and copy it. And then you would be able to export or paste that into the question right here. So far, so good. We've been able to get all the information that we need, and we learned some cool things about the Wireshark interface. So now let's look at the dissecting of packets. So packet dissection. Packet dissection is also known as protocol dissection, which investigates packet details by decoding the available protocols and fields. Wireshark supports a long list of protocols for dissection, and you can also write your own dissection scripts. You can find more details on that here, which is on the documentation for Wireshark that is on GitHub. That's available for us here. So it is the boundary / Wireshark. I don't know why I can't zoom in for, there we go. So boundary / Wireshark, which is at the very, very top right here. If I zoom in here for you, we can see that it is boundary / Wireshark and then blob master doc . So that's where you can find it. But essentially, if you just go to boundary / Wireshark, you can find this readme file over here, which is very, very useful if you really want a lot of data, especially for packet dissection and writing your own scripts. Now, this section covers the Wireshark using OSI layers, which you should already be familiar with, because we did talk about the OSI, the 7 layers of the OSI model, to break down packets and how to use these layers for analysis. It's expected that you already have background knowledge of OSI because we've covered it in the previous video, so you should be very much familiar with it. So here's what we can do with the packet details, or essentially kind of like a surface level view of this. So you can click on a packet, and in the packet list pane, open the details, and then double clicking it will just open it in a new window. A packet consists of 5 to 7 layers based on the OSI model and essentially the contents of the packet. We're going to go over all of them in the HTTP packet from a sample capture, and this will show the packet number 27. So you can see right here that we have clicked on packet number 27 here. And let's get kind of a good view. Hopefully you can see all of this stuff. I'll zoom in as needed. So we can see there are 3 locations that we have this red box around, right? So the first one is just the clicking of the packet. So that's what it is. So we click on packet 27, and automatically at the bottom right here, we can see some sections. So we have frame number 27. So this is the very, very first section, and then you can expand that clicking on that arrow. Then we have the Ethernet layer, the IP layer, the transmission layer, and then we have some reassembled TCP segments, and then you have the HTTP layer, and then you have the line-based text data. So we're looking at an HTTP packet just based on the hypertext transfer protocol portion that we see here. And then we can obviously see the IPv4, the source IP address that you see right here, the destination IP address, a lot of these things. And then you can also see that in this line item right here. So this would be the source IP address. This is the destination IP address. You can see that it's an HTTP packet. And then you can see that this was, what is it, the length of it, the 214 kilobytes, I believe. And then these are just some general info about it, which means that it was a successful request. So a 200 response code means that it's a successful request. And then there's some text and HTML inside of it that if you wanted to expand these sections, you would be able to see some of that data. Now this, on this side right here, we can see the hexadecimal and binary equivalents of this thing. This is the hexadecimal on the side right here. And this, from what I understand, is binary on the side right here, but it doesn't it doesn't look like binary. So let's say actually what we get from the description, from the explanations here. So we'll go over this. Okay, very good. And so we can see here, so let me zoom out a little bit and let me make sure that we actually have the details as we need. So each time you click a detail, it will highlight the corresponding part in the packet bytes pane. So this is the packet bytes pane. So I guess those are bytes, not necessarily binary. Let's have a closer view of the details pane. So if we look at the Hypertext Transfer Protocol, HTTP, we can see 7 distinct layers. So frame, packet, source, which is the MAC address, the source IP, protocol, protocol errors, application protocol, application data. Below, we'll go over the layers in more detail. So the frame, meaning frame number 27, the packet number 27 that we got. So the very, very first one, which is frame number 27, you just open this thing up, and then this is a bunch of data that you see inside of it. Now, inside of this, you can, we're not going to get too much explanation on this, but essentially it's going to say that you're looking at the frame packet that you're looking at and the details specific to the physical layer of the OSI model, which is layer number 1. So physical layer will give you, for example, the Ethernet data or the Ethernet, the fact that it's an Ethernet type. The physical layer, if you can remember from the OSI model, we're looking at things like the wiring and, for example, the actual Ethernet connection or maybe the Wi-Fi that was used for this particular packet capture. So the frame number, frame length, capture length, the frame is marked, no it's not. The frame is ignored, no it's not. The protocols in the frame are Ethernet type, IP, TCP, HTTP, yada yada yada, so on and so forth. This is like the most general data, the most generic data of this. And the one piece that's important or of note would be that it's on TCP port 80 and is HTTP as well as HTTP2 that we can kind of designate to this particular packet. The next one is going to be the source MAC layer. So now we're going into layer number 2, which is going to be our data link layer, right? And so in this, we get to see the source and destination MAC addresses, where you can see this right here. So this is a MAC address that you can see right here. And then you have the destination MAC address, which in this particular case seems to be a Xerox machine, that this is the destination MAC address for it, right? Then we have the layer 3, which is the IP protocol, the internet protocol, also known as the network protocol. So the network protocol will give us the source IP address as well as the destination IP address. We also get to see these are IPv4, so you can see Internet Protocol version 4. So these are the IPv4 addresses that we see right here. And then we have the TCP protocol as well. We have some checksum that has not been verified in this particular case, and then at the bottom it gives us a specific source and destination for protocols as well. And this is essentially general information as well, unless you break down these flags, and then you can kind of see the types of flags that are included in this, which is beyond the scope of this particular video. But for the most part, on layer number 3 is where you would get to see the source and destination IPv4 addresses, and this is all from the network layer of the OSI model. So if you remember, we do the physical, please do not throw sausage pizza away. So you have P for physical, D for data link, N for network, right, the network layer. Throw would be transport layer. So layer 4 is the details of the protocol, either UDP or TCP, and source destination ports. This is from the transport layer of the OSI model. So please do not throw, meaning the transport layer. So transmission protocol, the source number, which is source port 80, destination port 3371. We also get some other data about this thing, the sequence numbers as well, the flags that are also attached to this as well, which is a push and an acknowledgement flag that's attached to this. We can also see further sequence and acknowledgement and then timestamps, and then the payload that seems to be something attached to this, which is 160 bytes, or it could just be the payload of the actual data packet itself, the data itself that's being transferred. So transmission control is for transport. So of course it'll have data about the payload, whatever the data was that's being transported, right? So layer 4. And then protocol errors, this continuation of the 4th layer shows specific segments from the TCP that needed to be reassembled. So this one is actually just a continuation from the previous one. So we have 2 reassembled TCP segments, and then we can see that right here. Frame 26 is a part of this, and then we're on frame 27 right now. And then the segment count is 2. So this is these are a continuation. They're connected to each other. Frame numbers 26 and 27 are connected to each other. So frame 26 payload is from 0 to 1429, so for 1430 bytes, and then this one goes from 1430 to 1589, which is 160 bytes. So these two are combined. They're part of the same communication, essentially. And then we have the application layer, or the application protocol, which is layer 5 in this case. And this will be under the session. So this will show, it's technically from the application layer of the OSI model protocol, but if you wanted to look at layer 5, if you look at the actual OSI model, layer 5 is not application. Layer 7 is application. Layer 5 is technically session, but then when you look at the TCP IP model, layer 5, 6, and 7 are all put under the application layer. So that's kind of what they're explaining over here. But this will show details specific to the protocol used, such as the HTTP, FTP, SMB from the application layer of the OSI model. And in this particular case, we're looking at the hypertext transfer protocol, which is HTTP. So let's see if we can kind of zoom in on this a little bit more. So we have HTTP, we have the actual link, so Google ad services.com, page ads, so on and so forth. What else do we got? The content type here, the date that's associated with it, the request in the frame. So the request for this particular frame is frame 18. So for frame 27, the request for this data is in frame 18. The URI is the page at googlesyndication.com, and then file data in this particular case. So you have all of that. And then you have the application data, so the extension of the 5th layer to showing us specific application data, which kind of breaks down a little bit. I don't think it's a part of this. I think it was the very last portion of the packet itself. So line-based text data, and then we have the header. So this is actual the HTML header, and then the truncated data that's inside of it. So you can get a good amount of information from individual packets if you know what you're looking for, right? And then if you know how to also read these things. So if you wanted to see the request for this particular frame, you can go to frame 18 and then see the type of request, whatever the user actually sent out for the server to return this data to them. So now that we understand what a general packet is composed of, let's look at various application protocols and their specific details. So using the exercise PCAP file, we're going to look at packet number 38, which markup language is used under the HTTP protocol. So let's actually go look at packet number 38, and we can just go here, and there it is, number 38. You can open that up, and then under the hypertext transfer protocol, they're looking at the markup language. It's actually right here. It's actually at the it's right underneath it. You don't even need to expand this. It's extensible markup language. So they're looking for which type of markup language is actually used, and that is the extensible markup language. Now it says, what is the arrival date of the packet? So the answer format, and that what we're looking for is under the arrival date information. I think it would be under our transmission control details. So let's see if we can find the arrival date for this. It was actually under the hypertext transfer protocol section. And then right there you see date is May 13th, 2004. So this is the date of the packet right here. So that was the date that it arrived, so to speak. And so we can see that right here. So May 13, 2004 is the month, day, and the year. So that was actually found inside of the HTTP, the Hypertext Transfer Protocol section. So if you do that right there, this is the one that if we kind of broke it down or expanded this particular section, this is where it is. The date is right there. So the next one is, what is the TTL value, the time to live value? And the time to live value, I feel like is also here. So let me make sure that it actually, let me make sure it is before I tell you it is, right? No, that was in Internet Protocol version 4. That's in this section. And we see it right here, time to live. And that is 47. So that would be the value right here, TTL value, time to live. And then finally, what is the TCP payload size? So that should actually be, I remember that it was inside transmission control protocol. So if we go here, we should see it at the bottom with the payload. So payload is 424 bytes. TCP payload 424, which is the answer right here. And okay, so the E tag value. So that's the final thing that we need to look at. So let's get the E tag value, and the E tag value is also under the hypertext transfer protocol portion, and we can see that right here. That's the E tag value, and this one you can just right click and then copy, and then go to copy value, and then it'll copy everything that's inside of these quotations for you right here, and then that will be the answer that you get right there. So far so good. Now that we've gone through the dissection of the packet, let's start doing some navigation. So packet navigation. Wireshark will calculate the number of investigated packets, and it'll assign a unique number for each packet. This helps you process big captures and make it a little bit easier to go back to a specific point of an event, right? So we can see it right here. So you have the packet numbers 10 all the way to whatever, and then when you click on it, it actually gives you the frame number. The frame number is essentially the packet number that you see right here. And then at the very bottom of this, or not here, but if we look at the bottom of this piece right here, we can see the number, the total number of packets, so 58,620. So if I actually go all the way down to the bottom of this file, we'll see that we have 58,620 as our very last packet number. So that's how this thing is organized for us. And this is obviously from beginning to end of this particular capture. So packet 1 would be the beginning of the capture, packet 58,620 would be the end of the capture. Now, let's say let's say you have like millions of packets, right? So if you have a bunch of packets, you need to be able to go to an individual packet. And the way that you can do that is by using the option go to packet, right? Which is also, you can do it with Control G right here. So you just go to go and then go to packet, and then it'll open up a new little toolbar right here for you. And then you just type in the number of the packet that you want to go to, and it'll take you to that packet. So not only do they help count the total number of packets or make it easier to find and investigate specific packets, this feature not only navigates between packets up and down, it also provides in-frame packet tracking, and we can do go to specific packets like we just did right here. So apart from the packet number, Wireshark can help find packets by the packet content. And then we can use this by edit find packet to make a search inside the packets for a particular event of interest. This helps analysts and administrators to find specific intrusion patterns or failure traces. There are two crucial points in this. The first is knowing the input type. The functionality accepts 4 inputs, which is the display filter, hexadecimal value, string, and regex, regular expressions. String and regex searches are the most commonly used to search as search types. Their searches are case sensitive, but you can set the case sensitivity in your search by clicking the radio button for don't be case sensitive, basically. The second point is choosing the search field. You can conduct searches in 3 panes, which is the packet list, the packet details, and the packet bytes. And it's important to know the available information in each pane to find the event of interest. For example, if you try to find information available in the packet details pane and conduct the search in the packet list pane, Wireshark won't find it as if it doesn't even exist, right? Won't find it even if it exists. So you go to edit and find packet. You can also do Control F. So this one is very similar to just the regular find command. And then when you do this, you can see this portion right here that is brought up for you. And then we're looking in packet details. More often than not, you're looking in packet details. And then narrow and wide, I never change this. Case sensitivity, if you leave this off, it won't be case sensitive. It'll just be case insensitive. And then when you look for string, essentially you're just looking for anything, right? So for example, the download keyword right here is going to search through all of the packet details, every part of those layers that we just talked about. It's going to search through all of that for the word download. And then, for example, packet number 4 here, you can see just in the info portion right here that it says get download.html. So this is a HTTP request, it's a GET request, and it's getting the download.html page for us over there. And that's basically it, right? So it's very useful. This is actually very, very useful. I've solved a lot of I was going to say cases, but I've solved a lot of exercises by just going through the HTTP or the search, the find portion, the find function. I read something and I'm like, I've solved it by going through the HTTP. It's like, no, I solved it by using the find function. And then you can see that it gives you the get download, and it even shows you over here, and it actually even shows the download portion right here inside of the hexadecimal bytes portion. So this is the packet list view, this is the packet details view, and this would be the packet bytes view, as you saw over here, right? So there's packet list, packet details, and packet bytes. And for the most part, you always want to be in packet details so that it can search through all of the details here for you, unless you know exactly what you're looking for inside of the bytes. And for the most part, what you'll be doing is, if you're going to do packet bytes, you're going to use regular expressions, You're going to use regular expressions if you're going through packet bytes, because for the most part, you're going to be looking for some kind of a pattern. So we have now looked at how to get, how to find packets, and now we want to learn how to mark packets. So marking packets is another helpful functionality for analysts. You can find or point to a specific packet for further investigation by marking it. It helps analysts point to an event of interest or export particular packets from the capture. You can use the edit or right-click menu to mark or unmark packets. Marked packets will show in the black regardless of the original color representing the connection type. Note that marked packet information is renewed every file session, so marked packets will be lost after you close the captured file. So you can do this, edit, and then mark or unmark, mark all displayed, unmark all displayed, so on and so forth. And mark or unmark all displayed means if you have a displayed filter here, and you see something that has to do with a specific transaction, for example, let's say source IP. You want everything from a given source IP, and then you want to mark all of those packets from that source IP, and then you can go through that. And then once you have these things marked, you can either do, I want to see the next mark or the previous marked packet. And then you can do the same thing by either selecting it or doing a highlight. I think you can actually do a highlight like this too. So like that, yeah, there you go. So if you click on one, hold down the shift button on your keyboard and then click on the next one, it'll highlight everything in that range, and then you can right click and then do, oh, whoops. So I would need to actually do this and then do this. Let me see if I held it down. Nope, that doesn't work. So if I wanted to do this and then this, I would need to actually go to edit. And then from here, I would do mark or unmark packets. And I would do mark right here, Control M. And then it would mark all of these packets for me. And you can see that now they're in black. And then if I do this and then hold shift, do that again, and then do Control M, it'll unmark all of them for me. And there you go. That's what that looks like. So that is how you mark and unmark packets. And then we're going to go into packet comments. So packet marking, commenting is another helpful feature for analysis. So you can add comments for particular packets that will help the further investigation or point out important suspicious points for other layer analysts. So unlike packet marking, the comments can stay within the capture file until the operator removes them. So this is a persistent feature right here. So you can highlight a packet, right click and go to packet comment and add a comment, or you can go to edit and then packet comment and add a comment, and then you can start adding comments to it, and then that will be persistent. So if we go over here and let's go find the packet that they wanted us to look at, which was 38, I believe, right? This is the one that we were supposed to look at, and I think that is the one from what I remember. So let's see, 200 info. Let's say that this is the one, okay? We're just gonna assume that this is the one. We're gonna right click on it, and then we're gonna go packet comment, and then there we go. And then this was for the exercise, and then save that, and there we go. That's our packet comment. And then we can add that here. And if we open this up, somebody can potentially go ahead and look at it, because we have the packet comment at the very, very top right here. And you can break that down. It says this was for the exercise. So packet comments are very easily accessible once you've actually added them to the packet itself. And then we have exporting packets. So capture files can contain thousands of packets. As mentioned earlier, Wireshark is not an ADS, so sometimes it's necessary to separate specific packages from the file and dig deeper to resolve an incident. This functionality helps analysts share the only suspicious packages decided scope. So the packets that you think are relevant to your investigation, basically. So thus redundant information is not included in the analysis process. You can use the file menu to export packets. So export specified packets, and then you can do all packets, or you can do selected packets or marked packets, or you can just do a range between each one, and then you can go ahead and export them, and it'll create a new PCAP file for you that you can use for further investigation. You can also export objects. So you can extract files transferred through the wire. For a security analyst, it's vital to discover shared files and save them for further investigation. Exporting objects are available only for selected protocol streams. For example, DICOM, HTTP, IMF, SMB, and TFTP. So these are actual protocols that can include objects in them. For example, file transfer protocol, that's one of those things, or HTTP. These are types of protocols that can actually include objects, meaning files, right? So you can actually export them. So once you find something that may include a file in it, for example, if we go look at export objects for this given packet, which is 27 and 38, these are the ones that actually only include the packet. So if we go to export objects and go to HTTP right here, let me see if I can zoom in on this. So if we go to export objects and then use the HTTP protocol, it'll automatically show you which packets actually have something in them. And then so packet 27 and packet 38 in this particular case have something in them. And then you can just export the objects from those packets. Then we have time display format. So it lists all the packets as they are captured. So investigating the default flow is not always the best option. By default, Wireshark shows the time in seconds since beginning of capture. So again, the very first packet is the first capture. The very first packet is the start of the capture, and then the last packet would be the end of the capture, and it goes in chronological order in that regard. The common usage is in using the UTC time format, the universal time format, for a better view. You can use the view time display format to change the time display format for your own specific view. So seconds since beginning of capture, time of day since then, automatic from capture file, so on and so forth. So you can change this. The common one seems to be that UTC date and time of day, and it'll give you that information. And the default is seconds since beginning of capture. That's the default when you load it. But if you want to change it to the most common usage, which is UTC, and then you can convert it to your given time zones to make it a little bit more applicable to you. So when you do default time display format, so seconds since capture, that's what you see right here. And when you do the UTC format, notice how it's actually changed. So let's zoom in. This is the time. This is the seconds since the beginning of the capture. That's what you see here. And then this is the actual universal time zone, universal time code that you see right there. So it's very, very different when you actually look at the universal time code versus the time right here. And again, just knowing that this is the seconds since the capture started is very useful. But then if you actually want the time, the exact on the dot time, you can just change it to UTC time display and it'll give you that. Expert info. This is very useful here. So Wireshark detects specific states of protocols to help analysts easily spot possible anomalies and problems. These are only suggestions. There's always a chance of having false positives or false negatives. Expert info can provide a group of categories in 3 different severities. These are the group of categories we hear. So we have severity, so chat, information on the usual workflow, note, notable events like application errors or codes, warnings like unusual error codes or problem statements, and then error, problems like malformed packets. So this is the default right here that we can see over here. And then you can see the colors that are associated with it. Then you have frequently encountered information that are listed in the table that we can see right here. You can refer to the official documentation for more information. So checksum is a checksum error. The group is deprecated and deprecated protocol usage, meaning deprecated has been, I would say, is outdated. I think that's what deprecated kind of stands for. Let's search for Google for a specific thing. Past tense, yeah, deprecated, past tense, deprecated, past participle, express disapproval of, or I guess these are not relevant to us, but for the most part, deprecated would be it's past tense, it's old, right? That's what deprecated is. And then you have the comment, so packet comment detection, malformed packet detection. That's what the group that it falls on. And then you have the group right here. Oh, excuse me. So my apologies, my sincerest apologies. Checksums are not deprecated. Checksum is a group and it shows you a checksum error. Deprecated shows you deprecated protocols. Comment shows you packet comments. Malformed shows you malformed packets. My sincerest apologies. I thought this was all one line. I misread that, and I apologize for that. We can use the lower left bottom section in the status or bar Analyze Export Information menu to view all the available information. In a dialog box, it will show the packet number, summary, group protocol, and total occurrence. So you can click on it, do Analyze Export Information, or you can click on that dot that you see right here, this circle that you see right there, and it'll show that information to you. Both of them will bring you to the export information portion for that given packet that you've selected. I believe it's for the specific packet that we've selected, or maybe I think it's showing us everything for the detailed, for the actual overall capture. So if I do this and do export information, I'll see that there is an error here that is for packet 9100. Yeah, so this is actually showing everything inside of the capture. It's not for any individual packet. When you click on export information, it shows you all the information for the actual capture. So this is packet 9100, this is packet 44573, so on and so forth. These are all the errors that we have here, malformed packets. These are some more malformed packets. These are the warning packets that we see right here. There's a lot of warning packets, as we can see. And then we have note packets, chat packets, and of course comment packets. And this is the one that I added a packet or a comment to. This was 38 that I added a comment to. This one, number 12, says this is not a flag, this is not a flag, this is not a flag. That was the comment that they added to it. So we can see the ones that actually have comments to them as well. So that's what we have for that's it, export info. So that's it. All right, so now we have some questions here. So use the exercise PCAP to answer this. Search for the R4W string, the raw string in packet details. What is the name of artist 1? So we'll go here. We're going to go, or not go. Actually, I'm just going to do this. I'm going to do Control F to make it easier. And then now we have this packet details narrow and wide. We're going to search for the string, and I'm going to go inside of this box and I'm going to do R4W, which is raw basically. And we're going to click find, and let's see what it gives us. And it brings us to packet 33,790. And so it says, what is the name of artist 1? So let's open this up and look at some of the data here. So this is a, what do we see? Port 80, so this is an HTTP packet. Let's close that. Hypertext Transfer Protocol, we have all this information. We need to go within the contents of this to get what they're asking for. So this is what we see right here. So this is the contents, and then we're looking for the first artist, right? The name of the artist 1. So artists right here is the title right here that we go down, and then we can look at the rest of the data. And let's see, artist, this is all textile header, or header. And then let me see if I can find the actual artist 1. All right, so it's a little bit down right here. So where you can see begin content after ending the master header, we can see begin content, and then we come down here and the very first div, which is essentially the table right here that we can see right here. We have the div class story, href artist, php artist 1. And then we can kind of scroll to the right here. And then you can see the H3 value, meaning that everything that's inside of these two little brackets right here, that's the actual content of this. And so it's R4W8173. That is the artist's name. So artist 1 is that right there. And that is the answer that we see right here, R4W8173. So raw for string is what we, or R4W is what we searched for as a string. In this particular portion right here, I just did Control F and then I searched for R4W, and then that's what I was able to find. So go to packet 12 and read the comments. What is the answer? So let's actually do go and then go to packet, and then we're going to go to packet 12 now, and then there it is. And I want the comment, so I'm just going to go right here, packet comments. This is not a flag. This is not a flag. Is there anything at the end of that? No, there's not. Let's scroll down, and there's something at the bottom. I'm sure of it. So if we go down here, too much, let me see, where is it? Okay, so now that we're in the full screen mode right here, it's easier to just kind of make this full screen a little bit. And now you can actually see the packet comment. And so what we have over here is that it says go to packet 39765 and look at the packet details pane. Right click on the JPEG section and X something. And let's see, export packet. And export packet, what, bytes? Export packet bytes, is that what that says? Okay, so 39, I think that's all that we get, right? So 39765, that's all we get. So let's go over here, and then we'll go to packet 39765, right? That's what it was. 39765, go to the packet details, and then look at the JPEG, and then export packet something. So let's go down here and let's find the JPEG. So JPEG file exchange format. You can see this. Oh my gosh. So export packet bytes, I think, is what I'm supposed to be doing. Let me see if there's anything useful for me here. Doesn't seem to be. Export packet. So let's right click on that. Export packet bytes right here. Click on that. And then we got that. So we will save it as whatever, bytes. I'll save it as that. Save it on the desktop. And now we have it here. Open this thing. And let's see. This is the packet bytes. So what am I looking for? What's the answer that what are we looking for? What is the answer? So this looks like the hash value of something. So I'm guessing we're supposed to get the hash value of this. So let me make sure I'm looking at this right here. Packet bytes we have right here. Okay, so the hint doesn't really give us much in this regard. It just says go to the packet comment to view the comment. And then remember, you can also use statistics, capture file properties to view the available comments. So that doesn't give us much. So what we need to do, from what I understand, because it says in the comment, it says export packet bytes, and then I did, and then we got that image. And this image really doesn't give us anything apart from, you know, whatever this random ass, whatever the hell this image is right here. If I click on details, still don't get anything. So we're going to close this. And from what I understand, really the only thing that is left for me, so let's do properties and see if we, yeah, same thing, doesn't give me anything. So what I'm going to do is this. I'm just going to open a terminal. I'm going to I'll do an ls command real quick just to see where we're at. And pwd also shows me where I'm at. I need to go to the desktop to actually see my file, which is right there, the bytes file that we can see right here. So I will do, from what I understand, because the answer that I got, and it's been a very long time since I've done this room, the answer that I got looks like a hash value. So we can kind of do this like SHA-1 sum, and then do the bytes. And then that's what that looks like. We can do MD5 sum and do bytes. That's the MD5. We can also do SHA-256 sum bytes. Come on, there we go. So this is the answer right here, because it's the 911 da 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 da. That's the answer that we got. So it's the MD5 hash value, and you can essentially do whatever the name of the algorithm is, and then just do sum at the end of it. So SHA-1 sum, MD5 sum, SHA-256 sum. And as you can see, they get longer and longer the more complex the hash value is. And so in this particular case, the MD5 is the one that I recognize from the answers. So that is the answer. And that is what we got right here, 911, and it ends with EBF. So the question is kind of confusing. It's a little bit misleading. It's like, what is the answer? And it's like, I don't know. Like you're not asking me specifically what you want me to get for your answer. So I think the last time that I did this, I may have actually read on some documentation to see that they actually wanted us to find the hash value. And then so that's how you pull the hash values of any given file. So the big thing was that it said export the sum, right? Or not export the sum. It said export the bytes. So when you go here and when you click on the actual, the comment that we had on packet 12, it said go to this packet number and then export the bytes. And then when you look at this, you go to the JPEG section, which is what we have right here. And oh, you know what? These are, hold on, dissection is not implemented. These all look like sums too, but these are not the sums. No, these are not the sums that it's looking for. Okay, whatever. Anyways, so it said export the bytes. So we went to the actual JPEG portion of the packet, 39,765. We went to the JPEG portion at the bottom, right click on this thing, export packet bytes, and then it exported it as our JPEG. that we see right here, this JPEG file on the desktop. That's what it exported as, and then you just open up your terminal, go to the desktop, and then run the MD5 sum, and then you'll be able to get that value for yourself. Now, let's see, there is a .txt file inside the capture file. Find the file and read it. What is the alien's name? And so this was part of the export objects portion. So if we go here, export objects, and inside of the capture file, so I'll try the HTTP protocol first, and then we can see that there, my God, these are all exports that we can do. These are objects that we have. Holy cow. So let's do a text field. I'll do a .txt. Okay, this is the only one, no txt. This is the only one that I'm going to do. So I'm going to save this one. And then we'll do Node.txt, and we're going to put it on the desktop as well, and then save that. So just to give you an idea, over here you can actually filter what you want from all of the objects, and literally there are so many freaking objects. There's like thousands of objects inside of this thing. So I obviously don't want to save all of them, so I'm just going to do .txt because they said it's a .txt file. And then we can see that it's packet 4267, and it has the note.txt attached to it. So now that we have that, we can now go and look at the note.txt. And I can simply do it without even having to open it. We can do cat note.txt, and okay. There is that. Let's see. Packet master is the name of the alien that we see right here. Okay, great. So there is that. Packet master would be the name of the alien, which is what we have over here. And then look at the expert info section. What is the number of warnings? So we're going to go here. We're going to open up the Wireshark one more time. And if you remember, expert info is like right down here. It's that that red button right here. Click on that and it'll open up the expert warning. And then we can see right here. So the number of warnings, so I can go all the way to the end, and then we can see that there is 1,636 warnings. The warning is in yellow that you can see right here. So 1636, and that is the answer that we see right there. So that's how we were able to retrieve all of these answers. So now let's go to packet filtering. Wireshark has a powerful filter engine that helps you narrow down the traffic and focus on the event of interest. It has two types of filtering approaches, capture and display filters. Capture filters are used for capturing the traffic and only packets valid for the used filter. Display filters are used for viewing packets valid for the used filter. So we will discuss these filters and the advances in the next room, which would be the next room in the Wireshark series, which I've done a video on. So if you're curious about that, you can just search for Wireshark on the channel homepage and you'll be able to find the video for packet filtering. For now, we're going to look at the basic usage of display filters. We will help you a lot. So filters are specific queries designed for protocols available in Wireshark's protocol reference. While the filters are only an option to investigate the event of interest, there are two ways to filter traffic and remove the noise from the capture file. The first one uses queries, and the second one uses the right-click menu. Wireshark provides a powerful GUI, and there is a golden rule for analysts who don't want to write queries for basic tasks. If you can click on it, you can filter and copy it. So we can actually apply a packet as a filter. It's very, very interesting to think about, or a portion of the packet as a filter. So what they've done here is they've clicked on the source. They've right-clicked on source and then apply as filter and then the selected portion. And then you can see that right here is ip.source equals and then the actual IP address. So each one of these columns that you can see here can be implemented as a filter. So I can click on this, right click on that IP address, the destination address, and apply it as a filter, and then apply the selected as a filter. And then we can see that IP destination has now been changed to this, and I'm only seeing out of the this is the full screen version, so we can go here. I'm only seeing out of the 58,620 addresses or packets, out of the 58,620 packets, I can see that there's 28,984 of them are displayed that all have the destination IP address that we see here, 10.10.57.178. So you can take any portion of these things and apply them as filters. And if you want to wipe it, you can just click on that X, and then it'll remove it, and then everything will adjust again, and you'll be looking at the full list. So that's how you apply something as a filter from any given packet. There's another filter called the conversation filter. So when you use apply as filter, you will filter only a single entity of the packet. This option is a good way of investigating a particular value in packets. However, suppose you want to investigate a specific packet number and all the linked packets by following on IP addresses and port numbers. In that case, the conversation filter helps you view only the related packets and hide the rest of the packets. You can use the right-click menu or analyze conversation filter menu to filter conversation. So again, you would click on something and then you would go to conversation filter, and then you want the TCP conversation, for example, the TCP version of this conversation, and then it modifies it into a really big filter that you can see here. So in this one, the IP address equals 145 da 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 da, and IP address equals this. So these two both have to be present, and the TCP port needs to be 3372 and TCP port equals 80. So it shows you these two IP addresses. So both of these IP addresses have to be present, and both of these ports have to be present. And then all of a sudden you only see the stuff that's relevant to them, meaning that it went from, this is for HTTP 1. So let's actually go look at the one that we have right here. So we'll take this one, and then we'll do conversation filter. We'll do a TCP conversation filter, and then we can see that that has been, that's crazy. It's still 28,000 freaking packets. Jesus. So, but you can see right here. So you can see IP address equals this as well as this. So both of them have to be present, and TCP port equals 80 and 48,924. And still, even all of that considered, we have 58,000 that are total, and then we have displayed 28,000. So I guess those two, this set of data that we see right here is in a lot of freaking packets. So you can colorize the conversation. So it's similar to the conversation filter with one difference. It highlights the linked packets without applying a display filter and decreasing the number of viewed packets. So it'll just highlight them. This option works with the coloring rules option and changes the packet colors without considering the previously applied color rule. You can use right-click menu or view colorized conversation menu to colorize a linked packet in a single click. Note that you can use the view colorized conversation reset colorization to undo this particular operation. So colorize conversation instead of conversation filter, colorize conversation, TCP, and then choose a color, and then you can see that it will colorize every part of it without actually decreasing the number of packets that are displayed. And then you can just go colorize conversation one more time. So view, colorize conversation, and then reset colorization, and it puts it back to normal. Prepare as a filter, very similar to apply as a filter. This will help you create display filters using the right-click menu. However, unlike the previous one, this model doesn't apply the filters after the choice. It adds the required query to the pane and waits for the execution command, which is you just pressing enter, or another chosen filtering option by using the and or from the right-click menu. So it'll actually add it up here, but it won't press enter. And so what you can do is you can then use and after this. So you can say IP source equals this and IP or you know, the destination port equals whatever. So you can combine two queries together. So if we go back to our section here and clear this out, I can do this. I'll right click on that and I'll say prepare as filter, and then we'll prepare that so we can see that the IP address is now here. And so which one was it? 133. And then so we can do protocol, let's see, port. We'll do this. We'll do and, whoops, DST dest port. Is that what it is? How do you do dest to port? DST port equals 80. Is that right? Let me see. I forget the syntax for destination port. So let's look at what this one showed us here. And TCP port, I see. So TCP port is what I'm looking for. So it's not destination port. I'm looking for TCP port. TCP port, there you go. So you can do IP address equals this and TCP port equals 80, and then press enter. now it actually applies that filter, and then there's still 28,000 freaking packets. So that's not, it doesn't really narrow it down a lot, but at the very least you can prepare a specific piece as a filter and then modify that and then press enter, right? So that's the way that would be useful to create filters, by combining two strategies, by doing the right click menu and then typing up your own. And then you can do an apply as column. So the packet list pane provides basic information about each packet. You can use the right click menu or analyze and apply as column to add columns to the packet list. Once you click on a value and apply it as a column, it will be visible in the packet list pane. This function helps analysts examine the appearance of a specific value field across the available packets in the capture file. So you can enable, disable the columns shown in the packet list by clicking on top of the packet list pane. So you go here in the bottom right here, and you can take something, for example, IPv4 as the type. You can right click on that and then do apply as column. And then what happens is that you actually get a new column called IPv4. And then now you can do IPv4, you can do IPv6. As you scroll through it, you can see what type of Ethernet or what type of data packet you're looking at, just based on the fact that you added a type right here. It's a type. And then the field information here is IPv4. So now you can actually look at it via the column stream, right? Or the column view, excuse me. Then we have follow stream. So Wireshark displays everything in packet out portion size. However, it's possible to reconstruct the streams and view the raw traffic as it is presented at the application level. Following the protocol, streams help analysts recreate the application level and application level data and understand the level of interest. It is also possible to view the unencrypted protocol data like username, password, and other transfer data. So you can use right-click menu, analyze, follow TCP, UDP, HTTP stream, and then follow the traffic streams. Streams are shown in separate dialog box. Packets originating from the server are highlighted with blue, and those originating from the client are highlighted with red. We started looking at streams as we were going through the previous video that we did, trying to look at the difference between regular protocols and secure protocols, and what it looks like when you see something. For example, this is not the secure protocol, the encrypted version of something. This is the plain text version of an HTTP packet, because you can actually see this, right? If it was encrypted, this would all be a bunch of jargon, like just a bunch of random characters and letters, which we wouldn't be able to make sense of with the naked eye. So once you follow a stream, Wireshark automatically creates and applies the required filter to view the specific stream. Once a filter is applied, the number of the view packets will change. You will need to use the X button to get rid of the filter, whatever. Okay, so go to the packet number 4. Right-click on the hypertext transfer protocol and apply it as a filter. Now look at the filter pane. What is the filter query? So, I mean, that one is kind of a gimme, but we'll go here. So we'll do go to packet, and then go to packet number 4. And so we're here. And then we're going to right click on this. So this is what we see right here in this section right here. We're going to right click on that, and we're going to apply it as a filter. Select it. Is that's what they said, right? Is it filter or column? Yeah, apply it as a filter. So you apply it as a filter, and then you can see up here. So what is the filter? Is HTTP. So that's what we get right here. So what is the filter query? And we see that here it's HTTP. Now, what is the number of displayed packets? So when you do that, what's the number of displayed packets? And we can see that at the bottom right here, and that is 1,089. So finally, we got down to less than 28,000. Very nice. Okay, so 1,089 is the total number of the displayed packets. Go to packet 33790 and follow the stream. What is the total number of artists? So 33790 and follow the stream. So let's go here. We're going to go to packet 33790, press enter, and then we're going to right click on the packet. We are going to follow right here. So right click, follow TCP stream, and it will open this up for me. And now I need the total number of artists. So we got to go down here and look at the number of artists. So we can see get HTTP response was okay. and then we got that. And then get categories, and response was okay, and it gave me the categories. And then we're going to do get artists. So there we go, get artists, HTTP response was okay. So now I need the number of artists that have been sent to me. And get categories again, and list products, okay. And then show image, okay. And so this is the TCP stream, which seems to be encrypted. So this is not the version that we're looking for here. So we want the 33790. So we're going to go to this one more time. So go to packet 33790, and we got that. And I'm just going to X this out as well. So go to packet 33790, right click one more time, go to follow. And instead of TCP stream, I'm going to do HTTP stream. And this should, there you go. Now actually I can see the content. It was a good way to show you the difference. So the first one that you saw when we went TCP, we saw all of the encrypted data, and none of this stuff was making sense before. It was all basically encryption, right? You couldn't even see any of this data. So none of this stuff was useful for me. So now I can go down to the portion where it says get artists, and we can try to get the artist information. So get artists, there we go. So get artists. Let's kind of zoom in on this for you a little bit. So now we're going to the get artists request here, and the stuff in red is the request that's being made, and in the blue is the response. And so now I need to actually count the number of artists that I can see here. So we will go here, and let me see if I can't filter this, but I can find something. So let me see, we'll just do artist, and then find next, and artist title. Okay, that's great. So let's go to the next one. Artist PHP. Okay, that's great. Artist, okay. Artist 1. So this is artist 1. Next, and next. Artist 2. Next. Artist 3. Next. That's it. So there were 3. There were 3 artists that were listed. So if we come over here, we can see that there are 3 artists that are listed. Very good. Okay, so what is the name of the second artist? So we can go over here one more time, and let me do this follow one more time and look at the HTTP stream. And then we need to just find the artist 2. So I believe it was artist equals 2. I think that's what it was. So do find next, and then we have artist 2 right here. Boom. So artist equals 2, and he's Blade. So BLAD, and then the number 3, and that was this guy right here. So great. And that's it, actually. We are now at the conclusion. So we'll go through this. I'll give you a couple of final notes real quick, and then we are officially wrapped. Okay, so hopefully you found this video useful. If you want to find the other videos on Wireshark, I do recommend that you actually check out the content of the channel. So you can literally go to the channel itself, and you can go to the homepage right here that we see, click on this button, which is this search button right here, and then you can just type in Wireshark, and then you'll be able to find all of the content that's available for Wireshark. And you can see that there's a lot of content that's available for Wireshark, and we've used it in a lot of cases, and then T-Shark, which is the command line version of it. So there's a lot of good stuff for Wireshark. And I think that it would be beneficial to you if you actually looked at it. After a while, it just turns into Brim and these various other tools like Mimikatz and stuff like that. And Mimikatz, I feel like there was something that I did in the tags maybe, and what's happening is that it's showing the tags that are for these videos, and that's why Wireshark is coming up. But the ones that actually have a shark, so this guy that you see, that's a shark right there, that's a shark, that's a shark, that's a shark, there's a shark right here, T-Shark, right? So the ones that have a shark are the ones that have to do with Wireshark. And then you'll definitely be able to find the video that they were referencing when they're like, we're going to look at this in the next video, so on and so forth. That's what they were talking about. So that's how you can find all of the other videos on the channel that have to do with Wireshark. If you would like to get more videos like this one, or if you want to get future videos on the CySec101 training series or the CySec101 playlist that we have over here, I do recommend that you like, subscribe, turn on the notification bell, and of course, drop a comment. I am very much active in the comment section that we have over here, And I love when people reach out, and it means the world to me when I actually hear from you. If you have any questions, I'll respond to your comments or your questions in the comments. If it's a really big question, like what Darnell Knight gave us, and I reference this guy pretty much at every video inside of the CySec101 series, because it was because of him that I was like, okay, we should do an entire playlist on CySec101. And then we went back to the beginning. So that was one of the things that I think is very important to really point out. I really do look at the comments. I look at every comment that comes in. I'm looking at my phone all the time, waiting for new comments to come in, and I respond almost immediately. If it's a quick question, or if you just want to say hi, I'll even respond to you if you want to say hi, if you want to say thanks, whatever, or whatever it is, right? It means the world to me when I hear comments and when I actually get to interact with you guys. But it's also very important so I can answer the questions that you have. So make sure that you like, make sure you subscribe, you turn on notification bell so you actually get notified when a new video comes out. But then at the same time, drop a comment, because I really do want to hear from you. If you just want to say hi, if you want to say thanks, it's all good. If you really want to say thanks, then I encourage you to join the Hackaholics Anonymous community, even if you do it as a supporter level, because the supporter level is essentially you saying thanks for the content. And it starts at $4.99, and even for the supporter level, you'll get access to me in Discord as well as all of our advanced members in Discord. But then if you want to join and really take this seriously, we have the advanced memberships, which is the Cyber Agent, the Cyber Guardian, as well as the Cyber Master, and those guys get exclusive content every single month. They get exclusive downloads, they get Python automations, they get live streams with me. And for example, the Security Plus training series that's going to come out, they'll get all of the documents and the notes as well as the practice questions and practice examinations as a part of their membership with Hackaholics Anonymous. So if you want to join, you can do so in the link in the description below. You can do so by going to our homepage and clicking the join button, or you can simply go to youtube.com/@HankHacksHackers/join, and you'll be able to join. And I really hope that I see you in the comment section. If very, very awesome to be able to hear from you. If not, in the actual Discord chats that we have for Hackaholics Anonymous. It's your boy Hank Hackerson at Hank Hacks Hackers. Love, peace, and chicken grease. If no one else loves you, Hank loves you. I think this might be the last video that I'm going to record in 2024. I have to do some traveling to go see some family in the next couple of days. If I don't get to record any more videos, then I very much love you guys. And yeah, this is literally December 29th, so I might not be able to record anything, but by the time that this comes out, I think it'll actually be scheduled to drop on either the 30th or 31st of December. So I very much love you guys. I appreciate you guys. This community means a lot to me, more than I can articulate for you, and I'm very, very glad that you're here, and I look forward to seeing you in future videos. So if no one else loves you, Hank loves you, and I'll see you in the next video. Peace. In episode 19 of the CySec101 training series, we are going to go through the TCP dump tool, the basics of the TCP dump tool, which is a part of the networking module in the Cybersecurity 101 pathway of TryHackMe. And this is our second to last room to finish up the networking module, and the next one that we have is on Nmap, and then we get to go into cryptography and exploitation and all the other fun stuff. So today we're just going to be jumping into the TCP dump tool. This video has been brought to you by the Hackaholics Anonymous membership community, which is the premier YouTube community for security professionals and hackers. And to get access to a bunch of perks like Python automations, Discord servers, exclusive content, early access to content, exclusive downloads, live streams, and a variety of other things, I do encourage you to check out Hackaholics Anonymous. You can join through the link in the description below, or you can go to our homepage and click that join button, or you can simply go to youtube.com/@HankHacksHackers/join, and then you'll be able to join the community. Now, without further ado, let us jump into the TCP dump room. Okay, so the main challenge when studying networking protocols is that we don't get a chance to see the protocol conversations taking place. Now, conversations is just a back and forth that goes on with various IP addresses and ports and interfaces and so on and so forth. And we refer to those as conversations, us in the nerdy tech community of cybersecurity. So anytime that two different machines, it could be your cell phone or your laptop, it could be a server and somebody's client, which would be their computer. Anytime that there's an interaction that takes place between two different nodes, that is called a conversation. Now, all the technical complexity are hidden behind friendly and elegant user interfaces like what you see right here. This is an actual user interface. But if we went to look at the source, right, if I clicked on inspect right here and actually looked at the source of this page, it is not so friendly because there is so much code out behind the scenes right here that we don't even know what's going on. And this is not even what we're talking about when we're talking about conversations and all the different things that goes on. So there's a lot of stuff going on under the hood, so to speak. And you don't really see all of that because it's all hidden behind beautiful, elegant little user interfaces, right? So you access resources on your local network without ever seeing an ARP query, which is the address resolution protocol. Similarly, you would access internet services for years without seeing a single three-way handshake till you check a networking book or inspect a network traffic capture, which is what TCP dump actually is. And we did Wireshark in the last video, so you got a chance to check that out too. So the best study aid would be capturing network traffic and taking a closer look at the various protocols, and this helps us better understand how networks actually work. Now, this room introduces some basic command line arguments for using TCP dump. The TCP dump tool and its libpcap library are written in C and C++, which are actually relatively easy to wrap your head around. I would say they're not as easy as Python, but they're not as complicated as, I don't know, what can we say? Like maybe JavaScript might be a little bit more complicated than C or C++. So they were released for Unix-like systems in the late 1980s, which is like literally the infancy of computing, or the early 1990s. Consequently, they are very stable and offer optimal speed. The libpcap library is the foundation for various other networking tools today. Moreover, it was ported to MS Windows as WinPcap. Now, the objectives for this room are to capture packets and save them to a file, set filters on captured packets, control how captured packets are displayed, and of course, we're going to be using the wonderful TCP dump tool. The prerequisites are everything basically that we did at the beginning of this module. So there are episodes for every single one of these. So networking concepts, essentials, core protocols, and secure protocols, all of those are already live inside of the CySec101 playlist that is on this channel. So I highly encourage you to check those out if you haven't done so already, because there's some good essentials and core concepts and stuff that you really do need to at least be familiar with, because I don't think we're going to be going into the foundational stuff, the fundamentals in this video. We're more so going to be using the TCP dump tool. So if you don't know them, you probably need to know them. That's why they're called prerequisites. Now, that being said, we actually have our virtual machine that I already clicked on, and it's already started. That's this beautiful black screen that you see on the right. That is not so much an elegant interface. That is just a pure command line interface. It is a Unix system, a Linux system, I should say. It is a Linux system, Ubuntu 20.0.4, This is usually what it looks like when you go like connect to some kind of a server that is inside of a massive environment, and it hosts a bunch of different computers and a bunch of, let's say, web servers and databases and so on and so forth. This is what it looks like. You really don't get a GUI, a graphical user interface. You just get a command line. So at the very least, if you don't know how to run some basic commands on Linux, go check out all of the Linux fundamentals videos that are on the channel. Go check out the Linux Plus videos. It's like a whole playlist that I have for Linux Plus. And then there's, of course, the most popular video that's on this channel, which was, become a kick-ass Linux administrator. That video ended up kind of blowing the channel up. It was like the very first, I guess you could say, viral piece of content for relative to this channel, at least, right? It'll probably ultimately hit 1 million views, but I think it's like over 100-something thousand right now. So that is, that's available if you haven't checked it out, and if you don't know how to use Linux, because I'm not going to be explaining all the stuff that you need to do with Linux either. So first question is here: what is the name of the library that is associated with TCP dump? And that is libpcap. And then we press enter, and that is our answer. And we have officially gotten our first correct answer and finished with the intro. So let's jump into the basic packet capture here. So you can run TCP dump without providing any arguments. So basically just type TCP dump and press enter. But this is only useful to test that you actually have it installed. In any real case scenario, we have to be specific about what we want to listen to, where we want to write the data to, and how to actually display the packets that are going to be captured, right? Specifying the interface would be done with the I flag or the I option. So it would be -I, and then you could say any to capture traffic from any interface, or you could actually choose a specific interface. For example, if we do IPAS, which is essentially the list of IP addresses that would be on our system, we would get a couple that would show up, and then for each one of them there's some kind of a interface as well. So the LO interface is available pretty much on every computer, and that would be the local, aka the loopback interface. By the way, if you hear like buzzing in the background, there's like a massive windstorm that's going on right here, and it's kind of crazy. Like, I don't know if you could actually hear all the wind that's going on outside, but I feel like I'm recording in the middle of a freaking hurricane or something. It's pretty insane. Okay, so yeah, the LO is available on every computer. It's typically the loopback or the local address, and for that the IP address is always going to be 127.0.0.1, and that's for the most part on every machine that I've ran this command on. That exists on every single machine. So this is not what we're trying to really connect to or capture traffic for. What we are interested in is the actual interface. So in this case it's ENS5, and then the IP address for this is 10.10.20.253. And if we go to the top of my screen right here, that's the IP address that's been assigned to me, 10.10.20.253. So that's my temporary IP address for this virtual machine that we're using. So you could do ifconfig. You could also do IP. Oh, I guess ifconfig doesn't. It's not installed on this particular machine, so you cannot do ifconfig on this machine. Typically, you could be able to do ifconfig, and it would still essentially list the same thing that you would see over here. In this case, it would be IP-A-S, which is basically listing the available network interfaces, and it's like an acronym for IP address show, right? So that's basically what we would do. So I could actually do IP address show, and it would give me the same response, right? It's just the acronym version, the shortened version, in case you're lazy like the rest of us inside of the tech community. Believe it or not, tech people and programming people, like, they're actually super lazy. That's why they learn programming, because they want to shorten the process to do things. Anyways, whatever. All right, so now we have our interface, right? So what we want to do is we want to save the captured packets in this case. And you want to use the -w command to write something, right? So the extension is most commonly set to .pcap, which is the packet capture file extension, which is typically what we use with, Wireshark, or really any kind of packet capture file is ending with pcap. So that's how I recognize it, and I feel like everybody else also recognizes it that way. The saved packets can be inspected later using another program like Wireshark, which we did in the last video. You will not see packets scrolling when you use the -w option, because it's being written to the pcap file that you have designated. It won't display onto the screen, which can actually be very useful. So reading the packet capture from a file would be done with the -r. So when you do TCP dump, you can do the -r and then give it the file name, and now you're in read mode, and now you're reading the file. And then you can limit the number of the captured packets by using the -c and then giving it a count. So for example, if you do -c10, it will capture 10 packets, right? Don't resolve the IP address and port numbers. If you don't want to do that, that is done with the -n. And so this is avoid making such DNS lookups. You can actually use the -n argument, which basically means just show me IP addresses. I don't want to know the DNS resolutions or domain name service resolutions. I just want to see IP addresses. That's basically what we're doing here. If you don't want port numbers to resolve, you can use the -nn. Right, so if you don't want to see 80 being resolved to HTTP, you just want to see port 80, right? Then you would do -nn. And then so when you do -nn, it stops both the DNS resolve as well as the port number resolve. So you only see IP addresses, and then you actually see the port number. And then so this is what the command, for example, a combined command would look like. We're using sudo because we want to use admin privileges, root privileges, then TCP dump. We're going to capture it on the ENS5 interface. We want to count to 5, and then we don't want to see the IP addresses resolved to actual DNS, to domain names or host names or anything like that. We just want to see the IP address, and then from there, that's basically it. You just press enter, and then it captured 5 packets, 1, 2, 3, 4, 5. And then it showed us the information. It goes from this IP, it's going to this IP, and then it's going to, it's very interesting. I would say that this is the port number at the very end of it. And then what else do we have that's interesting? So we have, these are a couple of acknowledgments, it seems, the options. Let's see. Yeah, I mean, not much really. Doesn't really show much. It's just saying that there's IP addresses. The same IP address is pinging essentially the next IP address, and it's just acknowledgement packets. It looks like that's sending out, and I may not. Yeah, that's basically it. I don't think I'm missing anything with that, honestly. If you wanted a more verbose output, you could actually do -v. If you wanted very verbose, you would do -vv, and if you very verbose, you would do vvv, and it would give you more verbosity, which I love. That's like a really fun word. And verbose basically displays more on your screen compared to the last thing. To the last command. So I would say the best way to actually display this to you, to actually show this to you, is for me to actually run this. So I will do TCP dump, and I will do it on my ENS5 interface, which is what I got. And then we're going to limit it to 5. And then we're just going to also do the -n just for its and giggles. It says use the sudo password for the user, which is what we had actually over here, which I guess is going to be THM123. And there we go. All right, so we got our packets, and they've been captured. And this is basically what it looks like. The first one is this. It's going from 1010 to NT253 on port 22. It's going to this IP address, and it's going from this one to this one, and then going to this one again to this one, and then from this one to this one, etc. It's just a back and forth between 2 IP addresses, essentially. They're not one per line, so if I actually open this up in a new window, we'll probably see a better view of this. And this actually cleared it up again. So let me see if it saved my command. It didn't. So I will do sudo TCP dump interface ENS5, and then we will do what was it, N, and then we're going to count to 5 packets, and then THM123. And there we go. All right, so this one's a little bit cleaner because now you actually get to see 1 per line, so it's a little bit easier to actually read. So the first 2 are going from the 253.22 to 130 or 1130, and then 1130 is responding to 253.22, and then this one is sending another 2 packets, and that's basically it. Like it's really not much that's happening over here, and we try to see. I mean, I could technically like copy and paste this inside of Gemini and be like, break this down for me line by line. But for the most part, there's nothing interesting inside any of these packets for me to be like, oh, that's what this is. So it's essentially a communication going back and forth, and they look like pings. They look like basic acknowledgement requests or sequence requests, and that's basically it. I cannot find anything that's fascinating in it. Maybe if you're way better at reading these traffic lines than I am, maybe you can drop it in the comments and kind of what is it, enlighten us. That's the word that I was looking for. The thing that I wanted to show you though is if we did verbose at the end of this, right? So if we do -vvv, so I'll do super verbose, right? Press enter, and then we can see that there's per line. Now you can see that there's more stuff coming out per line, right? So I still have actually not before that even starts. The very top of this, TCP dump listening on link time 24 bytes, TCP dump verbose output suppressed, use V for output, listening on and capture size. So just from the top, that's actually different from the previous output that we got. And then we're actually now getting an extra layer of content that's coming out, as well as the IP addresses that are communicating with each other. Now there's a flag, there's a checksum, incorrect, sequence number, acknowledgement. What else do we got? There's clearly more options that are available that have been printed onto the screen. And that's basically what verbose does. It just gives you more of an output, more details for you to analyze, just in case you're really getting off on details, right? Like just in case you really like details. So these are our little cheat sheets for running commands with TCP dump. We have the -I giving us an interface, -W to write it onto a file, -R to read from a file, -C to count it, -N to not resolve the DNS, and then -NN to also not resolve. So the first N is DNS, the second N is the port number, and then -V gives us the verbose output. So looking at these things right here. So on the interface ETH0, counting the 50 or counting up to 50 packets captured and getting a verbose output. And then we have interface WL01 and then writing into the data PCAP file, and then any kind of interface without any domain name resolution or port resolution. These are the potential examples that you could run with TCP dump. Now it says, which option can you add to your command to display addresses only in numeric format? And that would be the -N, because we don't want to resolve the name. If you want to remember it that way, you don't want to resolve a name, you just want the number is what you're interested in. All right, so that was it. We just ran our first couple of TCP dump packet captures, and we did not output them onto a file. I guess I could technically output it onto a file just for giggles, right? So if we write ls, oh, we already have a PCAP file over here, so I can actually do TCP dump, and I can do it in read mode and do traffic.pcap, and then let's see. Oh my God, look at all that! Holy cow! This is what is inside of that oh my gosh, this thing is still going. All right, we're gonna stop. We're gonna stop reading that. Stop reading it. Control C. Okay, very good. Look at all this output. That one freaking PCAP file. Look at all this output. I mean, there's so much that I literally ran out of space and I can't scroll up. That is insane amount of output. We're probably going to use that for an exercise later on to try to capture some data or try to find some data through that massive freaking output file. That was ginormous. All right, anyways, let's now use expressions to filter. So we're going to use probably regular expressions to actually filter the packets that we are going to get. And let's see what we can learn from that. Okay, so you can run TCP dump without providing any filtering expressions. It's not going to be useful. So what you just saw is what we did without any filtering expressions. Just like in a social gathering, you don't try to listen to everyone at the same time. You would rather give your attention to a specific person, or at least a conversation between a couple of people. Considering the number of packets seen by our network card, it is impossible to see everything all at once. We need to be specific and capture what we are interested in inspecting. So if you wanted to filter by host, for example, we could use the host option, right? And this is not a -host, this is just host. So this is what the command looks like: sudo TCP dump host, and then in this case we're actually using the domain name and then doing a write to the PCAP file, right? You could also do this by IP address. So instead of doing domain name, you could basically just do host and then provide the IP address and then write it to the PCAP file. That's exactly what this command is actually displaying for us. And then you can see that example.com in this particular case, it's not showing us what the conversation is between these guys, but for the most part, we can see that maybe if it's ending in the .http, that would be presumed to be example.com's IP address on port 80. That's what HTTP is. And then that's what the conversation looks like. And then can we see anything else over here? No, there's nothing else over here that would give us any kind of a hint that that's example.com. The only thing that I can understand, or the only thing that I can kind of deduce, is that when it ends in the .http, it's assuming, or it's implying that it's sitting on port 80. So we're communicating with this particular IP address on port 80, which is HTTP, which is the communication that you would do with a website. And so that is the implying, right? That's the implication that we're talking to example.com in this conversation. So if you want to limit the packets to choose from a particular source IP address or host name, you must use the source host and then give it the IP, or source host name. And then similarly, you can limit packets to the destination by using DST host IP or the host name. And so you're obviously, this is the abbreviated version of it. So SRC and DST would represent source and destination respectively. You can also do a filter by port. So if you wanted to do a port filter, you would just do port and then give it the filter, right? The number of the port that you actually want to capture. And in this case, the port 53 is our DNS port. It is the default port for DNS. And so sudo TCP dump interface ENS5 on port 53, and then don't resolve by the name, just show me the IP addresses, and now we can see it, right? So this is going with any direction of conversation. So this is the source, it's going to destination on port 53, and then same thing over here. And then now the source is port 53 coming and talking to this same guy right here, and then second line, same thing. And then we have two conversations going on, right? So example.org, and then the response from example.org, I would say, and this one is getting the quad A record as well as the A record, and the A record would represent IPv4, and then quad A would represent IPv6. This is stuff that we talked about when we were going through the networking basics, the fundamentals of it. And so when you send that request of saying, hey, send me your IPv4 and your IPv6, then the IP address for example.com responds to us and says, this is my IPv4 address, and then this is my IPv6 address. And look at that, that's a massive freaking IP address. IPv6, it's just mind-boggling how much longer and more complicated it looks like than IPv4. And that's pretty much it. So that's all we got for this particular packet capture. And so in the example, we captured all the packets from a specific port number, port 53. You can obviously go source port number, and destination port number as well. And then we can now go filter by protocol. So if you wanted to filter by protocol, you could actually do IP, IPv6, or just IP6. You can do UDP, user datagram. You can do TCP, transmission control, or ICMP, which is the Internet Control Messenger Protocol, I want to say. In the example below, we limit our packet capture to ICMP packets, and then there's an echo request and reply that's happening, possible indication that someone is running the ping command. There's also an ICMP time exceeded due to running the traceroute command as explained in Networking Essentials. So this is what it looks like right here. TCP dump on the interface, ICMP is the only protocol that we want to capture, and then we can see the responses right here. So you can actually see that these line items for this traffic capture, and as well as the last one that we did when we were trying to get the A and the quad A records, it actually has a little bit more information for us to be able to analyze. For example, this actually says this is an ICMP echo request, which is essentially another way of saying this is a ping. This is an ICMP echo reply, which is another way of saying that this actually pinged back. And then time exceeded in transit could be technically trace route, which is the calculating the number of hops that something takes to go from its destination to, or from its source to its destination. That's typically what we see when we see time exceeded. Usually if it's down, and if like the server that you're trying to connect to is down and you can't connect to it, you would get either a time exceeded, or the response from ping is something like it couldn't be resolved or something like that. I don't think ping, if ping fails, I don't think it gives you a time exceeded. I think time exceeded is actually specific to traceroute. So that's how they kind of determined that that's what these two packets are, and then these are actual ping requests and replies. But yeah, that's basically it. This is the example to show you that you can use a specific protocol to filter for as you are doing your TCP dump capture. And then we actually have logical operators, which become very, very useful. So you have and, or, and then not. So and combines these two, right? So if we say I want to capture on this host and I want to capture on the TCP protocol, it would do everything that has to do with that host and the TCP, right? So when you use the keyword and, or the operator and, both of these conditions have to be true in order for the response to come, in order for the conversations to be filtered, right? If you did or, and then so you do TCP dump UDP or ICMP, then it will show you anything that has to do with UDP and anything that has to do with ICMP. Instead, if you did UDP and ICMP, which I guess technically won't work because you can only have one protocol, so that won't work. But essentially when you add or, you're filtering for both of these things, and you're going to get a much for the most part, you would get a much larger output than if you just did UDP, for example, right? So when you do or, you're adding both of these to the list, and then you're going to get either one, right? Either or. Show me anything that has to do with either or of those two. And then not means that I don't want to see TCP, right? In this particular case, we're saying show me anything that is not TCP. So anything other than TCP is what I want to see. For example, it could be UDP, ICMP, it could be ARP packets. It could be anything that would come back that is not TCP. As long as it's not TCP, I want to see it. That's basically what we're saying. So these are summaries and commands here. TCP host IP, TCP dump host name, and then we have TCP dump source host or destination host, and then TCP dump port number, source port or destination port, and then we have the TCP dump as well as the protocol, for example, IP or IPv6, ICMP, so on and so forth. Now, these are some examples of combining some of these options together. So we say, show it to me on any interface, and then show me only TCP conversations that have to do with port 22. This is what this whole thing is going to show us. And port 22 has to do with secure shell, because that is the default port for secure shell. And then I want to see everything that is on the WLO interface. I want it to be a UDP protocol, and I want it to be on port 123, port 123, which is the NTP port, so the network time protocol. And that, I think that actually just gives you just the time, like the date and time kind of a thing. Then we have TCP. Don't quote me on this. Let's actually click on it. It'll tell us. It says it's a networking protocol designed to synchronize the clocks of the computer over a network. It uses a designated reference time source such as the atomic or GPS clock to coordinate the system time for all network devices. It ensures that all computers within the network have the same accurate time, which is crucial for various applications, including logging, security, and data integrity. So it does not show you the time. It synchronizes the time. So big mistake right there. I hope you didn't listen to the first part of that sentence and skip. I hope you actually got the explanation for what network time protocol does. And we have TCP dump. This is a much longer command. So we have TCP dump on the ETH0 interface. The host that we're filtering for is example.com. And we want it to be on TCP port 443, meaning HTTPS. And then we wanted to write it to the https.pcap file. So it's going to listen on this interface. It's going to filter for the example.com domain name. And it's going to filter for the TCP protocol on port 443. And then we're going to write everything onto that pcap file. So for the questions from this task, we will read captured from this thing right here, traffic.pcap, that massive file. As mentioned earlier, you can use the -R to read it. Then we're going to read it and then count 5 of the packets because there are just too many damn packets. It should display the first 5 packets in the file without looking up the IP address. Remember, you can count the lines by piping the output via the WC command. In the terminal below, we can see that we have 910 packets with the source IP address set to 192. Please note that adding the N to avoid unnecessary delays in attempting to resolve IP addresses. In the example below, we didn't use sudo as well as reading from the file does not require root privileges. So basically what they did was they read this file, they looked for this source host, and then they did not resolve it, and then they just did word count, and word count just counts the number of lines by default, and so there was a 910 just about this freaking IP address. So obviously it's a massive file. If you're just looking for one IP address and then you have 910 records, yeah, that's a massive file. So questions here. How many packets in traffic PCAP use the ICMP protocol? So this is what we're going to do. We will go here actually, and then we will do TCP dump. Let me see if my keyboard is even working. TCP dump -R and then traffic.pcap. And then what we want to do is ICMP is what we're doing, right? That's it, right? ICMP protocol. and then that's basically it. And then what I'm going to do is I'm going to do the word count, and then I'll actually, hold on, I'll do -n so it doesn't resolve the names, and then we'll do word count, press enter, and then it says 26. So the first number here is, I believe, the number that we're looking for. So we will run 26, and that is indeed the right answer. Beautiful. That's the command that we ran. So just so you know, in case you're trying to find this answer yourself, it is TCP dump -r, and then reading the traffic PCAP file. We're looking for the ICMP protocol. -n would be to not resolve the names, so that it saves us a little bit of computing power. And then using that vertical pipe right there, which it's for my keyboard, it's the button that's right above my enter button. And if you hold down shift and then you press that, you will pipe it, and then you pipe it to the word count, and it counts the number of lines, and then it gives us 26. All right, very good. What is the IP address of the host that asked for the MAC address of 192.168, so on and so forth? So the IP address of the host that asked for the MAC address of this. Now the MAC address is the ARP protocol. So we're going to look for ARP protocol, and then we're going to search for this host, and I think we should be able to find it with that. So let's do this. We'll do TCP dump -r and then traffic.pcap, and then we're going to do ARP because we want the ARP protocol, and then we're going to do the host, and then we're going to do this thing. Let me see if I can copy paste inside of this. That would be very clutch if I could. I could. Very good. Okay. And I think that's it. And I'll just do -n to not resolve anything. Press enter. And then we got 2 ARP requests. That's all we got, which is very useful. Out of that massive file, there's only 2 ARP requests. So it says, who has this IP address? Tell this IP address. So this is the guy that is trying to find out. Can I copy this? Okay, there we go. I think I copied it. So if I go here and paste it, I think that should work, right? Sweet. Nice. Very good. Now, what hostname subdomain appears in the first DNS query? So we're going to filter by DNS as our protocol, and then we're just going to count, because I don't know how many of them there are going to be. So I'm just going to count the top 5. And then we will get the subdomain, hostname subdomain, and I mean that should be it. It's like something.com, I think. So let's see. So if we're going to go back here, and the last one that we ran, I didn't review it with you, but this is the last one that I ran, TCP dump -r. Basically, this part is going to stay the same every time because we're reading from the PCAP file. We looked for the ARP protocol because that's the address resolution protocol that searches for a MAC address. And then we went by the host of this particular host because that's the one that we want to see who's asking for this host. And then I did not resolve the names, so it would only give me IP addresses, and then there was only 2 records that showed up. Now the next one that we want to do is TCP dump, which is going to read again from the traffic.pcap file. In this case, we're going to do DNS, and we're just going to count it to 5, and then that's it, really. I'm just going to press enter, and it says can't parse filter expression, syntax error. Did I do something wrong? What did I do wrong? Let's see. What's the question? What host name appears in the first DNS query? I thought I did it right. Let me see. Okay, so basically another way to do this, which I literally sometimes when I make these mistakes, I'm like, dude, what? It's so simple. We're just going to do port 53 because that's the port for DNS. And I'm just going to count 5. And then let's see what we got. So on port 53, and then what's the question again? What hostname subdomain appears in the first DNS query? So if I go to the hostname subdomain, that shows up in the first DNS query. I believe it's the compute internal.domain. No, actually, it's right here. It's the mirrors.rockylinux.org. So if I just do that, that should have copied it. Sweet. There you go. Just like that. Just like that. Easy money. Easy. All right, cool. All right, we have now filtered expressions. Now let's do some advanced filtering. Ooh. All right, so there are many more ways to filter packets. After all, in any real-life situation, we would need to filter through thousands or even millions of packets. It is indispensable to be able to express the exact packets to display. For example, we can limit the displayed packets to those smaller or larger than a certain length. So greater length filters packets that have a length greater than or equal to the specified length, and then same thing, less than or equal to the specified length. So you can check the PCAP filter manual page by issuing the command man PCAP filter. However, for the purposes of this room, we're going to focus on one advanced option that allows you to filter packets based on the TCP flags. Understanding the TCP flags will make it easy to build on this knowledge and master more advanced filtering techniques. So what do we have? Before proceeding, it's worth visiting binary oh my god. Okay, binary operators, bro. This is, I need to take off this mask off the top of my head just to give my head a little bit of breathing room here. A binary operation works on bits, meaning zeros and ones. An operation takes 1 or 2 bits and then returns 1 bit. Let's explain it more in depth and consider the following 3 binary operations: and, the pipe, and then the exclamation. So ampersand takes 2 bits and returns 0 unless both inputs are 1, as shown in the table below. Okay, my god. So input 1 is 0, input 2 is 0, so inputs 1 and input 2 will end up being 0. Input 1 is 0, input 2 is 1, input 1 and input 2 combined would be 0, and then 1 and 0 would also be 0, and then 1 and 1 will end up being 1. Okay, so the way that I'm processing this, I try to look for patterns. The way that I process it is that if, and I don't know if this is right, okay, so this may be completely wrong, and we're about to find out if I'm right or wrong, but 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. And then 1 times 1 is 1. That's the pattern that I noticed. Now, I don't know if that's actually the correct pattern or the way to read this, but that's basically all I got. Because I know it's not addition. 0 plus 1 would actually be 1. So I know that's not addition. It would be, I would say, multiplication. So now, the pipe. Let's go down here again. So the pipe, or the OR option, I guess. It takes 2 bits and then returns 1. So takes 2 bits, returns 0 unless both inputs are 1. This takes 2 bits and returns 1 unless both inputs are 0. So basically the inverse of this whole thing. So if we do 0 and 0, it's 0. 0 and 1 is 1. 1 and 0 is 1. And then 1 and 1 is 1. This one I have no pattern for. It takes 2 bits and returns 1 unless both inputs are 0. So that's basically the only thing that I can. And then this takes 2 bits and returns 0 unless both inputs are 1. So basically this one, from what I'm understanding, if as long as both of the inputs are 1, that's the only place that you'll get a response of 1. Apart from that, doesn't matter essentially what the inputs are, it will always return 0. That's if you're doing ampersand. If you're doing the pipe or the OR, then it'll take 2 bits and it will return 1 unless both of them are actually 0. So it's literally the opposite of this. So 0 and 0 would end up being 0. Every other option will end up actually giving you 1. And then we have the not, so the exclamation mark. It'll take 1 bit and then it inverts it. And input of 1 will give you a 0, and input of 0 will give you a 1. And this one is basically it. This is like it's a much simpler, it seems to be a much simpler pattern to recognize. Binary, bro. Jeez Louise. All right, okay, very good. Header bytes. The purpose of this section is to be able to filter packets based on the contents of a header byte. Consider the following protocols: the ARP, Ethernet, ICMP, IP, TCP, and UDP. There are just a few networking protocols we have studied. How can we tell TCP-dump to filter packets based on the contents of the protocol header byte? We will not go into the details about the headers of each protocol, as this is beyond the scope of this room. Instead, we will focus on the TCP flags. So using PCAP filter, the TCP dump allows you to refer to the contents of any byte in the header using the following syntax. The proto, and then inside of the square brackets, you would have the expression and then the size. So proto refers to the protocol, for example, whatever the protocol is that you've chosen. And then these all refer to ARP, ICMP, IPv4, and what is it? ARP, excuse me, yeah, so ARP, Ethernet, so ARP, Ethernet, ICMP, IPv4, IPv6, and then TCP, and then UDP respectively. Expression indicates the byte offset, where 0 refers to the first byte, and then size indicates the number of bytes that interest us, which can be 1, 2, or 4. It is optional and is 1 by default. To better understand this, consider the following 2 examples from the PCAP filter manual page. Don't worry if you find it difficult. Okay, so I feel like that was for me. That literally, that piece of instruction was talking to me. They're like, yeah, don't worry about it. If you don't get it, don't worry about it. Don't. I'm gonna try to get it, but if I don't get it, don't worry about it. That's basically what they're telling me right now. Okay, so ether 0 and 1 does not equal 0. So it takes the first byte in the Ethernet header, which starts with 0, right? So that's what they say. So the 0 refers to the first byte. So it takes the first byte in the Ethernet header and the decimal number 1, so and 1, for example, quad 0 and then 0001 in binary, and applies the and, okay, the and binary option. It will return true if the result is not equal to the number. So for example, if this obviously is not equal to this thing. So we're looking at Ethernet byte 1 and I guess the number 1, right? So we're looking at the decimal 1. And then so if it does not equal to 0, then it's going to return true. The purpose of this filter is to show packets sent to a multicast address. A multicast Ethernet address is a particular address that identifies a group of devices intended to receive the same data. IP0, looking at the first byte of the IP, and compares it with the hexadecimal number of F, which in binary is this. It will return true if the result is not equal to the decimal number 5, which is this. I'm like losing my shit. I kind of get it, actually. I kind of get the pattern. It feels like I'm kind of understanding it. So this is the IP protocol, the first byte of the IP protocol, and then we're looking at this is the hexadecimal for the character, for the number F, I guess, then hexadecimal number F, which is this would be the pattern for hexadecimal number F. So if this byte is not equal to that, not equal to 5, which would be this, then it would return true. I think. I don't know if I wrap my head around that well enough. I'm so sorry if I'm not explaining this correctly, because I also am having a tough time wrapping my head around it. So if you're as confused as I am, I guess that's okay, because they said don't worry if it's too difficult or whatever. I don't know why they would do this to us if we shouldn't worry. If it's difficult, it's like, well, why are you doing this to us? Like, it feels like it's torture. Don't worry if you find the above 2 examples complex. We included them so you know what you can achieve with this. However, fully understanding the above examples is not necessary to finish this task. Instead, we will focus on filtering TCP packets based on the set TCP flags. Look at this. This is so much easier. I recognize all of these. So you can use the TCP and then the TCP flag to refer to the TCP flags field. These are the flags that are available. So this is the synchronize, this is the acknowledge, this is the finish, this is the reset, and this is the push. So much easier than this shit right here. Excuse my French. Based on the above, we can write this TCP dump, and then look at this TCP flag. So that's the option, essentially. This is what you would have to declare. And then you say that you want it to equal to the SYN flag. So TCP, and then looking for the TCP flags, that's the pattern that we're choosing. And then from here, we want the pattern to actually equal to the SYN flag. And then TCP dump, again, TCP flags and TCP SYN does not equal to 0, right? So it does not equal the capture TCP flags with at least the SYN synchronize being set. So in this particular case, 0 would be false and then 1 would be true. So with at least the SYN is being set, that is what this means, is that it's not 0, meaning it is 1. That's what I'm concluding from that. And then TCP flags and TCP SYN and TCP acknowledge are not 0, meaning at least the SYN and acknowledge are set. So that would be the way that we can filter using these advanced filtering options. Okay, so now let's see if we can actually get the answers to these. How many packets have only the TCP reset flag set? So I'm actually going to use this thing so I can use the examples that we have on the right side over here. So we want, we're going to do TCP dump, and then I'm guessing we're reading the packet, right? So TCP dump r traffic.pcap. I think that's what we're supposed to be reading to be able to find this. So how many packets have that set? And then what we're looking for is this. We're going to do a quotation, we're going to do TCP, and then we're going to do these square brackets. And we're going to say TCP flags, and then close the square brackets. And we just want the flag to be set. So we're going to do and, the ampersand, and then TCP RST. So TCP dash RST is going to be not equal to, so exclamation equal 0, meaning it is set, right? So it wants the TCP reset flag to be set. This is the acronym for TCP reset right here. So it would look like just like this, except we're just changing it from SYN to RST. And then that's what the command would look like right here, assuming that we're supposed to be reading the PCAP file right here. That's what the command would look like. So let's press enter. Oh, I forgot to count it. Goodness gracious. That seems like a lot of packets. Yeah, that doesn't look like that's the answer. Let's end that. Can you stop? Can you stop, please? Thank you. All right, so let's do that one more time. And I'm going to TCP flags, right? And then TCP RST is set. That's basically what it would be. And then how many packets have only that set? It doesn't tell me what interface I'm supposed to be reading from or any of that stuff. So that's the piece that's kind of confusing for me. Maybe we're just supposed to run it on our current interface. That's kind of what I'm gathering from this, because apart from that, I have no idea what else is the option for me to be reading from. Okay, so instead of doing this, I'm just going to pipe this into word count and let's see what we get. And that's 65,598. So that's definitely not the one that I am trying to read, because that is a massive output. So I'm going to do just TCP dump by itself. And then I'm going to just write the rest of the options right here real quick. All right, so that is the command, and I'm not reading from the PCAP file. I'm just running basically this thing, and then with the RST packet set. So this is what the new command actually looks like here. TCP dump, TCP flags right here, and TCP RST is not 0, meaning it is set. Press enter, and it says you don't have permission to capture on that device. Oh, I need to do sudo. Goodness gracious. Okay, let's do that one more time. Okay, here we go. And I will actually pipe that into the word count as well. And then we need the password. All right, so that is the mistake that I made, was that I was trying to actually filter for this flag being set when I was just literally supposed to just be like, okay, I only want to see the ones that actually have reset set. So TCP dump, read the traffic file, and then we're going to do TCP flags right here. Same, this part stays the same, right? And then we're just going to say is equal to TCP-RST, and then pipe that into word count so we can see the number of packets, and then we can see that it's 57. So that's a much smaller number, much more manageable, and that is indeed the right answer. Okay, so now the next question is, what is the IP address of the host that sent packets larger than 15,000 bytes? And so we're just going to essentially read again, but then we're just going to use greater than 15,000, right? So We're going to do TCP dump. Again, we're going to read from the traffic.pcap, and then we're just going to say greater than 15.123. And oh crap, I forgot to count it. So we're just going to let me clear this. I'll go up, and then we'll just rerun that, and we'll just count it. It says 56, right? Or, oh, what's the IP address of the host that sent packets larger than 15,000 bytes? Okay, I was actually supposed to do that. Okay, that it sent packets. And then I was supposed to also do the end so it doesn't resolve the name. Man. A lot of stuff. Okay, so if I am correct about this, because all of the IP addresses that are sending are exactly the same, so 185.117.80.53, and that would be the one. So 185.117.80.53, and that is indeed the right answer. So just to show you what the final command for that looked like, it was this thing right here. Let's zoom in a little bit. This is the final command, TCP dump, read from the traffic file, greater than 15,000, and then just -n, so it doesn't resolve the name for me. I just want to see the IP address, and that was indeed the answer that we found over here. So excellent. Now we can move on to displaying packets. So let's see what we can learn here. All right, as you can imagine, there are a lot of different options for displaying packets. The ones that we're going to be talking about are these options right here. So the -Q would be the quick output, which prints brief packet information. -E would be the link level header. -A would be the packet data in ASCII. -XX, lower x's, dos Equis, shows the packet data in hexadecimal format referred to as hex. And then a capital X shows packet headers and data in hex and ASCII. So to demonstrate how this would look like, we would read from the two pcaps, or two packets.pcap, I guess. So the above options manipulate the output. First, we'll display two captured packets without using any additional arguments. And so this is what it will look like if you were just doing two packets without any additional arguments. That's what it looks like. Now, if we wanted to get the brief packet information, we just do -Q, and then you can see that it's literally it's like so small compared to what this is, right? So again, that starts the same, HTTPS. This one is HTTPS. It's going to this, right? It's going to this TCP 25, and I mean you have to go a ways to be able to find that TCP 25, which is nope. It's at the very end. So you see length 25, and then I guess we see TCP at some point. Do we even see TCP over here? We don't. We don't even see TCP over here. So it doesn't tell us that it's a TCP packet. It just tells us that the length is 25 at the very end of that. Over here, it says it's a TCP packet, and it's 25. I'm assuming that's the length. And then same thing over here, much shorter version, right? So this is the quick version. Shows the timestamp along with the source and destination IP and the source and destination port numbers. So these are the port numbers. So that's what it is. Source destination IP, and then I'm guessing these are the source destination. No, it's not. These would be the port numbers, right? Unless I'm misreading this. Anyways, link level header would be done with the -E, and so it gives us the let's see, if you're on Ethernet or Wi-Fi network and want to include MAC addresses in TCP dump output, all you need to do is add the -E. It's convenient when you're learning how specific protocols like ARP and DHCP function. It can also help you track the source of any unusual packets on your network, meaning trying to find the actual MAC address that is connected to the IP address that is sending these weird packets. So these are the MAC addresses that we can see right here. And then these are the destination MAC addresses that we can see right here. Ethernet types we have over here, the lengths of the packets. And then these are the IP addresses, as well as the, I guess, the resolved names, because we haven't done a -N to not resolve the names. So this is giving us the link level header. And then the data link layer is what this is referring to. If you think about the ISO 7 layers, this is what that is referring to, is the link level layer, the data link layer. Displaying packets as ASCII, this is very, very different from what you just saw. As you can tell, there's some extra data that's going on over here. For example, these pieces are the ASCII layers of this. So the American Standard Code for Information Interchange is ASCII. It represents text. In other words, you can expect this to display all bytes mapped to English letters, numbers, and symbols, as you can see over here. So by is one of those, I guess. Displaying in hexadecimal format looks very, very different as well. And what we have here, ASCII works well when packets' contents are plain text English. It won't work if the contents have undergone encryption or even compression. Furthermore, it won't work for languages that don't use English alphabet. Hence, we need another way to display packet contents regardless of format. Being 8 bits, any octet can be displayed as 2 hexadecimal digits. Each hexadecimal digit represents 4 bits. To display the packets in hexadecimal, we must add the -XX, and you can see that over here. And so each 2 of these represents a letter, right? So that's what they said, right? It won't work, being 8 bits, any octet can be displayed as 2 digits. So yeah, this is what we see right here. So if we wanted to see what these are, for example, we could go ahead and Google hexadecimal to text, and then hex to text is what we will see over here. And if I do 02 and then convert it, what would it give me? Okay, maybe 02 is too short, so we'll do this whole thing. I'll just take this block right here. Let's see if I can convert this to text at all. Oh, whoops. Convert that. I mean, it didn't convert to text, but it kind of did. So in a way it worked. But basically you can do that with with the use of a fairly simple online converter. And then if you wanted to see hexadecimal, you would just do -XX. That's all I gotta say, right? And then $X would give you the ASCII as well as the hexadecimal. And you know what? This is actually pretty close, because EM at 5 something something, that's kind of what this looks like right here. Oh, no, it's not. What am I saying? It's not even remotely close. Never mind. My bad, guys. My bad. So these are what they look like. -Q, -E, -A, -dos X, and -X. And then we got those. So what is the MAC address of the host that sent an ARP request? So the host that sent an ARP request, the MAC address of the host that sent an ARP request. I mean, there's a lot of them. Is it supposed to be from the traffic PCAP that I read? Okay, so if we went over here and let's read it. Yeah, it's just a massive amount of data. That's definitely not gonna work. So is there a hint for me? There's no hint for me. So I have to try to figure out exactly which one I'm trying to look for. Or is it the one, maybe it's the one from what we saw here of the host that sent an ARP request. So maybe this is the one that we actually are referring to here. The one that sent the ARP request would be the one at the top, I believe. That's the one that sent the request. So this would be the MAC address of the one that sent the request. I think that's what we're referring to here. Nope, that is not the one. All right, so it's neither of these, which tells me that we actually do have to read that big PCAP file. So let's see if we can try to craft a message here, or a command that would actually work. So ARP is what we want, and then we're gonna do the -E because it's gonna give us including MAC addresses. So we're gonna press enter here. Oh, okay, so it is much smaller. That is actually a very nice output. So we want the one that sent the request, which is the first one, I would say. So let's copy that and see. Let's see if that's the one. Cool, that was the one. Okay, excellent. So that's the main difference here. That is what we had to do, is we just had to specify that we are using the ARP protocol, or we're searching for the ARP protocol. And then we did -E so it can show us the actual Ethernet MAC addresses. And that was it. Just like that, we are officially done with this. So let's see what the conclusion is going to say. The conclusion says absolutely nothing. It just says we've covered various TCP dump options. Congratulations. So along with Wireshark and Tshark, TCP dump is an excellent tool for better understanding of networking protocols. And you're officially done. Look at that. We're done. Congratulations if you made it to this one. And if you made it to the end, I hope you actually got some value out of this. If you did indeed get value from this video, I do encourage you to like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out. And we are still in the CySec101 series. I just finished Security Plus, and that's going to be going up in, I think, on the 9th. I'm recording this on the 7th, I believe. And since that is actually done and it's been published, we can now run back into CySec101. And then there's also the AI cybersecurity series that's going to be coming out that I'm super excited about, because I personally think that it's the future. Everybody needs to know how to train AI, and you need to know how to integrate with AI. And I think that's one of the most powerful skills that you can develop. So that's going to be the next major training series that we're going to probably do, because that's what the community has been voting on over the last couple of days. So if you have not done so already, make sure that you like, subscribe, turn on the notification bell so that you get notified the next time that a comment comes up, that a content comes out, and then drop a comment. That's what I was trying to say. I kind of got ahead of myself. Drop a comment. Let me know if you had any questions. Let me know if there's something that you are curious about that you would like to see some videos on. And the AI thing is actually something that we actually got from a vote inside of the community, which is something that I did on this day right here. Hey, for the next major series, I want to see what's going on. And so far there's been 127 votes, and the AI for cybersecurity is currently leading. The other option was the Certified Ethical Hacker course that is available through Cisco, and that's getting a lot of votes as well. So it's kind of a very close, usually one option blows out the other option. This one is actually kind of close, so I feel like I'm probably going to do both of them. But I'm I'm personally interested on AI and cybersecurity. So again, just make sure that you stay tuned. Make sure you like, subscribe, turn on notification bell, all that good stuff, so that you get notified the next time that a video comes out, especially in the CySec101 series, especially in basically everything else that we're going to be doing. So if you have not done so already, make sure you do all of those things. Like, subscribe, turn on notification bell, drop a comment, all that good stuff. And then there's the Hackaholics Anonymous membership community, which is the premier YouTube community for security professionals and hackers. And as a part of that community, you get access to so many different types of perks, all the way from the cyber supporter, as well as going all the way up to the cyber master. There's, Discord servers for each level. There's going to be, when you get to the advanced levels, there's going to be exclusive content, exclusive downloads like Python automations every single month. We do live streams. There's so many things. So you can join through the link in the description below. You can join through the join button that's on our home page. Just go to the home page and click join. And of course, you can go to youtube.com/@HankHacksHackers/join, and then you will be able to join the Hackaholics Anonymous community. I really hope to see you inside of the Discord server. If not, I hope to see you inside of the comment section on the channel. This is your boy Hank Hackers, and at Hank Hacks Hackers, your favorite network and system attacker/protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease, and I'll see you in the next video. And then you could actually even see my little puppies right here, sleeping right here. They're being all cute and quiet, which is very rare for them because they're usually raising up a freaking storm. But it's late at night, and it's time for everybody to go to sleep. So time for me to go. I'm gonna go edit this real quick, publish it, and then I will see you in the next one. Peace. In episode 20 of the CySec101 series, we're going to go through the basics of the Nmap tool, which is a very powerful tool for network enumeration, and this is a part of the networking module of the Cybersecurity 101 pathway of TryHackMe. This is actually a room I have not done before. I've done several rooms on Nmap, but on this particular video, we're actually going through new content. So you can see there's none of the green checkboxes here. And for the most part, I think we're going to get a decent introduction to Nmap. Of course, it is coming from the perspective of Cybersecurity 101, so we're not going to do too crazy of a deep dive, but there's a lot of other videos that I've done on Nmap, so if you really want to get some more advanced tactics, you can definitely go and watch those videos as well. If you'd like to support this channel, consider joining Hackaholics Anonymous, the premier channel for security professionals and hackers. We have 4 tiers: the Cyber Supporter, Agent, Guardian, and Master. Each tier gets their own Discord server and early access to content. The Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus much more. So to join, you can simply click the link in the description below. You can go to our homepage and click the join button, or you can go to youtube.com/@HankHacksHackers/join to be able to join Hackaholics Anonymous. Now, without further ado, let us jump into the basics of Nmap. All right, so first, just to understand what Nmap actually does, if you've never seen it before, if you've never heard of it or used it before, the best way is obviously to imagine a particular scenario. So imagine you're connected to a network and you're using various network resources like email, web browsing, whatever. There are 2 questions that come up. The first is, how can we discover other live devices on this network or on other networks? And the second is, how can we find out the network services that are running on these live devices, for example, including SSH and web servers, right? So if you want to find out if they have web servers running or if they have secure shell open, so on and so forth. So one approach would be to do it manually. If you had to do it live on this particular IP range, for example, you can see a tool like Ping or ARP-Scan, or you can even use some other tools to check the 254 IP addresses that are available on this particular subnet, right? So we did an entire episode on network protocols and network basics, and then you should know what a subnet looks like. So when you see the 24 right here, you would assume that on this particular section, we have these octets that are actually filled in. So 3 octets are filled in and the last octet is being changed. So that means on this particular subnet, you have 254 potential IP addresses, and you can technically do that, right? You could technically go ahead and do that manually using something like Ping, and then you can see which one of them respond and then just do manual information gathering or ARP-Scan or something like that. But Ping won't give any information if the target system firewall blocks ICMP traffic, so you would literally be stopped in your tracks. And then ARP-Scan only works if your device is connected to the same network, because it is doing an address resolution protocol, which requires MAC addresses, which means you need to be connected via Ethernet or Wi-Fi in the same network, yada, yada, yada. So this would be a very, essentially, it would be a waste of time without an advanced and reliable tool. And with the right tools and enough time, one would have a list of the live hosts on a target network. We need a flexible tool. And so that brings us to Nmap, I guess what I'm kind of jumping at. So it says discovering the running services on a host is also equally time consuming. So if you want to see Telnet or see what other ports are available for Telnet, we can do that, I guess, with a variety of different tools. There's literally thousands of ports that could be connected to Telnet. So this will take a lot of time if you wanted to do it manually without the use of Nmap. All right. So finally, that's where this whole thing comes to play here. It's an open source network scanner that was first published in 1997. This is literally an industry standard tool. So anything in cybersecurity, pen testing, ethical hacking, Nmap is one of those names that everybody knows about. And at the very least, you should know how to run a basic Nmap scan. You don't need to know advanced scans to be dangerous. I feel like if you know just some of the basic scans, you'll be fairly functional in the, I would say, like the introductory and intermediate levels of cybersecurity, if you just know where to start and how to use Nmap, and we'll obviously be going into the details of that. So the objectives here is to first learn how to discover live hosts, find running services on the live host, distinguish the different types of port scans, and then detect the versions of the running services, control the timing, and format the output to make it easily readable, and so you can actually have a report that you can refer back to or send to other people, so on and so forth. So these are some of the key functionalities of Nmap, and we're actually going to be using them today. All of the networking videos that I've done at the beginning of this networking module, so basically these 4 videos right here, these are the ones that would be prerequisites for this room, and they are available in the CySec101 pathway. So if you have not checked them out, I would highly request or recommend that you go check them out, just to make your life a little bit easier as we move on with the rest of this particular video. So We are ready to go, and the virtual machine has already started. My attack box is up and running. If you have access to TryHackMe, you can use OpenVPN and your own computer to be able to attack the virtual machine that would be over here. So we've actually been given a virtual machine. This is our target machine that we're going to be scanning. And then the attack box that we have over here is a completely different IP address that we're going to be using to run this. So your computer, your own computer, could be an attack box if you have Kali Linux or essentially Nmap installed on any one of your machines. But you would need to connect to the TryHackMe servers using OpenVPN. For the purposes of this exercise, I'm going to be using the attack box that comes with TryHackMe. And I think that's all the disclosures I got to give you. So let's go into host discovery. So the first question that we had was who is online, right? So the first question, who is online? This aims to find out how to use Nmap to discover the live hosts, meaning hosts that are online. We can do this in a variety of sophisticated, fancy ways. We need to understand that Nmap uses multiple ways to specify its targets. So for example, you can actually use IP range. So you could say, if you want to scan everything from 01 to 010, you can write it as, you have the subnet, and then you have 1 to 10. That would be one version of it. You can also use subnet mapping as well. So if you want to scan an entire subnet, you could actually do the 01 or this portion right here, and then you would go from 1, and then when you do the /24, you're essentially implying that for this octet, this is, or for this range, excuse me. So each one of these that is between these dots right here represents an octet. So when you have 3 octets, that would be a range of 24 inside of this subnet. And so this subnet mask has 24, meaning this very last octet is the one that we want to discover hosts to, which would essentially be the equivalent of doing the subnet here and then doing 0 to 255, very similar to what we did here. But instead of doing 0 to 255, you could literally just do /24, and then it would search for every single IP address that could potentially exist. And then if it's obviously a live host, it'll show it to you. You can also target a host name, meaning a domain name. You could actually type in a domain name to see if there are any open ports or any services or so on and so forth available on that domain name. So if you want to discover online hosts on a network, we can do the SN option, which is basically the ping scan. However, it's not limited like ping because it can actually do other functionalities as well, meaning it could actually find ports and other things for you as well. So we should note that throughout this room, we're going to either run Nmap as root or using sudo because we don't want to restrict the abilities. Running Nmap as a local non-root user will limit us fundamental types of scans, so on and so forth. So we will, I would assume we're going to get some credentials to be able to do that as sudo. So if our IP address in this case would be this, then if we wanted to scan the entire subnet, we would be able to do it as such. So we've already discussed that. Then you would do nmap sn, and then you would basically ping everything on the subnet to see what you can find. So this is what the command itself looks like. They're running it as root, so they don't need to type in sudo. When you're already logged in as root, you can essentially remove the sudo portion of the command and just type in the entire command, and it will run it as root. And this is what the output basically looks like, right? So it'll start looking for a variety of different things for you, and I'll say, this is the IP address that's up, this IP address is up, this IP address is up, this one is up. Usually 1 is for the default gateway, and then 255 would be for the broadcast address. So it'll scan everything, and typically if the host is up, at the very least .1 and .255 will also be up, and everything in between, which is these ones right here, are going to be these various devices that are on that network. So because we're scanning the local network where we're connected to Ethernet or Wi-Fi, we can look up the MAC address of the device. Consequently, we can figure out the network card vendors, which is beneficial information that can help us guess the type of target devices that we have. And this is not something that you can do with ping. So that's one of those functionalities, right? You can actually find out the services and the versions of things that are connected to an individual IP address. When scanning a directly connected network, Nmap starts by sending ARP requests. When a device responds to the ARP request, Nmap labels it with host is up. So you can see this right here. So where do we see it? We can see Nmap report unknown. I feel like I saw host is up on here at some point. I literally thought I saw it. Maybe, oh, host is up. There we go. Host is up, host is up, host is up. Very good. Okay, cool. Scanning a remote network, so it's not connected to your Wi-Fi and it's not connected to your Ethernet, right? Remote network means that at least one router separates our system from this network. As a result, all our traffic to the target systems must go through one or more routers. Unlike scanning a local network, we cannot send ARP requests to this. So the system IP address that we have is this, and it belongs to this subnet or this network. In the terminal, we scan the network belonging to a completely different subnet where there are two or more routers or hops separating us. So this will be the command, very similar to the last command that we ran, but you can see that the output is very, very different than what you get over here, because this actually also gives you MAC addresses as well as the cards. So this is the card that you see right here. These are the network cards that they're talking about. This is actually available for pretty much every single MAC address that is connected to this. So on this one, we don't see that. We don't see the MAC address, and obviously we don't see the network cards that are connected to it. But we do see that obviously the first one is going to be up. These are up all here, and it'll go, and it basically tells us that there are 5 hosts that are up. By the way, a quick side note, if you hear sirens in the background, I'm literally recording this as there are fires all over the LA County area in Southern California. And I'm trying to avoid a bunch of anxiety. So I was like, okay, let me just get busy and start doing some recordings as well. But literally, as I'm recording this, the worst fires that have ever happened to Southern California are taking place. So it's kind of a crazy little situation that's going on. And our specific location is on evac alert, so they're letting us know that, you know, potentially they may let us know at any point that we need to evacuate. So you know, I have my go bags packed, and I have a bunch of water that we bought, and we have canned food and all that stuff, and I have power cables as well as several power sources that I bought for situations like this. So for the most part, we're prepared if we need to evacuate. I really hope we don't have to evacuate, but this is me literally attempting to avoid all of the scary thoughts that go on in my head by just trying to be functional and useful and create some videos for you guys. So that's a completely different side note. I have no idea if anybody's going to notice it or watch it or pay attention to this portion. It's a lot of people, I feel like they skip around in these videos. So just in case you actually did hear that piece, you know where my mindset is at during these recordings for tonight. So the Nmap output shows that 5 hosts are up, but how did Nmap discover this? To learn more, let's see some sample traffic generated by Nmap. And so we're looking at what we see over here, which is a Wireshark screenshot. And we did a few, or not a few, we did at least one video on Wireshark in this particular CySec101 training series, but there's a lot of videos that I've done on Wireshark. So if you want some more intermediate/advanced stuff, you can go check that out as well. But you should at the very least be familiar with this screenshot, this visual right here. So 11.1 is live and responded to the ICMP echo. 11.2 seems down. So Nmap sent 2 ICMP echo ping requests, 2 ICMP timestamps, 2 TCP packets to port 443 with the SYN flag set, and 2 TCP packets to port 80 with the acknowledgement flag set. The target didn't respond to any of them, and we observed several ICMP destination unreachable packets from the 151. So if you pay attention to it, it's coming from our source IP, right? So what did we say that our source IP was? It was 6689, and then we're scanning anything that is on 11 dot something, right? So we are looking at 6689. Let me see if I can kind of zoom in on this a little bit. So these are our sources, right? 6689, 6689 is contacting 11 dot whatever, and 11.1 responded back to us. So echo reply came back to us. So we know that at least 11.1 is up. 11.2, we tried to reach out to 11.2 in a lot of different ways, TCP, ICMP, so on and so forth. And we tried to reach out to various ports that we see here, 443, 80, and there was even a timestamp request. And then the responses that we got from that, we didn't get any responses from that actually. So we only got responses from 11.151 apart from 11.1, which actually replied to us that we know that it's up. we got a bunch of responses from 11.151 and destination unreachable. And then 11.2, there's no responses on this screenshot. So that's basically what we see over here. And there's most of them are ICMP, requests and replies, and then we have several TCPs, because when you do run SN as the option with Nmap, at the very least it'll try to see if it can find other ways to communicate with the desired IP range to see if it can get us any responses. Now it seems that this one was actually down because it didn't respond to any of the requests that we sent out. So it's worth noting that we have more control over how Nmap discovers live hosts, like the -PS, which is the port list that we can do, and then PA, which is another port list, and then PU, which is another port list. And these are all caps lock. And these are for a variety of different types of scans for the ports. So for example, you can do a TCP SYN scan, which is what this is, port SYN, and then TCP acknowledgement scan, which is port acknowledgement. And then we also have the TCP or the UDP scan, excuse me, which is port UDP. And then via the given ports, however, this is beyond the scope of this room. But for the most part, essentially what that means is that the port list portion that you see right here could be, you could do port 80, and then you could do comma port 443, comma port 22, comma port 25, so on and so forth. And then that's how the port list would be. You could either separate them individually by commas, or you could do a range of ports where you say do 1 dash 1000, and it will scan everything from port 1 to 1000, basically. It is beyond the scope of this room, but that's essentially the gist of it. If you want to learn more about that, you can go and watch the other Nmap videos on the channel. So as a final point, Nmap offers a list scan with the SL option, S lowercase capital L, and this scan only lists the targets to scan without actually scanning them. For example, SL yada yada will list 256 targets that will be scanned. This option helps confirm the targets before running the actual scan. So this is not going to run the scan. It's just going to list what potentially can be scanned. And so if you do a range like this, there are 256 targets, because each one of these sections that you see here can go from 0 to 255. So it includes 0, and then it includes 1 to 255, which is total 256. So that's kind of what that looks like. SN, so lowercase s, lowercase n, aims to discover the live host without attempting to discover the services running on them. This scan might be helpful if you want to discover these services on a network without causing much noise. However, this won't tell us which services are running. If we want to learn more about those things, we need to do some other types of scans, and they tend to be more noisy, meaning something like this. Well, Wireshark isn't designed to be an intrusion detection system or a SIM or anything like that. So Wireshark can only be helpful if somebody who's looking at the data knows what they're looking for. But for an intrusion detection system, when you run these noisy types of scans, it'll actually pop up. And the intrusion detection, the IDS or the IPS or the SIM, any of those things will actually be like, hey, somebody's scanning us. Maybe we should block these IP addresses from scanning us. So that is what we got so far. So now, once the attack box is ready, which is ready, we're going to open the terminal to access Nmap and then use that to answer the questions for the rest of these things that we got over here. So what is the last IP address that will be scanned when your target is this and then 27, which is interesting. I know what it would be if it was /24, because that's basically what we're doing, and we'll scan that entire range. So what we are getting over here is that I think this is like a specific potential range. Maybe we're going to scan up to the 27th IP address or something like that. The hint says use Nmap's list scan SL to see what we can find. So whoops, I should not have done that. Now I can't zoom out of this thing. But at the very least, we can actually just run Nmap and then make that happen. So let's run Nmap real quick and then see what we can find. So I'm actually already logged into root. It seems that I don't need to switch users or anything like that. So this is what the command is going to be, right? It's going to be Nmap, and then we're going to do S capital L, and then we're basically just going to put in the IP range, which is 192.168.0.1, and then we're going to do a /27, and that is I don't think that's the actual machine that we've been assigned. It isn't the machine that we've been assigned. So that's very interesting to kind of see. So it's not going to run the scan. That's the one thing that we did get. But it is going to list whatever is available for us when we actually type this type of a command out here. So I'm just going to press enter, and it's going to give me the last one, which is going to be 031. And it says 32 IP addresses. And this is what's very interesting to me. I don't know what this thing right here actually is representing, because it starts with 1 and it goes all the way to 31, and it's saying 32 IP addresses because it actually also does 0. I don't know what the 27 represents. I really need to find out what that represents, because that's going to bug me and I have no idea what that means. So we're going to go to our handy dandy AI friend to explain this to us. Okay, so this is actually a pretty super technical answer. All right, so this is the starting IP address of the range, right? //27 is the CIDR, the classless interdomain routing notation. It specifies the number of bits used for the network portion of the IP address. /24 is the common example. It would mean 24 bits are used for the network, leaving 8 bits for host addresses. So 256 possible hosts minus 2 for the network, which ends up being 254 actual usable hosts. 27 means 27 bits are used for the network, leaving 5 bits for the host, meaning 2 to the power of 5, 32 possible hosts, meaning minus 2 for the actual the 1 and the 0 and the 255, or the 1 and 255, I guess, which means we would actually have 30 usable hosts. So the target identification nmap would attempt to scan all the IP addresses within this range. This would typically include addresses from 01 to 030. Nmap would try to determine which of these IP addresses have active hosts. For each active host, Nmap would attempt to identify what services are running on the hosts. This often sends probes, operating system detection, yada, yada, yada. So it denied the portion where I did SN for the most part. Did I do SN? I thought I did. Let me see. Oh, I didn't. I just said that would be the thing. So we're doing an SL scan. So I didn't tell it about that. So I guess it's going to, if I understand correctly, this goes a little bit into the details of subnetting. So when we do 24, we are saying that we're going to leave 20, or we're going to take up 24 bits for the network. And each one of these is an octet, right? So if each one of these is an octet, that means that this is 8, this is 8, this is 8. Everything between these dots is an 8. So that'll be 24. If we are taking 27 bits, that means we're also taking 20. So in a range of 3, this would technically be 25, 26, 27. That's technically it. Or am I misunderstanding? I feel like I'm totally misunderstanding this. I think I'm going beyond the scope of this room. I apologize. I always go down these freaking rabbit holes. And if you ask anybody who's actually been a subscriber of this channel for a while, they will tell you the same thing. I always freaking go down these crazy rabbit holes because I'm trying to figure out extra information to try to answer these things for us. But basically the answer is this, right? The last IP address is the 168.0.31. That's going to be our answer. But I was just trying to find out what that /27 means, which I guess technically now we know, right? It's saying that it's taking 27 bits, right? That's basically what it says. It means that 27 bits are used for the network, leaving 5 bits for the host, which would be 2 to the power of 5, which would be 32 possible hosts. And then if there are 8 bits left for the host, which is what this does, that means 2 to the power of 8. Okay, so now I understand that actually. Now I get it. So when we do 24 like this, that means we are leaving the last octet, which would be 8 bits. So it would be 2 to the power of 8, which leaves us 256. If we are doing 27, we just take the total that's available for us, which is 32. If there are 4 octets, that means there are 32 bits available. So if we've taken up 27 bits, that means we are leaving 5 bits for the hosts. So 2 to the power of 5 means 32. That's actually how you do the calculation. I was trying to do it based on the numbers, the positions inside of these decimal points, but that's not the way to do it. So it's the 2 to the power of whatever bits would be the way that that's figured out. Okay, That's not required for you to know in CySec 101. I literally went off the reservation and I kind of lost my mind a little bit because I really wanted to figure out the answer to that. But we actually got our answer, and we did it by running this scan right here. Very, very simple scan. Nmap dash SL, lowercase s, capital L, and then the IP range itself. And that's all we got. All right, so now let's move on to port scanning. So where the host scan was telling us who is online, port scanning is telling us who is listening. So from all of the services, or not all of the services, excuse me, from all of the devices that are online, on those devices, which ports are listening? That's basically what that means. So we used SN to discover the live hosts. We want to discover the network services listening on those live hosts. And we mean any process that's listening for incoming connections on either a TCP or UDP port. Common network services like web servers, which listen on ports 80 and 443, DNS servers, which is typically on UDP and TCP port 53. These are default ports, by the way. You can always change these when you're doing your configurations. By design, TCP has 65,535 ports, and then there's also 65,535 UDP ports, right? So there's a lot of ports that are available. So how do we find out what services are attached to these freaking ports? So scanning those things would be to attempt telnet to the port, I guess, is like the easiest and most basic way to do it. But if you're inclined to scan with telnet client, trying to establish a connection with every target port, in other words, you attempt to complete the three-way handshake with every target port. However, only open ports would actually respond appropriately. And then this procedure is not very different from Nmap's connect scan, but it is way more labor intensive. Instead of just running a connect scan with Nmap, you would be trying to connect to the freaking thing via a telnet client, which, in my humble opinion, unless it's an automated telnet client, if you're trying to do it manually, it's like, why would you do that? Because literally you would have to run, unless you can write scripts, right? If you know how to run scripts, then you should be all good in that regard as well. But the connect scan, which is a very nice TCP scan, it does the full three-way handshake, right? It does the three-way handshake for TCP, meaning sending out a synchronize, then getting a SYN acknowledgement and then an acknowledgement. That is a three-way handshake, right? We covered this in the networking basics. So our scanning machine has the IP address of this, and the target system has TCP port 22 open, port 23 closed. In the part that's marked with 1, you can see how the TCP three-way handshake was completed and later torn down with the reset acknowledgement pack by Nmap packet. The part marked with 2 shows a connection attempt to a closed port, and the target system responds with a reset acknowledgement immediately. So part 1, which is these 3 right here, the one, let's open this up, zoom in. 1, 2, and 3 packets right here are the packets for the TCP connect scan. So you see the SYN packet sent, and then the server responds with a SYN acknowledgement, and then we send out an acknowledgement, and now we have completed the connection. And then at the very end, we get a reset acknowledgement, which means the connection is now killed. So we are the 148 machine, and we're trying to connect to the 211 machine, and we get our connection, and then at the very end, we send the reset acknowledgement, meaning close this connection. And then when we try to connect to the 211 on a different port, so this was on port 22, which is the SSH port, when we try to do it on port 23, as soon as we send the initial SYN request, the SYN packet, we are immediately met with a reset acknowledgement, meaning that one is actually closed, and we literally have nothing to do with it. So that's what it looks like when you have a full completed handshake and then one that wasn't even available or possible to connect to. Then you have the SYN scan, which is a stealthy scan. So as far as the noisiness of the scans are concerned, the connect scan is the noisiest because you're actually trying to complete a three-way handshake via a port, and that always shows up on even the most basic intrusion detection systems or SIMs or so on and so forth. If you're not trying to raise a lot of noise, but you're trying to see if the port is open, typically a SYN scan will actually do the job. So unlike the connect scan, which tries to connect to the port, completing that handshake, The SYN scan only executes the first step, meaning it just sends that SYN packet. And then the three-way handshake is never completed. The advantage is that it's expected to lead to fewer logs as the connection is never established, and hence it's considered a relatively stealthy scan. And we can do this with the lowercase, uppercase s, and then on this one it was the lowercase s and then the uppercase t for connect, or TCP, if you want to do it like that. Stealth is very easy. It's lowercase, uppercase. So SYN, and a stealth, so on and so forth. So now we actually see the response the way that we previously ran it, except in this particular case, where there was the 148 to 211, 211 to 148, 148 to 211, that whole handshake that was completed, right? So this is the actual TCP scan that we see right here. In this particular case, there was just a SYN scan that was sent, and then there was a reset acknowledgement that was sent back from the service. In this case, it's showing that the TCP attempt to a closed port. In this case, the exchange is the same as the connect scan, but you know, it's very similar to just running a SYN scan by itself, because literally it's just sending the SYN packet. So the marked with the 1 is showing listening reply with a TCP SYN acknowledgement packet. However, Nmap responded with a TCP reset packet instead of completing the TCP scan. So okay, you know what? My bad completely. This is actually the SYN scan that's been completed. This is not the TCP scan. That is my bad completely, because the first one that we saw, it actually had 4 packets, and the 4th one was the reset. This is just the SYN, and then the SYN was acknowledged, and then we never sent the final acknowledgement. We immediately just sent a reset because we didn't want to complete that handshake or complete that connection. My bad, you guys. My bad. Okay, but the second one was pretty much the same thing, because the port 23 was closed, so the initial SYN request was never acknowledged, and so we were never able to make anything as far as a SYN scan connection. The UDP ports, although most services use TCP, many use UDP. Examples include DNS, DHCP, NTP, which is the Network Time Protocol, SNMP, which is the Network Management Protocol, and VoIP, which is Voice over IP. UDP does not require establishing connection and tearing it down afterwards. Furthermore, it is very suitable for real-time communication, such as live broadcasts or streaming on Netflix, for example, that also uses a UDP typically. All these are reasons to consider scanning for and discovering services that are listening on UDP. The lowercase s, uppercase u is the scan for UDP services. Because UDP is simpler than TCP, we expect the traffic to differ. The screenshot shows several ICMP destinations unreachable, port unreachable responses as Nmap sends UDP packets to closed UDP ports. So we can see the protocol has changed to UDP instead of TCP. It's all going from 148 to 211, and then we're trying to connect to a variety of different ports, and all of the responses that we get from 211 to 148 saying destination unreachable, port unreachable, are the closed ports. They're not available, right? And the same thing with this final response that we get at the bottom right here as well. So these are closed ports that we're getting with the UDP scan that we're running. Now, limiting the target ports, so running for the most common 1000, which is 1 to 1000 basically. This might not be what you're looking for, therefore Nmap offers you the option to actually do a variety of other things. So -F is for fast mode, which scans the 100 most common ports instead of the most common 1000 ports. It's actually, so it's the most common 1000 ports, my bad. It's not 1 to 1000. It is the most common 1000 ports. I do believe that it is 1 to 1000, but it may not necessarily be 1 to 1000. It's just scanning the most common 1000 ports. 3389, for example, is the port for remote desktop, which is something that's for Microsoft, and that is not in the 1 to 1000 range. It's literally above 1000. So that is actually my bad. Again, my bad on the misinformation. -F is for fast mode, which scans the 100 most common ports instead of the 1000 most common. And then if you do P, so lowercase p, and then just giving it a range, it'll specify the range of ports. So for example, if you do P10 to 1024, it scans from port 10 to port 1024, while doing P and then -25 will scan all the ports between 1 and 25. And if you do -P-, it scans all the ports which means every 65,535 ports. So this thing will take forever, just so you know. When you do -p-, it takes a long time to complete that scan because it's literally scanning for 65,000 ports. So this is our summary. We have S_T that does a TCP connect. S_S does a SYN scan, which is just a stealth scan. S_U is the UDP scan. -F would be fast mode, which does the 100 most common. And then you can do -P range and then specify a range. And then -P- scans all the 65,000 plus ports. So now let's do some scans. How many TCP ports are open on the target system at the target machine that we have? So we're looking for TCP ports, and basically what I'm going to do, I'm not going to run the entire freaking 65,000. I'm literally just going to do the nmap, and I'll do lowercase s_T, and I'll do 10, 10, 185, 58. I'm just going to run that, and that was very quick. So we have a total of, let's see here, this was the command nmap S_T, and I gave it the IP address. So we have how many? It says scan and it doesn't tell me. Okay, so 1, 2, 3, 4, 5, 6 is what I have open. 1, 2, 3, 4, 5, 6, and find the listening web server on that IP address and access it with your browser. What is the flag that appears on the main page? So if we look at these things just to see what the services are, okay, so this is an echo service on port 7. This is a discard service, which essentially it's kind of the equivalent of null, which just gets rid of whatever goes there. This is the daytime, which gives us just a date and time, and it's like a calendar type of a thing, just checking the date and time at the time. QOTD, I would assume that's quote of the day, I guess. And then this is secure shell. And then there's only one that is an HTTP service, which implies that that is actually the web service, because HTTP is the protocol for internet services, right? Hypertext Transfer Protocol. So I need to open up my browser, and the way that we do this by just going to the IP address. So I always do HTTP : // and then just do the IP address, and then you would do the colon again, and then you would do 8. I think it was 8008. Is that what it was? Was it 8008, 8005? Let me see. Let me go find that. It's easier if I just make this full screen real quick. Okay, yeah, it is 8008. So there we go. And this is what that looks like. 10, 10, 185, 18. And then you do that colon, and then you do 8008, meaning you want to connect to port 8008 on that IP address, and then press enter. And now it says unable to connect. So that is interesting. Let's see if we can fix this. Oh, that's my bad. It's not 185.18. It's 185.58. That's what it is. And there we go. Okay, cool. There's the flag. I was like, I knew I was doing it right. I don't know why it wasn't working. And it was because I mistyped the IP address. Cool beans. There we go. We got it. Now we can move on to version detection. With version detection, we can now actually get specific information about each individual port. So for example, if you do the -O option, it'll give you the operating system, the OS, right, detection, and then triggers that to get various indicators to make an educated guess about the target operating system. So in this case, it's running Linux 4.x or 5.x running. So if we look at it right here, we can see it. So for port 22, it's open. The MAC address is this. Device type is general purpose, running Linux 4.8, 5.x, and then Linux kernel right here, and then 4.15, 5.8, network distance 1 hop, right? And because we're getting the MAC address, it implies that we're on the same network, and then it only took 1 hop to get there. So that's kind of some of the things that we can conclude from this. But that's what we get from it. It actually gives you the operating system, or at the very least, a good guess on what the operating system would be. That's what O does. And notice that they also did a lowercase uppercase s, which means this is a SYN scan, a stealth scan, and then the O, and then we ran it on the IP address, and this is what we got. If you wanted to do service and version detection, you can do lowercase s, V for version. That's how I remember these things. And then that's what we could run over here. And then we can see host is up and the port itself is here. SSH is here. The version of SSH that's running is OpenSSH. And then it's giving you the MAC address still. And then service info is the OS is Linux, but it doesn't give you everything about the Linux kernel. So notice that on this one, it gave you more on the actual Linux version that you have over here, as well as the Linux kernel. But there was nothing that had to do with what version of SSH was running over there. On this one, you actually get to see the version of SSH that's running, and then Ubuntu, so on and so forth. And it gives you Linux, but it doesn't give you anything about the Linux version or the kernel. If you wanted to force the scan, this is one of those interesting things. There's a possibility that the target host doesn't reply during the discovery phase, meaning it doesn't reply to the ICMP request, the ping. So consequently, Nmap will mark this host as down and won't launch a port scan against it. We can actually ask Nmap to treat all the hosts as online and port scan every host, including those that didn't respond during the host discovery phase. So that's what it means to force the scan. And you can do this with the PN, so capital P lowercase n option. And this scans the host that appears to be down, even though, you know, supposedly it's down. We're still going to scan it and see if there's anything available on the ports on that IP address. So capital O is the OS detection. S capital V, so lowercase s capital V is the service and version detection. Capital A does everything, and this is another one of those things that takes a long time. So if you do a capital A on all of the 65,000 ports, step away from your computer, come back in a couple of hours. It's going to take a while for it to finish that scan. If you do capital A, but you do it on one port, then it'll take maybe a couple of minutes, right? Because it's just looking at all the details for that given port. But for the most part, if you run it on, you know, the top 1,000 most common or even the top 100 most common, it'll take a minute for it to complete that. And then you have capital P lowercase n, which scans everything that appears to be down. So what is the name of the name and detected version of the web server that's running on our IP address over here? So I'm just going to go back to my full screen browser here. And so now we know that the IP address is on port 8008. So what I can do now is I can actually make this a little bit more customized, and I can do -P and then give it 8008 as the port, and then I'll do 10.10.185.58 and then press enter, and then that should give me the response hopefully fairly quickly. But it's running on port 8008. Here we go. So we got it's the light TPD 1.4. whatever, and we're just gonna copy that, and that is our answer. So paste, enter, and we are all good. So you can see that it's fairly simple to run these things. It's not complicated. But it's very useful, right? It's very insightful. And interestingly enough, again, I stand corrected. Even though this is not on the same Wi-Fi as me, we were still able to get the MAC address, which tells me that when you run SV or when you run -O, it will get you the MAC address even if it's not on your specific network, on your Wi-Fi or Ethernet network. So my bad. I'm like messing up with all of my information. So hopefully you're paying attention to all of these things, and when I make these little corrections, you can actually walk away with the correct information. All right, so let's talk about timing. So how fast is fast? Nmap actually gives you options to control the scan speed and timing. And this is where a lot of these flags that you see right here come in. So running the scan at the normal speed might trigger an IDS or other security solutions. It's reasonable to control how fast the scan should go. It'll give you 6 timing templates, and the name says it all: paranoid, sneaky, polite, normal, aggressive, and insane. So you pick the timing template by its name or number. For example, you can do T0, capital T and then 0, which means you're super paranoid. So you want the timing to be as slow as possible so you're not going to get detected. You can also do T space 0, or you can do T and then type out paranoid to opt for the slowest timing. And in the scans below, we'll launch a SYN scan targeting the 100 most common TCP ports, which means lowercase s, uppercase s, and then the IP address, and then you do capital F for fast, and it'll do the 100 most common. We repeated the scan with different timings, 0, 1, 2, 3, and 4. In the lab setup, Nmap took different amounts of time to scan the 100 ports. The table below could give you an idea, but you will get different results depending on the network setup and target system. So same scan, same exact scan, right? Except the first one was T0, meaning paranoid, and it took 9.8 hours against the 100 most common ports, okay? You took T1 sneaky, it took 27 minutes. Polite took 40 seconds. Normal took 0.15 seconds, and an aggressive took 0.13 seconds. So it's a very big leap to go from 9.8 hours, pretty much 10 hours, to 0.13 seconds. Do you see how difference is? So the same scan, literally same exact scan, and it's going against the top 100 most common ports. But 100 ports could take 9.8 hours, or it could take less than a second, depending on where you're at. In the screenshot, we can see that the time that the Nmap send the different packets. In this screenshot below, when scanning the timing being T0, we can see that Nmap waited 5 minutes before moving to the next port. So this is what you see right here. 300 seconds resembles 5 minutes, right? 600 seconds, and then 600 seconds again. So this was all, I guess, the same thing. And then 900 seconds, 1200 seconds, 1500, 1800. So it's basically adding 5 minutes to every single ping or SYN packet that's going out. And then it's going against, there was 2 that went against port 22. So that's why we see that. But there was all these various ports that are going out. And these are the 100 most common ports that are happening. So every 5 minutes it's sending out a packet, right? That is very paranoid, right? It's trying to avoid being detected. This is the one that waited 15 seconds between every 2 ports because we set the timing to T1. And so you can see that here as well, 15, 30, 45, so on and so forth. Same list of ports right here. And then when we went to T2 and it dropped to 0.4 seconds, you can see that here as well. You can see the progression of how much quicker these ports are. T3 dropped it to running as fast as it could potentially, it's now not even counting in seconds anymore. It's counting in milliseconds, right? And then we don't have any other screenshots. But that's basically what you can take away from this, is that when you go paranoid, it really takes its time. And then when you go aggressive, then it'll happen in a matter of a second or two. A second helpful option is the number of parallel service probes. The number of parallel probes can be controlled with the min parallelism and then the number of probes, and max parallelism number of probes. These options can be used to set a minimum and maximum on the number of TCP and UDP port probes active simultaneously for a host group. By default, Nmap will automatically control the number of parallel probes if the network is performing poorly. Dropping packets, for example, dropping packets, the number of parallel probes might fall to 1. Furthermore, if the network performs flawlessly, the number of parallel probes can reach several hundred, meaning there are several hundred probes going out at the same time trying to find these various open ports for you, which is why you can have quick responses, or as quick of a response as you can, for example, less than a second to scan 100 ports, right? But if it's not responding, if the packets are being dropped, then it's just going to use one probe because it wants to make sure that it actually gets everything and the network isn't being responsive, so on and so forth. Another option would be the min rate or max rate. They control the maximum and minimum rates at which Nmap sends packets. This provides the number of packets per second. It's worth mentioning that the specified rate applies to the whole scan and not to a single host. The last option we will discover is the host timeout. This option specifies the maximum time you are willing to wait, and it is suitable for slow hosts or hosts with slow network connections. So T0 to 5 ends up giving you the paranoia rate, right? The sensitivity rate. It's the timing template. So you can go from super paranoid or just not paranoid at all, not giving an F, and then just running as fast as you possibly can. Minimum and maximum parallelism is the number of parallel probes. And then minimum maximum rate is the maximum rate packets per second that are being sent out. And then host timeout is the maximum amount of time to wait for a target host. So you can say host timeout and give it 300 seconds, and it would say that is 5 minutes, right? So what is the non-numeric equivalent of T4? And we see over here, which is aggressive, is the non-numeric equivalent of T4. There we go. So dash capital T, aggressive, is how you can actually say the same thing as T4. You want it to be aggressive. All right, so now let's get some instructions on how to actually generate some output files for ourselves. So when I think of output, I think of an output file, but the way that they're talking about output is how verbose the response is going to be and what you're going to end up seeing, and then how you can debug things. So I'm just jumping to all the wrong conclusions today. It focuses on two main things: showing additional information while a scan is taking place, which is called verbose or verbosity, and then showing the file format to save the scan report. Okay, I guess we are going to be talking about actual output files. So in some cases, the scan takes a very long time to finish or produce any output that will be displayed on the screen. Sometimes you might be interested in more real-time information about the progress. The best way to get more updates while it's happening is to enable verbosity. Consider the following terminal output without verbosity, which is what we see over here. And it's just a stealth scan against this subnet, right? You can see that these are the results, and then it took 41 seconds, and then this is basically all the output that we got onto the screen. There was one port that's open, and that's it, right? That's what you get when you don't do verbose. Now you do the same exact thing, except you just add the verbose at the end. They did remove the stealth scan part of it, so they did not enable stealth scan. They just enabled verbosity. And then now you can see a very different type of an output. So you can actually see as it's going, right? So this resembles basically the in-between between dot 2 and then dot 253. So you can imagine that it went 3, 4, 5, 251, 252, 253. So it scanned all of those things, and all of it was printed onto the screen, as well as these various messages that are attached to it. And then there was a situation saying, okay, now we're doing a stealth scan at this particular port or this particular IP address. And then this IP address, we are now going to scan 1,000 ports on it. And then these are the results that we're getting. Discovered an open port, and then still stealth scan was completed. And this is the complete report for this. And then you get to see the 902 port. So the same port is officially being listed as an open port, which we saw exactly over here as well, except in the process of it displaying everything onto the screen. I'm doing this, now I'm doing this, now I'm doing this, now I'm doing this. Oh, I found an open port. Okay, now I completed my scan. And then this is the official report that you get from me right here. So -v is more than enough of a verbose output, but you can also do very verbose or very, 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 very verbose, right? Like you could just add as many freaking V's as you want. Not as many, but you can go up to 4 V's. You can specify the verbosity level directly, for example, V2 or V4. You can even increase the verbosity level by pressing V after the scan has already started. I didn't know that. That's actually very useful to know. Sometimes I just cancel the scan and restart it and put -V. I had no idea that you can actually just press V after the scan's already started. That's very useful. If all this verbosity does not satisfy your needs, you must consider the debugging level output. Similarly, you can increase the debugging level by adding more Ds. That's what she said. You can go up to D9. Before choosing that, make sure you're ready for thousands of information and debugging lines, because it's going to give you a lot of output. Now, we're talking about saving it inside of an output file. So we would need to save the scan results. Nmap gives us various formats. You can do ON file name, which is just a normal output, OX, which would be an XML output file, OG, which would be a greppable output used for grep, and AWK, awk, which are search patterns. Well, grep is more like searching for strings. You can actually use patterns, but awk has its own syntax for finding various types of patterns. And then OA, which is outputting in all major formats, which will generate multiple output files for you. So if we actually do OA and then save it into gateway, the name will be gateway, right? So the name of the file will be gateway, but it will be gateway.xml, gateway.txt, so on and so forth. So this is what you get: gnmap, gateway nmap, gateway xml, right? These are the things that you get. So What option must you add to your nmap command to enable debugging? And that is throwing some D's on this thing. So -D is the answer for that. And before we jump into the conclusion over here, which is actually a really nice little cheat sheet that we have based on everything that we just discussed, I do want to show you one other quick little tool here that is very, very useful. So this is what I teach in every command line or any kind of Linux and even Windows, right? So the Windows syntax is different, so I don't want you to think that you can use this command for Windows, but if you're using any kind of Linux machine or even Mac OS, because it runs on Unix, which is a very similar operating system, you can do man, and then you can do nmap, and then it'll give you the manual page for nmap, which tells you, okay, this is what it is, this is a basic synopsis, and then you can do the scan type and the options, and that's basically what you can run. And then you can go throughout the description of it if you want to, which is like a very lengthy description. And then you start seeing examples of this. So nmap-a t4 on this domain name, and it'll start giving you what the output will look like. And then if you go down, it'll give you what all of the various options are that you can actually run for nmap. So for example, you can run the IL, which would be input from a list of hosts and networks, and then you would have to give it a file name, right? And that would take an entire list of hosts or networks, and it will start scanning against all of those. And in this regard, you would need to do an O and then actually output the report, because it's going to be a massive report. There are the host discovery options you have, there are the scan techniques that you have, and then there's something very, very interesting that is available, is the script scans. So these are actually pre-embedded scripts. These are scripts that come with nmap, and you can actually, there's an entire list of scripts that are available, and you can even get a help menu for each one of the scripts, and you can even get a list of these scripts that are available to see what types of scripts are available and what you can run. And then some of them actually do vulnerability scans as well. So you could do a vulnerability scan within nmap, which is again very, very useful. And then these are all of the output options that you have, and there's just a bunch of stuff. So there's a lot of options that are available to use nmap. And then this is what the use of a manual page is like. So if you've never used this tool, or the tool that you're thinking about using, you can look at the manual page, and the manual pages are very extensive. Like, this is a very extensive, for each option, it's telling you this is what it does, this is how you can use it. So it gives you a lot of breakdown, a lot of good information, so that you know what to do if you've never used this tool before. Now, if you don't like reading and you just want somebody to guide you through these things, then I recommend going to check out the nmap videos that are on this channel. I do give you a forewarning. At the time that I was recording those videos, I was using one of those plug-in headphones that they're like the wired headphones that connect to your computer, and it's kind of like the cell phone headphones, the white wired headphones. And I was wearing a hoodie the day that I was recording them, so the hood of my hoodie was scrubbing or rubbing against the mic, so there's like scratchy noises, and people have commented on it, and people were upset about it, and I just did not re-record those things because it took a while to record those things. And unless it's absolutely necessary, I do not re-record content, but the content is still good. If you can get past the occasional little scratching noises, the content is still very solid, and you'll learn a lot about nmap. So full disclosure, there's a little bit of scratchy noises on those things. I am now in a much different recording environment, and I have a better microphone, and the quality of the noises, or the quality of the voice is better, and whatever, blah, 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 blah. Okay, so let us go into our conclusion and summary, and then I'll give you a couple of extra notes at the very end, and then we'll wrap this video. In conclusion, we have ran a variety of different scan types and options with nmap. It's important to understand that we actually ran nmap with sudo privileges because we were signed in as root, and we were able to use a lot of its features. Now, if you wanted to run something like a stealth scan, the SYN stealth scan, it'll actually ask you to run it with sudo privileges, and it will cancel it out. So it'll either say run with sudo, or it's just going to default to running a connect scan, because a stealth scan technically is used for pen testing, ethical hacking, and it wants to make sure that you actually have sudo privileges, or you know what you're doing, so on and so forth. So that was one of the important things that you need to keep in mind, that the couple of scans that we ran, that was a stealth scan, it is required with sudo privileges or root privileges to be able to run some of these things, because they are reserved for administrators and root users. These were some of the massive amounts of, just a few of the massive amounts of options that are available inside of Nmap. In the network security module that we did, the 4 rooms that are connected exclusively to Nmap, it's not part of CySec101. It's a completely different series of videos that we did, but there are 4 rooms that were a part of Nmap, and I have recorded all of those rooms. So you actually see that we see all of these check marks that are over here, and then there's the Nmap live host discovery, basic port scans, advanced port scans, and post port scanning. All of those videos are on this channel, and you can go find them to get more information about Nmap if you're curious how to use it. It is a very powerful tool, and if you're serious about security, whether as a pen tester or as defensive security, I would recommend you learn how to use Nmap. And then these are just a variety of different options that are available on the video that we just ran today. And you can, of course, go ahead and look at the manual page for Nmap, and you will get a much more detailed outline of what each one of these options actually represents and how to use them. And it'll give you even sample commands that you can use to actually create those Nmap commands, so you can use these various options that are available for you. So what kind of scan, this is the final question, what kind of scan will Nmap use if you run Nmap this just basically with local user privileges? And that would be the TCP scan. So what would we call it? TCP connect scan? So Nmap TCP scan. So if we just run it, basically it'll run as the TCP scan. That's basically what I know. But let me see. I feel like I'm not TCP scan. I want to say it's TCP scan. Yeah, it is a TCP. I think it's actually, I think that's what they're looking for, is a connect scan. That's what they're looking for. Yeah. Okay, I got. Okay, very good. And so we're officially done with this video. So let me just give you a couple of extra pointers, and then we're out of here. Alright, so if you found this video useful, and if you want to get more videos like this one in the future, I do encourage you to like, subscribe, turn on the notification bell so that you get notified the next time a video comes out, especially the videos that are inside of the CySec101 series. There's also all of these videos that are on the channel that, for example, recently Security Plus came out, and it's a 5 video series that has its own playlist. There's also the playlist for Linux Plus that came out, and there's a variety of other, you see all these different playlists that we have over here. So there's a lot of good content on this channel, and I do get recommendations from our community to create more content that is actually unique for you guys and is actually demanded by you guys. So it's something that I'm passionate about creating, and I just want to make sure that you get exactly what you're looking for as your connection and as your as the community. Essentially, this is for you, right? So make sure that you drop a comment, let me know what you think. If you have any questions, I'll answer your questions in the comments. If not, if it's a really good question, I'll create a video in response to your question. Or this entire playlist, the CySec101 playlist, is in response to Darnell Knight's comment, and I give him a shout out every time that I can remember to actually give him a shout out. And this is why we created it. So at the very least, say thank you, Darnell, in the comment section if you want, or just drop your questions or anything like that. Make sure that you like, subscribe, turn on the notification bell, all that good stuff, and of course drop a comment, even if you just want to say thank you. As another form of thank you, you can actually support this channel by joining the Hackaholics Anonymous membership community, which is the premier channel for security professionals and hackers. And we have 4 tiers that are available: the Cyber Supporter, Agent, Guardian, and Master. And each tier gets their own Discord server and early access to content. But the Agent, Guardian, and Master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus a lot more. And to join them, you can simply click the link in the description below. You can also go to our homepage and click the join button, or you can go to youtube.com/@HankHacksHackers/join, and you'll be able to join the Hackaholics Anonymous community. I very much hope to see you inside of the Discord servers, even if it is just coming in as a very valued cyber supporter supporter. But if not, I hope I see you in the comment section inside of the YouTube channel. It's your boy Hank Hackers, and at Hank Hacks Hackers, your favorite network and system attacker / protector. Love, peace, and chicken grease. If no one else loves you, Hank loves you. I'll see you in the next video. Later.